Part 1 of Chapter 5 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by SammieC. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 5, Flight Controls. Introduction. This chapter focuses on the flight control systems a pilot uses to control the forces of flight and the aircraft's direction and attitude. It should be noted that flight control systems and characteristics can vary greatly, depending on the type of aircraft flown. The most basic flight control system designs are mechanical and date back to early aircraft. They operate with a collection of mechanical parts such as rods, cables, pulleys, and sometimes chains to transmit the forces of the flight deck controls to the control surfaces. Mechanical flight control systems are still used today in small general and sport category aircraft, where the aerodynamic forces are not excessive. See Figure 5-1. As aviation matured and aircraft designers learned more about aerodynamics, the industry produced larger and faster aircraft. Therefore, the aerodynamic forces acting upon the control surfaces increased exponentially. To make the control force required by pilots manageable, aircraft engineers designed more complex systems. At first, hydromechanical designs, consisting of a mechanical circuit and a hydraulic circuit, were used to reduce the complexity, weight, and limitations of mechanical flight control systems. See Figure 5-2. As aircraft became more sophisticated, the control surfaces were actuated by electric motors, digital computers, or fiber optic cables. Called fly-by-wire, this flight control system replaces the physical connection between pilot controls and the flight control surfaces with an electrical interface. In addition, in some large and fast aircraft, controls are boosted by hydraulically or electrically actuated systems. In both the fly-by-wire and boosted controls, the feel of the control reaction is fed back to the pilot by simulated means. Current research at the National Aeronautics and Space Administration, NASA, Dryden Flight Research Center, involves Intelligent Flight Control Systems, IFCS. The goal of this project is to develop an adaptive, neural network-based flight control system. Applied directly to flight control system feedback errors, IFCS provides adjustments to improve aircraft performance in normal flight, as well as with system failures. With IFCS, a pilot is able to maintain control and safely land an aircraft that has suffered a failure to a control surface or damage to the airframe. It also improves mission capability, increases the reliability and safety of flight, and eases the pilot workload. Today's aircraft employ a variety of flight control systems. For example, some aircraft in the sport pilot category rely on weight shift control to fly, while balloons use a standard burn technique. Helicopters utilize a cyclic to tilt the rotor in the desired direction, along with a collective to manipulate rotor pitch and anti-torque pedals to control yaw. See Figure 5-3. For additional information on flight control systems, refer to the appropriate handbook for information related to the flight control systems and characteristics of specific types of aircraft. Flight control systems. Flight controls. Aircraft flight control systems consist of primary and secondary systems. The ailerons, elevator or stabilator, and rudder constitute the primary control system and are required to control an aircraft safely during flight. Wing flaps, leading edge devices, spoilers, and trim systems constitute the secondary control system and improve the performance characteristics of the airplane or relieve the pilot of excessive control forces. Primary flight controls. Aircraft control systems are carefully designed to provide adequate responsiveness to control inputs while allowing a natural feel. At low airspeeds, the controls usually feel soft and sluggish, and the aircraft responds slowly to control applications. At higher airspeeds, the controls become increasingly firm and aircraft response is more rapid. Movement of any of the three primary flight control surfaces, ailerons, elevator or stabilator, or rudder, changes the airflow and pressure distribution over and around the airfoil. These changes affect the lift and drag produced by the airfoil/control surface combination and allow a pilot to control the aircraft about its 3 axes of rotation. Design features limit the amount of deflection of flight control surfaces. For example, control stop mechanisms may be incorporated into the flight control linkages, or movement of the control column and/or rudder pedals may be limited. The purpose of these design limits is to prevent the pilot from inadvertently over-controlling and overstressing the aircraft during normal maneuvers. A properly designed airplane is stable and easily controlled during normal maneuvering. Control surface inputs cause movement about the 3 axes of rotation. The types of stability an airplane exhibits also relate to the 3 axes of rotation. See Figure 5-4. Ailerons. Ailerons control roll about the longitudinal axis. The ailerons are attached to the outboard trailing edge of each wing and move in the opposite direction from each other. Ailerons are connected by cables, bell cranks, pulleys, and/or push-pull tubes to a control wheel or control stick. Moving the control wheel or control stick to the right causes the right aileron to deflect upward and the left aileron to deflect downward. The upward deflection of the right aileron decreases the camber, resulting in decreased lift on the right wing. The corresponding downward deflection of the left aileron increases the camber, resulting in increased lift on the left wing. Thus, the increased lift on the left wing and the decreased lift on the right wing causes the airplane to roll to the right. Adverse yaw. Since the downward deflected aileron produces more lift, as evidenced by the wing raising, it also produces more drag. This added drag causes the wing to slow down slightly. This results in the aircraft yawing toward the wing which had experienced an increase in lift and drag. From the pilot's perspective, the yaw is opposite the direction of the bank. The adverse yaw is a result of differential drag and the slight difference in the velocity of the left and right wings. See Figure 5-5. Adverse yaw becomes more pronounced at low airspeeds. At these slower airspeeds, aerodynamic pressure on control surfaces are low, and larger control inputs are required to effectively maneuver the airplane. As a result, the increase in aileron deflection causes an increase in adverse yaw. The yaw is especially evident in aircraft with long wingspans. Application of rudder is used to counteract adverse yaw. The amount of rudder control required is greatest at low airspeeds, high angles of attack, and with large aileron deflections. Like all control surfaces at lower airspeeds, the vertical stabilizer/rudder becomes less effective and magnifies the control problems associated with adverse yaw. All turns are coordinated by use of ailerons, rudder, and elevator. Applying aileron pressure is necessary to place the aircraft in the desired angle of bank, while simultaneous application of rudder pressure is necessary to counteract the resultant adverse yaw. Additionally, because more lift is required during a turn than when in straight and level flight, the angle of attack, AOA, must be increased by applying elevator back pressure. The steeper the turn, the more elevator back pressure is needed. As the desired angle of bank is established, aileron and rudder pressures should be relaxed. This stops the angle of bank from increasing because the aileron and rudder control surfaces are in a neutral and streamlined position. Elevator back pressure should be held constant to maintain altitude. The rollout from a turn is similar to the roll-in, except the flight controls are applied in the opposite direction. Aileron and rudder are applied in the direction of the rollout, or toward the high wing. As the angle of bank decreases, the elevator back pressure should be as relaxed as necessary to maintain altitude. In an attempt to reduce the effects of adverse yaw, manufacturers have engineered 4 systems: differential ailerons, freeze-type ailerons, coupled ailerons and rudder, and flaperons. Differential ailerons. With differential ailerons, one aileron is raised a greater distance than the other aileron is lowered for a given movement of the control wheel or control stick. This produces an increase in drag on the descending wing. The greater drag results from deflecting the up aileron on the descending wing to a greater angle than the down aileron on the rising wing. While adverse yaw is reduced, it's not eliminated completely. See Figure 5-6. Freeze-type ailerons. With a freeze-type aileron, when pressure is applied to the control wheel or control stick, the aileron that is being raised pivots on an offset hinge. This projects the leading edge of the aileron into the airflow and creates drag. It helps equalize the drag created by the lowered aileron on the opposite wing and reduces adverse yaw. See Figure 5-7. The freeze-type aileron also forms a slot so air flows smoothly over the lowered aileron, making it more effective at high angles of attack. Freeze-type ailerons may also be designed to function differentially. Like the differential aileron, the freeze-type aileron does not eliminate adverse yaw entirely. Coordinated rudder application is still needed wherever ailerons are applied. Coupled ailerons and rudder. Coupled ailerons and rudder are linked controls. This is accomplished with rudder-aileron interconnect springs, which help correct for aileron drag by automatically deflecting the rudder at the same time the ailerons are deflected. For example, when the control wheel or control stick is moved to produce a left roll, the interconnect cable and spring pulls forward on the left rudder pedal, just enough to prevent the nose of the aircraft from yawing to the right. The force applied to the rudder by the springs can be overridden if it becomes necessary to slip the aircraft. See Figure 5-8. Flaperons. Flaperons combine both aspects of flaps and ailerons. In addition to controlling the bank angle of an aircraft, like conventional ailerons, flaperons can be lowered together to function much the same as a dedicated set of flaps. The pilot retains separate controls for ailerons and flaps. A mixer is used to combine the separate pilot inputs into this single set of control surfaces called flaperons. Many designs that incorporate flaperons mount the control surfaces away from the wing to provide undisturbed airflow at high angles of attack and/or low airspeeds. See Figure 5-9. Elevator. The elevator controls pitch about the lateral axis. Like the ailerons on small aircraft, the elevator is connected to the control column in the flight deck by a series of mechanical linkages. Aft movement of the control column deflects the trailing edge of the elevator surface up. This is usually referred to as up elevator. See Figure 5-10. The up elevator position decreases the camber of the elevator and creates a downward aerodynamic force, which is greater than the normal tail-down force that exists in straight and level flight. The overall effect causes the tail of the aircraft to move down and the nose to pitch up. The pitching moment occurs about the center of gravity, CG. The strength of the pitching moment is determined by the distance between the CG and the horizontal tail surface, as well as by the aerodynamic effectiveness of the horizontal tail surface. Moving the control column forward has the opposite effect. In this case, elevator camber increases, creating more lift, less tail downforce, on the horizontal stabilizer/elevator. This moves the tail upward and pitches the nose down. Again, the pitching moment occurs about the CG. As mentioned earlier in the coverage on stability, power, thrust line, and the position of the horizontal tail surfaces on the empennage are factors in elevator effectiveness controlling pitch. For example, the horizontal tail surfaces may be attached near the lower part of the vertical stabilizer, at the midpoint, or at the high point, as in the T-tail design. T-tail. In a T-tail configuration, the elevator is above most of the effects of downwash from the propeller, as well as airflow around the fuselage and/or wings during normal flight conditions. Operation of the elevators in this undisturbed air allows control movements that are consistent throughout most flight regimes. T-tail designs have become popular on many light and large aircraft, especially those with aft fuselage-mounted engines, because the T-tail configuration removes the tail from the exhaust blast of the engines. Seaplanes and amphibians often have T-tails in order to keep the horizontal surfaces as far from the water as possible. An additional benefit is reduced vibration and noise inside the aircraft. At slow speeds, the elevator on a T-tail aircraft must be moved through a larger number of degrees of travel to raise the nose a given amount than on a conventional tail aircraft. This is because the conventional tail aircraft has the downwash from the propeller pushing down on the tail to assist in raising the nose. Since controls on aircraft are rigged so that increasing control forces are required for increased control travel, the forces required to raise the nose of a T-tail aircraft are greater than those for a conventional tail aircraft. Longitudinal stability of a trimmed aircraft is the same for both types of configuration, but the pilot must be aware that the required control forces are greater at slow speeds during takeoffs, landings, or stalls than for similar-size aircraft equipped with conventional tails. T-tail airplanes also require additional design considerations to counter the problem of flutter. Since the weight of the horizontal surfaces is at the top of the vertical stabilizer, the moment arm created causes high loads on the vertical stabilizer, which can result in flutter. Engineers must compensate for this by increasing the design stiffness of the vertical stabilizer, usually resulting in a weight penalty over conventional tail designs. When flying at a very high AOA with a low airspeed and an aft CG, the T-tail aircraft may be susceptible to a deep stall. In a deep stall, the airflow over the horizontal tail is blanketed by the disturbed airflow from the wings and fuselage. In these circumstances, elevator or stabilator control could be diminished, making it difficult to recover from the stall. It should be noted that an aft CG is often a contributing factor in these incidents, since similar recovery problems are also found with conventional tail aircraft with an aft CG. See Figure 5-11. Since flight at a high AOA with a low airspeed and an aft CG position can be dangerous, many aircraft have systems to compensate for this situation. The systems range from control stops to elevator downsprings. An elevator downspring assists in lowering the nose of the aircraft to prevent a stall caused by the aft CG position. The stall occurs because the properly trimmed airplane is flying with the elevator in a trailing edge down position, forcing the tail up and the nose down. In this unstable condition, if the aircraft encounters turbulence and slows down further, the trim tab no longer positions the elevator in the nose down position. The elevator then streamlines and the nose of the aircraft pitches upward, possibly resulting in a stall. The elevator downspring produces a mechanical load on the elevator, causing it to move toward the nose-down position if not otherwise balanced. The elevator trim tab balances the elevator downspring to position the elevator in a trimmed position. When the trim tab becomes ineffective, the downspring drives the elevator to a nose-down position. The nose of the aircraft lowers, speed builds up, and a stall is prevented. See Figure 5-12. The elevator must also have sufficient authority to hold the nose of the aircraft up during the round-out for a landing. In this case, a forward CG may cause a problem. During the landing flare, power is usually reduced, which decreases the airflow over the empennage. This, coupled with reduced landing speed, makes the elevator less effective. As this discussion demonstrates, pilots must understand and follow proper loading procedures, particularly with regard to the CG position. More information on aircraft loading, as well as weight and balance, is included in Chapter 9, Weight and Balance. Stabilator. As mentioned in Chapter 2, Aircraft Structure, a stabilator is essentially a one-piece horizontal stabilizer that pivots from a central hinge point. When the control column is pulled back, it raises the stabilator's trailing edge, pulling the airplane's nose up. Pushing the control column forward lowers the trailing edge of the stabilator and pitches the nose of the airplane down. Because stabilators pivot around a central hinge point, they are extremely sensitive to control inputs and aerodynamic loads. Anti-servo tabs are incorporated on the trailing edge to decrease sensitivity. They deflect in the same direction as the stabilator. This results in an increase in the force required to move the stabilator, thus making it less prone to pilot-induced overcontrolling. In addition, a balance weight is usually incorporated in front of the main spar. The balance weight may project into the empennage or may be incorporated on the forward portion of the stabilator tips. See Figure 5-13. Canard. The canard design utilizes the concept of two lifting surfaces, the canard functioning as a horizontal stabilizer located in front of the main wings. In effect, the canard is an airfoil similar to the horizontal surface on a conventional aft tail design. The difference is that the canard actually creates lift and holds the nose up, as opposed to the aft tail design, which exerts downward force on the tail to prevent the nose from rotating downward. See Figure 5-14. The canard design dates back to the pioneer days of aviation, most notably used on the Wright Flyer. Recently, the canard configuration has regained popularity and is appearing on newer aircraft. Canard designs include two types, one with a horizontal surface of about the same size as a normal aft tail design, and the other with a surface of the same approximate size and airfoil of the aft-mounted wing known as a tandem wing configuration. Theoretically, the canard is considered more efficient because using the horizontal surface to help lift the weight of the aircraft should result in less drag for a given amount of lift. Rudder. The rudder controls movement of the aircraft about its vertical axis. This motion is called yaw. Like the other primary control surfaces, the rudder is a movable surface, hinged to a fixed surface, in this case to the vertical stabilizer, or fin. Moving the left or right rudder pedal controls the rudder. When the rudder is deflected into the airflow, a horizontal force is exerted in the opposite direction. See Figure 5-15. By pushing the left pedal, the rudder moves left. This alters the airflow around the vertical stabilizer/rudder and creates a sideward lift that moves the tail to the right and yaws the nose of the airplane to the left. Rudder effectiveness increases with speed. Therefore, large deflections at low speeds and small deflections at high speeds may be required to provide the desired reaction. In propeller-driven aircraft, any slipstream flowing over the rudder increases its effectiveness. V-tail. The V-tail design utilizes two slanted tail surfaces to perform the same functions as the surfaces of a conventional elevator and rudder configuration. The fixed surfaces act as both horizontal and vertical stabilizers. See Figure 5-16. The movable surfaces, which are usually called ruddervators, are connected through a special linkage that allows the control wheel to move both surfaces simultaneously. On the other hand, displacement of the rudder pedals moves the surfaces differentially, thereby providing directional control. When both rudder and elevator controls are moved by the pilot, a control mixing mechanism moves each surface the appropriate amount. The control system for the V-tail is more complex than that required for a conventional tail. In addition, the V-tail design is more susceptible to Dutch roll tendencies than a conventional tail, and total reduction in drag is minimal. End of Part 1 of Chapter 5. Part 2 of Chapter 5 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by SammieC. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 5, Flight Controls. Part 2. Secondary Flight Controls. Secondary flight control systems may consist of wing flaps, leading-edge devices, spoilers, and trim systems. Flaps. Flaps are the most common high-lift devices used on aircraft. These surfaces, which are attached to the trailing edge of the wing, increase both lift and induced drag for any given AOA. Flaps allow a compromise between high cruising speed and low landing speed, because they may be extended when needed and retracted into the wing structure when not needed. There are 4 common types of flaps: plain, split, slotted, and Fowler flaps. See Figure 5-17. The plain flap is the simplest of the 4 types. It increases the airfoil camber, resulting in a significant increase in the coefficient of lift, CL, at a given AOA. At the same time, it greatly increases drag and moves the center of pressure, CP, aft on the airfoil, resulting in a nose-down pitching moment. The split flap is deflected from the lower surface of the airfoil and produces a slightly greater increase in lift than the plain flap. More drag is created because of the turbulent air pattern produced behind the airfoil. When fully extended, both plain and split flaps produce high drag with little additional lift. The most popular flap on aircraft today is a slotted flap. Variations of this design are used for small aircraft as well as for large ones. Slotted flaps increase the lift coefficient significantly more than plain or split flaps. On small aircraft, the hinge is located below the lower surface of the flap, and when the flap is lowered, a duct forms between the flap well in the wing and the leading edge of the flap. When the slotted flap is lowered, high-energy air from the lower surface is ducted to the flap's upper surface. The high-energy air from the slot accelerates the upper surface boundary layer and delays airflow separation, providing a higher CL. Thus, the slotted flap produces much greater increases in maximum coefficient of lift, CL max, than the plain or split flap. While there are many types of slotted flaps, large aircraft often have double and even triple slotted flaps. These allow the maximum increase in drag without the airflow over the flap separating and destroying the lift they produce. Fowler flaps are a type of slotted flap. This flap design not only changes the camber of the wing, it also increases the wing area. Instead of rotating down on a hinge, it slides backwards, on tracks. In the first portion of its extension, it increases the drag very little, but increases the lift a great deal, as it increases both the area and camber. As the extension continues, the flap deflects downward. During the last portion of its travel, the flap increases the drag with little additional increase in lift. Leading edge devices. High-lift devices also can be applied to the leading edge of the airfoil. The most common types are fixed slots, movable slats, leading edge flaps, and cuffs. See Figure 5-18. Fixed slots direct airflow to the upper wing surface and delay airflow separation at higher angles of attack. The slot does not increase the wing camber, but allows a higher maximum CL because the stall is delayed until the wing reaches a greater AOA. Movable slats consist of leading edge segments, which move on tracks. At low angles of attack, each slat is held flush against the wing's leading edge by the high pressure that forms at the wing's leading edge. As the AOA increases, the high-pressure area moves aft, below the lower surface of the wing, allowing the slats to move forward. Some slats, however, are pilot-operated and can be deployed at any AOA. Opening a slat allows the air below the wing to flow over the wing's upper surface, delaying airflow separation. Leading edge flaps, like trailing edge flaps, are used to increase both CL max and the camber of the wings. This type of leading edge device is frequently used in conjunction with trailing edge flaps and can reduce the nose-down pitching movement produced by the latter. As is true with trailing edge flaps, a small increment of leading edge flaps increases lift to a much greater extent than drag. As greater amounts of flaps are extended, drag increases at a greater rate than lift. Leading edge cuffs, like leading edge flaps and trailing edge flaps, are used to increase both CL max and the camber of the wings. Unlike leading edge flaps and trailing edge flaps, leading edge cuffs are fixed aerodynamic devices. In most cases, leading edge cuffs extend the leading edge down and forward. This causes the airflow to attach better to the upper surface of the wing at higher angles of attack, thus lowering an aircraft's stall speed. The fixed nature of leading edge cuffs extracts a penalty in maximum cruise airspeed, but recent advances in design and technology have reduced this penalty. Spoilers. Found on many gliders and some aircraft, high-drag devices called spoilers are deployed from the wings to spoil the smooth airflow, reducing lift and increasing drag. On gliders, spoilers are most often used to control rate of descent for accurate landings. On other aircraft, spoilers are often used for roll control, an advantage of which is the elimination of adverse yaw. To turn right, for example, the spoiler on the right wing is raised, destroying some of the lift and creating more drag on the right. The right wing drops, and the aircraft banks and yaws to the right. Deploying spoilers on both wings at the same time allows the aircraft to descend without gaining speed. Spoilers are also deployed to help reduce ground roll after landing. By destroying lift, they transfer weight to the wheels, improving braking effectiveness. See Figure 5-19. Trim systems. Although an aircraft can be operated throughout a wide range of attitudes, airspeeds, and power settings, it can be designed to fly hands-off within only a very limited combination of these variables. Trim systems are used to relieve the pilot of the need to maintain constant pressure on the flight controls, and usually consist of flight deck controls and small hinged devices attached to the trailing edge of one or more of the primary flight control surfaces. Designed to help minimize a pilot's workload, trim systems aerodynamically assist movement and position of the flight control surface to which they are attached. Common types of trim systems include trim tabs, balance tabs, anti-servo tabs, ground adjustable tabs, and an adjustable stabilizer. Trim tabs. The most common installation on small aircraft is a single trim tab attached to the trailing edge of the elevator. Most trim tabs are manually operated by a small vertically mounted control wheel. However, a trim crank may be found in some aircraft. The flight deck control includes a trim tab position indicator. Placing the trim control in the full nose down position moves the trim tab to its full up position. With the trim tab up and into the airstream, the airflow over the horizontal tail surface tends to force the trailing edge of the elevator down. This causes the tail of the airplane to move up and the nose to move down. See Figure 5-20. If the trim tab is set to the full nose up position, the tab moves to its full down position. In this case, the air flowing under the horizontal tail surface hits the tab and forces the trailing edge of the elevator up, reducing the elevator's AOA. This causes the tail of the airplane to move down and the nose to move up. In spite of the opposing directional movement of the trim tab and the elevator, control of trim is natural to a pilot. If the pilot needs to exert constant back pressure on a control column, the need for nose-up trim is indicated. The normal trim procedure is to continue trimming until the aircraft is balanced and the nose-heavy condition is no longer apparent. Pilots normally establish the desired power, pitch attitude, and configuration first, and then trim the aircraft to relieve control pressures that may exist for that flight condition. Anytime power, pitch attitude, or configuration is changed, expect that retrimming will be necessary to relieve the control pressures for the new flight condition. Balance tabs. The control forces may be excessively high in some aircraft, and, in order to decrease them, the manufacturer may use balance tabs. They look like trim tabs and are hinged in approximately the same places as trim tabs. The essential difference between the two is that the balancing tab is coupled to the control surface rod, so that when the primary control surface is moved in any direction, the tab automatically moves in the opposite direction. The airflow striking the tab counterbalances some of the air pressure against the primary control surface and enables the pilot to move more easily and hold the control surface in position. If the linkage between the balance tab and the fixed surface is adjustable from the flight deck, the tab acts as a combination trim and balance tab that can be adjusted to any desired deflection. Anti-servo tabs. Anti-servo tabs work in the same manner as balance tabs, except instead of moving in the opposite direction, they move in the same direction as the trailing edge of the stabilator. In addition to decreasing the sensitivity of the stabilator, an anti-servo tab also functions as a trim device to relieve control pressure and maintain the stabilator in the desired position. The fixed end of the linkage is on the opposite side of the surface from the horn on the tab. When the trailing edge of the stabilator moves up, the linkage forces the trailing edge of the tab up. When the stabilator moves down, the tab also moves down. Conversely, trim tabs on elevators move opposite of the control surface. See Figure 5-21. Ground adjustable tabs. Many small aircraft have a non-movable metal trim tab on the rudder. This tab is bent in one direction or the other while on the ground to apply a trim force to the rudder. The correct displacement is determined by trial and error. Usually, small adjustments are necessary until the aircraft no longer skids left or right during normal cruising flight. See Figure 5-22. Adjustable stabilizer. Rather than using a movable tab on the trailing edge of the elevator, some aircraft have an adjustable stabilizer. With this arrangement, linkages pivot the horizontal stabilizer about its rear spar. This is accomplished by use of a jack screw mounted on the leading edge of the stabilator. See Figure 5-23. On small aircraft, the jack screw is cable-operated with a trim wheel or crank. On larger aircraft, it is motor-driven. The trimming effect and flight deck indications for an adjustable stabilizer are similar to those of a trim tab. Autopilot. Autopilot is an automatic flight control system that keeps an aircraft in level flight or on a set course. It can be directed by the pilot or it may be coupled to a radio navigation signal. Autopilot reduces the physical and mental demands on a pilot and increases safety. The common features available on an autopilot are altitude and heading hold. The simplest systems use gyroscopic attitude indicators and magnetic compasses to control servos connected to the flight control system. See Figure 5-24. The number and location of these servos depends on the complexity of the system. For example, a single-axis autopilot controls the aircraft about the longitudinal axis, and a servo actuates the ailerons. A three-axis autopilot controls the aircraft about the longitudinal, lateral, and vertical axes. 3 different servos actuate ailerons, elevator, and rudder. More advanced systems often include a vertical speed and/or indicated airspeed hold mode. Advanced autopilot systems are coupled to navigational aids through a flight director. The autopilot system also incorporates a disconnect safety feature to disengage the system automatically or manually. These autopilots work with inertial navigation systems, global positioning systems, GPS, and flight computers to control the aircraft. In fly-by-wire systems, the autopilot is an integrated component. Additionally, autopilots can be manually overridden. Because autopilot systems differ widely in their operation, refer to the autopilot operating instructions in the Airplane Flight Manual, AFM, or the Pilot's Operating Handbook, POH. Chapter Summary. Because flight control systems and aerodynamic characteristics vary greatly between aircraft, it is essential that a pilot become familiar with the primary and secondary flight control systems of the aircraft being flown. The primary source of this information is the AFM or the POH. Various manufacturer and owner group websites can also be a valuable source of additional information. End of Part 2 of Chapter 5.
Part 1 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 6. Aircraft Systems. Introduction. This chapter covers the primary systems found on most aircraft. These include the engine, propeller, induction, ignition, as well as the fuel, lubrication, cooling, electrical, landing gear, and environmental control systems. Power plant. An aircraft engine, or power plant, produces thrust to propel an aircraft. Reciprocating engines and turboprop engines work in combination with the propeller to produce thrust. Turbojet and turbofan engines produce thrust by increasing the velocity of air flowing through the engine. All of these power plants also drive the various systems that support the operation of an aircraft. Reciprocating engines. Most small aircraft are designed with reciprocating engines. The name is derived from the back and forth, or reciprocating, movement of the pistons, which produces the mechanical energy necessary to accomplish work. Driven by a revitalization of general aviation, or GA, industry and advances in both material and engine design, reciprocating engine technology has improved dramatically over the past 2 decades. The integration of computerized engine management systems has improved fuel efficiency, decreased emissions, and reduced pilot workload. Reciprocating engines operate on the basic principle of converting chemical energy, fuel, into mechanical energy. This conversion occurs within the cylinders of the engine through the process of combustion. The 2 primary reciprocating engine designs are the spark ignition and the compression ignition. The spark ignition reciprocating engine has served as a power plant of choice for many years. In an effort to reduce operating costs, simplify design, and improve reliability, several engine manufacturers are turning to compression ignition as a viable alternative. Often referred to as jet fuel piston engines, compression ignition engines have the added advantage of utilizing readily available and lower cost diesel or jet fuel. The main mechanical components of the spark ignition and compression ignition engine are essentially the same. Both use cylindrical combustion chambers and pistons that travel the length of the cylinders to convert linear motion into the rotary motion of the crankshaft. The main difference between spark ignition and compression ignition is the process of igniting the fuel. Spark ignition engines use a spark plug to ignite a pre-mixed fuel-air mixture. Fuel-air mixture is the rate of weight of the fuel and weight of air in the mixture to be burned. A compression ignition engine first compresses the air in the cylinder, raising its temperature to a degree necessary for automatic ignition when fuel is injected into the cylinder. These 2 engine designs can further be classified as 1. Cylindrical arrangement with respect to the crankshaft, radial, inline, V-type, or opposed. 2. Operating cycle, 2 or 4. And 3. Method of cooling, liquid or air. Radial engines were widely used during World War II, and many are still in service today. With these engines, a row or row of cylinders are arranged in a circular pattern around the crankcase. The main advantage of a radial engine is the favorable power-to-weight ratio, figure 6-1. Inline engines have a comparatively small frontal area, but their power-to-weight ratios are relatively low. In addition, the rearmost cylinders of an air-cooled inline engine receive very little cooling air, so the engines are normally limited to 4 or 6 cylinders. V-type engines provide more horsepower than inline engines and still retain a small frontal area. Continued improvements in engine design led to the development of a horizontally opposed engine, which remains the most popular reciprocating engines used on smaller aircraft. These engines always have an even number of cylinders, since a cylinder on one side of the crankcase opposes a cylinder on the other side. Figure 6-2. The majority of these engines are air-cooled and are usually mounted in a horizontal position when installed on fixed-winged airplanes. Opposed-type engines have a higher power-to-weight ratios because they have a comparatively small, lightweight crankcase. In addition, the compact cylinder arrangement reduces the fuel's frontal area and allows a streamlined installation that minimizes aerodynamic drag. Depending on the engine manufacturer, all of these arrangements can design to utilize spark or compression ignition and operate on either a 2 or 4-stroke cycle. In a 2-stroke engine, the conversion of chemical energy into mechanical energy occurs over a 2-stroke operating cycle. The intake, compression, power, and exhaust processes occur in only 2 strokes of the piston rather than the more common 4 strokes. Because a 2-stroke engine has a power stroke each revolution of the crankshaft, it typically has a higher power-to-weight ratio than a comparable 4-stroke engine. Due to the inherent inefficiency and disproportionate emissions of the earliest designs, use of the 2-stroke engine has been limited in aviation. Recent advances in material and engine design have reduced many of the negative characteristics associated with 2-stroke engines. Modern 2-stroke engines often use conventional oil sumps, oil pumps, and full pressure-fed lubrication systems. The use of direct fuel injection and pressurized air, characteristic of advanced compression ignition engines, make 2-stroke compression ignition engines a viable alternative to the more common 4-stroke spark ignition designs. Figure 6-3. Spark ignition 4-stroke engines remain the most common design used in aviation today. Figure 6-4. The main parts of a spark ignition reciprocating engine include the cylinders, crankcase, and accessory housing. The intake/exhaust valves, spark plugs, and pistons are located in the cylinders. The crankshaft and connecting rods are located in the crankcase. The magnetos are normally located on the engine accessory housing. In a 4-stroke engine, the conversion of chemical energy into mechanical energy occurs over a 4-stroke operating cycle. The intake, compression, power, and exhaust processes occur in 4 separate strokes of the piston. 1. The intake stroke begins as the piston starts its downward travel. When this happens, the intake valve opens and the fuel/air mixture is drawn into the cylinder. 2. The compression stroke begins when the intake valve closes and the piston starts moving back to the top of the cylinder. This phase of the cycle is used to obtain a much greater power output from the fuel/air mixture once it is ignited. 3. The power stroke begins when the fuel/air mixture is ignited. This causes a tremendous pressure increase in the cylinder and forces the piston downward away from the cylinder head, creating the power that turns the crankshaft. 4. The exhaust stroke is used to purge the cylinder of burned gases. It begins when the exhaust valve opens and the piston starts to move towards the cylinder head once again. Even when the engine is operated at a fairly low speed, the 4-stroke cycle takes place several hundred times each minute. Figure 6-5. In a 4-cylinder engine, each cylinder operates on a different stroke. Continuous rotation of a crankshaft is maintained by the precise timing of power strokes in each cylinder. Continuous operation of the engine depends on the simultaneous function of auxiliary systems, including the induction, ignition, fuel, oil, cooling, and exhaust systems. The latest advance in aircraft reciprocating engines was pioneered in the mid-1960s by Frank Thielert, who looked to the automotive industry for answers on how to integrate diesel technology into an aircraft engine. The advantage of a diesel-fueled reciprocating engine lies in the physical similarity of diesel and kerosene. Aircraft equipped with a diesel piston engine runs on standard aviation fuel kerosene, which provides more independence, higher reliability, lower consumption, and operational cost saving. In 1999, Thielert formed Thielert Aircraft Engines, TAE, to design, develop, certify, and manufacture a brand new Jet A-burning diesel cycle engine, also known as jet-fueled piston engine, for the GA industry. By March 2001, the first prototype engine became the first certified diesel engine since World War II. TAE continues to design and develops diesel cycle engines, and other engine manufacturers, such as Société de Modélisation Aeronautique, SMA, now offer jet-fueled piston engines as well. TAE engines can be found on the Diamond DA40 single and the DA42 Twin Star, the first diesel engine to be part of the type certificate of a new original equipment manufacturer, OEM, aircraft. These engines have also gained a toehold in the retrofit market with the Supplemental Type Certificate, STC, to re-engine the Cessna 172 models and the Piper PA-28 family. The jet-fueled piston engines technology has continued to progress, and a full authority digital engine control, FADEC, discussed more fully later in this chapter, is standard on such equipped aircraft, which minimizes complication of engine control. By 2007, various jet-fueled piston aircraft had logged well over 600,000 hours of service. Propeller. The propeller is a rotating airfoil subject to induced drag, stalls, and other aerodynamic principles that apply to any airfoil. It provides the necessary thrust to pull, or in some cases push, the aircraft through the air. The engine power is used to rotate the propeller, which in turn generates thrusts very similar to the manner in which a wing produces lift. The amount of thrust produced depends on the shape of the airfoil, the angle of attack of the propeller blade, and the revolutions per minute, RPM, of the engine. The propeller itself is twisted so the blade angle changes from hub to tip. The greatest angle of incidence, or highest pitch, is at the hub, while the smallest angle of incidence, or smallest pitch, is at the tip. Figure 6-6. The reason for the twist is to produce uniform lift from the hub to the tip. As the blade rotates, there is a difference in the actual speed of the various portions of the blade. The tip of the blade travels faster than the part near the hub because the tip travels a greater distance than the hub in the same length of time. Figure 6-7. Changing the angle of incidence, pitch, from the hub to the tip to correspond with the speed produces uniform lift throughout the length of the blade. A propeller blade designed with the same angle of incidence throughout its entire length would be inefficient because as airspeed increases in flight, the portion near to the hub would have a negative angle of attack while the blade tip would be stalled. Small aircraft are equipped with either one or two types of propeller. One is the fixed pitch and the other is adjustable pitch. Fixed pitch propeller. A propeller with fixed blade angles is a fixed pitch propeller. The pitch of the propeller is set by the manufacturer and cannot be changed. Since a fixed pitch propeller achieves the best efficiency only at a given combination of airspeed and RPM, the pitch setting is ideal for neither cruise nor climb. Thus, the aircraft suffers a bit in each performance category. The fixed pitch propeller is used when low weight, simplicity, and low cost are needed. There are two types of fixed pitch propellers, climb and cruise. Whether the airplane has a climb or cruise propeller installed depends upon its intended use. The climb propeller has a lower pitch, therefore less drag. Less drag results in a higher RPM and more horsepower capability, which increases performance during takeoffs and climbs, but decreases performance during cruising flight. The cruise propeller has a higher pitch, therefore more drag. More drag results in lower RPM and less horsepower capability, which decreases performance during takeoffs and climbs, but increases efficiency during cruising flight. The propeller is usually mounted on a shaft, which may be an extension of the engine crankshaft. In this case, the RPM of the propeller would be the same as the crankshaft RPM. On some engines, the propeller is mounted on a shaft geared to the engine crankshaft. In this type, the RPM of the propeller is different than that of the engine. In a fixed pitch propeller, the tachometer is an indicator of engine power. Figure 6-8. A tachometer is calibrated in hundreds of RPM and gives a direct indication of the engine and propeller RPM. The instrument is color-coded, with a green arc denoting the maximum continuous operating RPM. Some tachometers have additional markings to reflect engine and/or propeller limitations. The manufacturer's recommendations should be used as a reference to clarify any misunderstanding of tachometer markings. The RPM is regulated by the throttle, which controls the fuel/airflow to the engine. At a given altitude, the higher the tachometer reading, the higher the power output of the engine. When operating altitude increases, the tachometer may not show correct power output of the engine. For example, 2300 RPM at 5,000 feet produces less horsepower than 2300 RPM at sea level because power output depends on air density. Air density decreases as altitude increases, and a decrease in air density, higher density altitude, decreases the power output of the engine. As altitude changes, the position of the throttle must be changed to maintain the same RPM. As altitude is increased, the throttle must be opened further to indicate the same RPM as at a lower altitude. End of Part 1 of Chapter 6. Part 2 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 6, Part 2. Adjustable Pitch Propeller. The adjustable pitch propeller was the forerunner of the constant speed propeller. It is a propeller with blades whose pitch can be adjusted on the ground with the engine not running, but which cannot be adjusted in flight. It is also referred to as the ground adjustable propeller. By the 1930s, pioneer aviation inventors were laying the groundwork for automatic pitch change mechanisms, which is why the term sometimes refers to modern constant speed propellers that are adjustable in flight. The first adjustable pitch propeller systems provided only two pitch settings, low and high. Today, most adjustable pitch propeller systems are capable of a range of pitch settings. A constant speed propeller is a controllable pitch propeller whose pitch is automatically varied in flight by a governor maintaining constant RPM despite varying air loads. It is the most common type of adjustable pitch propeller. The main advantage of a constant speed propeller is that it converts a high percentage of brake horsepower, bhp, into thrust horsepower, THP, over a wide range of RPM and airspeed combinations. A constant speed propeller is more efficient than other propellers because it allows selection of the most efficient engine RPM for the given conditions. An aircraft with a constant speed propeller has two controls, the throttle and the propeller control. The throttle controls power output and the propeller control regulates engine RPM. This in turn regulates propeller RPM, which is registered on the tachometer. Once a specific RPM is selected, a governor automatically adjusts the propeller blade angle as necessary to maintain the selected RPM. For example, after setting the desired RPM during cruising flight, an increase in airspeed or decrease in propeller load will cause the propeller blade angle to increase as necessary to maintain the selected RPM. A reduction in airspeed or increase in propeller load will cause the propeller blade angle to decrease. The propeller's constant speed range, defined by the high and low pitch stops, is the range of possible blade angles for a constant speed propeller. As long as the propeller blade angle is within the constant speed range and not against either pitch stop, a constant engine RPM will be maintained. If the propeller blades contact a pitch stop, the engine RPM will increase or decrease as appropriate, with changes in airspeed and propeller load. For example, once a specific RPM has been selected, if aircraft speed decreases enough to rotate the propeller blades until they contact the low pitch stop, any further decrease in airspeed will cause engine RPM to decrease the same way as if a fixed pitch propeller were installed. The same holds true when an aircraft equipped with a constant speed propeller accelerates to a faster airspeed. As the aircraft accelerates, the propeller blade angle increases to maintain the selected RPM until the high pitch stop is reached. Once this occurs, the blade angle cannot increase any further, and the engine RPM increases. On aircraft equipped with a constant speed propeller, power output is controlled by the throttle and indicated by a manifold pressure gauge. The gauge measures the absolute pressure of the fuel/air mixture inside the intake manifold, and is more correctly a measure of manifold absolute pressure, MAP. At a constant RPM and altitude, the amount of power produced is directly related to the fuel/airflow being delivered to the combustion chamber. As the throttle setting is increased, more fuel and air flows to the engine and MAP increases. When the engine is not running, the manifold pressure gauge indicates ambient air pressure, i.e. 29.92 inches mercury. When the engine is started, the manifold pressure indication will decrease to a value less than ambient pressure, i.e. idle at 12 inches mercury. Engine failure or power loss is indicated on the manifold gauge as an increase in manifold pressure to a value corresponding to the ambient air pressure at an altitude where the failure occurred. See Figure 6-9. The manifold pressure gauge is color-coded to indicate the engine's operating range. The face of the manifold pressure gauge contains a green arc to show the normal operating range, and a red radial line to indicate the upper limit of manifold pressure. For any given RPM, there is a manifold pressure that should not be exceeded. If manifold pressure is excessive for a given RPM, the pressure within the cylinders could be exceeded, placing undue stress on the cylinders. If repeated too frequently, this stress can weaken the cylinder components and eventually cause engine failure. As a general rule, manifold pressure, in inches, should be less than the RPM. A pilot can avoid conditions that overstress the cylinders by being constantly aware of the RPM, especially when increasing the manifold pressure. Conform to the manufacturer's recommendations for power settings of a particular engine to maintain the proper relationship between manifold pressure and RPM. When both manifold pressure and RPM need to be changed, avoid engine overstress by making power adjustments in the proper order. When power settings are being decreased, reduce manifold pressure before reducing RPM. If RPM is reduced before manifold pressure will automatically increase, possibly exceeding the manufacturer's tolerances. When power settings are being increased, reverse the order. Increase RPM first, then manifold pressure. To prevent damage to radial engines, minimize operating time at maximum RPM and manifold pressure, and avoid operation at maximum RPM and low manifold pressure. The engine and/or airframe manufacturer's recommendations should be followed to prevent severe wear, fatigue, and damage to high-performance reciprocating engines. Induction systems. The induction system brings in air from the outside, mixes it with fuel, and delivers the fuel/air mixture to the cylinder where combustion occurs. Outside air enters the induction system through an intake port on the front of the engine cowling. This port normally contains an air filter that inhibits the entry of dust and other foreign objects. Since the filter may occasionally become clogged, an alternate source of air must be available. Usually, the alternate air comes from inside the engine cowling, where it bypasses a clogged air filter. Some alternative air sources function automatically, while others operate manually. Two types of induction systems are commonly used in small aircraft engines. 1. The carburetor system, which mixes the fuel and air in the carburetor before this mixture enters the intake manifold. 2. The fuel injection system, which mixes the fuel and air immediately before entry into each cylinder or injects fuel directly into each cylinder. Carburetor systems. Carburetors are classified as either float type or pressure type. The float type of carburetor, complete with idling, accelerating, mixture control, idle cutoff, and power enrichment systems, is probably the most common of all carburetor types. Pressure carburetors are usually not found on small aircraft. The basic difference between a float type and a pressure type carburetor is the delivery of fuel. The pressure type carburetor delivers fuel under pressure by a fuel pump. In the operation of the float type carburetor system, the outside air first flows through an air filter, usually located at an air intake in the front part of the engine cowling. This filtered air flows into the carburetor and through a venturi, a narrow throat in the carburetor. When the air flows through the venturi, a low pressure area is created, which forces the fuel to flow through a main fuel jet located at the throat. The fuel then flows into the airstream, where it is mixed with the flowing air. See Figure 6-10. The fuel/air mixture is then drawn through the intake manifold and into the combustion chambers where it is ignited. The float type carburetor acquires its name from a float, which rests on fuel within the float chamber. A needle attached to the float opens and closes an opening at the bottom of the carburetor bowl. This meters the correct amount of fuel into the carburetor, depending upon the position of the float, which is controlled by the level of fuel in the float chamber. When the level of fuel forces the float to rise, the needle valve closes the fuel opening and shuts off fuel flow to the carburetor. The needle valve opens again when the engine requires additional fuel. The flow of the fuel/air mixture to the combustion chambers is regulated by the throttle valve, which is controlled by the throttle in the flight deck. The float type carburetor has several distinct disadvantages. In the first place, imagine the effect that abrupt maneuvers have on the float action. In the second place, the fact that its fuel must be discharged at low pressure leads to an incomplete vaporization and difficulty in discharging fuel into some types of supercharged systems. The chief disadvantage of the float carburetor, however, is its icing tendency. Since the float carburetor must discharge fuel at a point of low pressure, the discharge nozzle must be located at the venturi throat, and the throttle valve must be on the engine side of the discharge nozzle. This means that the drop in temperature due to fuel vaporization takes place within the venturi. As a result, ice readily forms in the venturi and on the throat valve. A pressure type carburetor discharges fuel into the airstream at a pressure well above atmospheric. This results in better vaporization and permits the discharge of fuel into the airstream on the engine side of the throttle valve. With the discharge nozzle located at this point, the drop in temperature due to fuel vaporization takes place after the air has passed the throttle valve and at a point when engine heat tends to offset it. Thus, the danger of fuel vaporization icing is practically eliminated. The effects of rapid maneuvers and rough air on the pressure type carburetors are negligible since their fuel chambers remain filled under all operating conditions. Mixture control. Carburetors are normally calibrated at sea level pressure, where the correct fuel-to-air mixture ratio is established with the mixture control set in the full rich position. However, as altitude increases, the density of air entering the carburetor decreases, while the density of the fuel remains the same. This creates a progressively richer mixture, which can result in engine roughness and an appreciable loss of power. The roughness is normally due to spark plug fouling from excessive carbon buildup on the plugs. Carbon buildup occurs because the rich mixture lowers the temperature inside the cylinder, inhibiting complete combustion of the fuel. This condition may occur during the pre-takeoff run-up at high elevation airports and during climb or cruise flight at high altitudes. To maintain the correct fuel/air mixture, the mixture must be leaned using the mixture control. Leaning the mixture decreases fuel flow, which compensates for the decreased air density at high altitude. During a descent from high altitude, the mixture must be enriched, or it may become too lean. An overly lean mixture causes detonation, which may result in rough engine operation, overheating, and a loss of power. The best way to maintain the proper mixture is to monitor the engine temperature and enrich the mixture as needed. Proper mixture control and better fuel economy for fuel-injected engines can be achieved by the use of an exhaust gas temperature (EGT) gauge. Since the process of adjusting the mixture can vary from one aircraft to another, it is important to refer to the Airplane Flight Manual (AFM) or the Pilot's Operating Handbook POH, to determine the specific procedures for a given aircraft. Carburetor icing. As mentioned earlier, one disadvantage of the float-type carburetor is in its icing tendency. Carburetor ice occurs due to the effect of fuel vaporization and the decrease in air pressure in the venturi, which causes a sharp temperature drop in the carburetor. If water vapor in the air condenses when the carburetor temperature is at or below freezing, ice may form on internal surfaces of the carburetor, including the throttle valve. See Figure 611. The reduced air pressure, as well as the vaporization of fuel, contributes to the temperature decrease in the carburetor. Ice generally forms in the vicinity of the throttle valve and in the venturi throat. This restricts the flow of the fuel/air mixture and reduces power. If enough ice builds up, the engine may cease to operate. Carburetor ice is most likely to occur when temperatures are below 70 degrees Fahrenheit or 21 degrees Celsius, and the relative humidity is above 80%. Due to the sudden cooling that takes place in the carburetor, icing can even occur with temperatures as high as 100 degrees Fahrenheit or 38 degrees Celsius, and humidity as low as 50%. This temperature drop can be as much as 60 to 70 absolute versus relative degrees Fahrenheit. 70 times 100 divided by 180 equals 38.89 degrees Celsius. Remember, 180 degrees Fahrenheit from freezing to boiling versus 100 degrees for the Celsius scale. Therefore, at an outside air temperature of 100 degrees Fahrenheit, or 37.78 degrees Celsius, a temperature drop of an absolute 70 degrees Fahrenheit, or 38.89 degrees Celsius, results in an air temperature in the carburetor of 30 degrees Fahrenheit, or -1 degree Celsius. See Figure 6-12. The first indication of carburetor icing in an aircraft with a fixed pitch propeller is a decrease in engine RPM, which may be followed by engine roughness. In an aircraft with a constant speed propeller, carburetor icing is usually indicated by a decrease in manifold pressure, but no reduction in RPM. Propeller pitch is automatically adjusted to compensate for loss of power. Thus, a constant RPM is maintained. Although carburetor ice can occur during any phase of flight, it is particularly dangerous when using reduced power during a descent. Under certain circumstances, carburetor ice could build unnoticed until power is added. To combat the effect of carburetor ice, engines with float-type carburetors employ a carburetor heat system. Carburetor heat. Carburetor heat is an anti-icing system that preheats the air before it reaches the carburetor and is intended to keep the fuel/air mixture above the freezing temperature to prevent the formation of carburetor ice. Carburetor heat can be used to melt ice that has already formed on the carburetor if the accumulation is not too great, but using the carburetor heat as a preventative measure is a better option. Additionally, the use of carburetor heat as an alternate air source can be used if the intake filter clogs, such as in sudden or unexpected airframe icing conditions. Carburetor heat should be checked during the engine run-up. When using carburetor heat, follow the manufacturer's recommendations. When conditions are conducive to carburetor icing during flight, periodic checks should be made to detect its presence. If detected, full carburetor heat should be applied immediately, and it should be left in the on position until the pilot is certain all the ice has been removed. If ice is present, applying partial heat or leaving heat on for an insufficient time might aggravate the situation. In extreme cases of carburetor icing, even after the ice has been removed, full carburetor heat should be used to prevent further ice formation. If installed, a carburetor temperature gauge is useful in determining when to use carburetor heat. Whenever the throttle is closed during flight, the engine cools rapidly, and vaporization of fuel is less complete than if the engine is warm. Also, in this condition, the engine is more susceptible to carburetor icing. If carburetor icing conditions are suspected and closed throttle operation anticipated, adjust the carburetor heat to the full on position before closing the throttle and leave it on during the closed throttle operation. The heat will aid in vaporizing the fuel and help prevent the formation of carburetor ice. Periodically, open the throttle smoothly for a few seconds to keep the engine warm. Otherwise, the carburetor heater may not provide enough heat to prevent icing. The use of carburetor heat causes a decrease in engine power, sometimes up to 15%, because the heated air is less dense than the outside air that has been entering the engine. This enriches the mixture. When ice is present in an aircraft with a fixed pitch propeller, and the carburetor heat is being used, there is a decrease in RPM, followed by a gradual increase in RPM as the ice melts. The engine also should run more smoothly after the ice has been removed. If ice is not present, the RPM will decrease and then remain constant. When carburetor heat is used on an aircraft with a constant speed propeller and ice is present, a decrease in the manifold pressure will be noticed, followed by a gradual increase. If carburetor icing is not present, the gradual increase in manifold pressure will not be apparent until the carburetor heat is turned off. It is imperative for a pilot to recognize carburetor ice when it forms during flight, because a loss of power, altitude, and/or airspeed will occur. These symptoms may sometimes be accompanied by vibration or engine roughness. Once a power loss is noticed, immediate action should be taken to eliminate ice already formed in the carburetor and to prevent further ice formation. This is accomplished by applying full carburetor heat, which will cause a further reduction in power and possibly engine roughness as melted ice goes through the engine. These symptoms may last from 30 seconds to several minutes, depending on the severity of the icing. During this period, the pilot must resist the temptation to decrease carburetor heat usage. Carburetor heat must remain in the full hot position until normal power returns. Since the use of carburetor heat tends to reduce the output of the engine and to increase the operating temperature, carburetor heat should not be used when full power is required, as during takeoff or during normal engine operation, except to check for the presence or to remove carburetor ice. Carburetor air temperature gauge. Some aircraft are equipped with a carburetor air temperature gauge, which is useful in detecting potential icing conditions. Usually, the face of the gauge is calibrated to degrees Celsius, with the yellow arc indicating the carburetor air temperatures where icing may occur. This yellow arc typically ranges between negative 15 degrees Celsius and positive 5 degrees Celsius, or 5 degrees Fahrenheit and 41 degrees Fahrenheit. If the air temperature and moisture content of the air are such that carburetor icing is improbable, the engine can be operated with the indicator in the yellow range with no adverse effects. If the atmospheric conditions are conducive to carburetor icing, the indicator must be kept outside the yellow arc by application of carburetor heat. Certain carburetor air temperature gauges have a red radial, which indicates the maximum permissible carburetor inlet air temperature recommended by the engine manufacturer. If present, a green arc indicates the normal operating range. Outside air temperature gauge. Most aircraft are equipped with an outside air temperature (OAT) gauge calibrated in both degrees Celsius and Fahrenheit. It provides the outside or ambient air temperature for calculating true airspeed. It is also useful in detecting potential icing conditions. Fuel injection systems. In a fuel injection system, the fuel is injected directly into the cylinders, or just ahead of the intake valve. The air intake for the fuel injection system is similar to that used in a carburetor system, with an alternate air source located within the engine cowling. This source is used if the external air source is obstructed. The alternate air source is usually operated automatically, with a backup manual system that can be used if the automatic feature malfunctions. A fuel injection system usually incorporates 6 basic components: an engine-driven fuel pump, a fuel/air control unit, fuel manifold or fuel distributor, discharge nozzles, an auxiliary fuel pump, and fuel pressure/flow indicators. See Figure 6-13. An auxiliary fuel pump provides fuel under pressure to the fuel/air control unit for engine starting and/or emergency use. After starting, the engine-driven fuel pump provides fuel under pressure from the fuel tank to the fuel/air control unit. This control unit, which essentially replaces the carburetor, meters fuel based on the mixture control setting and sends it to the fuel manifold valve at a rate controlled by the throttle. After reaching the fuel manifold valve, the fuel is distributed to the individual fuel discharge nozzles. The discharge nozzles, which are located in each cylinder head, inject the fuel/air mixture directly into each cylinder intake port. A fuel injection system is considered to be less susceptible to icing than the carburetor system, but impact icing on the air intake is a possibility in either system. Impact icing occurs when the ice forms on the exterior of the aircraft and blocks openings such as the air intake for the injection system. Advantages of fuel injection: reduction in evaporative icing, better fuel flow, faster throttle response, precise control of mixture, better fuel distribution, easier cold weather starts. Disadvantages: difficulty in starting a hot engine, vapor locks during ground operations on hot days, problems associated with restarting an engine that quits because of fuel starvation. End of Part 2 of Chapter 6. Part 3 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 3 of Chapter 6. Superchargers and Turbosuperchargers. To increase an engine's horsepower, manufacturers have developed forced induction systems called supercharger and turbosupercharger systems. They both compress the intake air to increase its density. The key difference lies in the power supply. A supercharger relies on an engine-driven air pump or compressor, while a turbosupercharger gets its power from the exhaust stream that runs through a turbine, which in turn spins the compressor. Aircraft with these systems have a manifold pressure gauge, which displays MAP within the engine's intake manifold. On a standard day at sea level with the engine shut down, the manifold pressure gauge will indicate the ambient absolute air pressure of 29.92 inches mercury. Because atmospheric pressure decreases approximately 1 inch mercury per 1,000 feet of altitude increase, the manifold pressure gauge will indicate approximately 24.92 inches mercury at an airport that is 5,000 feet above sea level with standard day conditions. As a normally aspirated aircraft climbs, it eventually reaches an altitude where the MAP is insufficient for a normal climb. That altitude limit is the aircraft's service ceiling, and it is directly affected by the engine's ability to produce power. If the induction air entering the engine is pressurized or boosted by either a supercharger or a turbosupercharger, the aircraft's service ceiling can be increased. With these systems, an aircraft can fly at altitudes with the advantage of higher true airspeeds and the increased ability to circumnavigate adverse weather. Superchargers. A supercharger is an engine-driven air pump or compressor that provides compressed air to the engine to provide additional pressure to the induction air so the engine can produce additional power. It increases manifold pressure and forces the fuel/air mixture into the cylinders. The higher the manifold pressure, the more dense the fuel/air mixture and the more power an engine can produce. With a normally aspirated engine, it is not possible to have the manifold pressure higher than the existing atmospheric pressure. A supercharger is capable of boosting manifold pressure above 30 inches mercury. For example, at 8,000 feet, a typical engine may be able to produce 75% of the power it could produce at a mean sea level, MSL, because the air is less dense at the higher altitude. The supercharger compresses the air to a higher density, allowing a supercharged engine to produce the same manifold pressure at higher altitudes as it could at sea level. Thus, an engine at 8,000 feet MSL could still produce 25 inches mercury of manifold pressure, whereas without a supercharger, it could produce only 22 inches mercury. Superchargers are especially valuable at high altitudes, such as 18,000 feet, where the air density is 50% that of sea level. The use of a supercharger in many cases will supply air to the engine at the same density as it did at sea level. With a normally aspirated engine, it is not possible to have manifold pressure higher than the existing atmospheric pressure. A supercharger is capable of boosting manifold pressure above 30 inches mercury. The components of a supercharged induction system are similar to those of a normally aspirated system, with the addition of a supercharger between the fuel metering device and intake manifold. A supercharger is driven by the engine through a gear train at 1 speed, 2 speed, or variable speeds. In addition, superchargers can have one or more stages. Each stage also provides an increase in pressure, and superchargers may be classified as single-stage, two-stage, or multi-stage, depending on the number of times compression occurs. An early version of a single-stage, single-speed supercharger may be referred to as a sea-level supercharger. An engine equipped with this type of supercharger is called a sea-level engine. With this type of supercharger, a single gear-driven impeller is used to increase the power produced by an engine at all altitudes. The drawback of this type of supercharger is a decrease in engine power output with an increase in altitude. Single-stage, single-speed superchargers are found on many high-powered radial engines and use an air intake that faces forward so the induction system can take full advantage of the ram air. Intake air passes through ducts to the carburetor, where fuel is metered in proportion to the airflow. The fuel/air change is then ducted to the supercharger, or blower impeller, which accelerates the fuel/air mixture outward. Once accelerated, the fuel/air mixture passes through a diffuser, where air velocity is traded for pressure energy. After compression, The resulting high-pressure fuel/air mixture is directed to the cylinders. Some of the large radial engines developed during World War II have a single-stage, 2-speed supercharger. With this type of supercharger, a single impeller may be operated at 2 speeds. The low impeller speed is often referred to as the low blower setting, while the high impeller speed is called the high blower setting. On engines equipped with a 2-speed supercharger, a lever or switch in the flight deck activates an oil-operated clutch that switches from one speed to the other. Under normal operations, takeoff is made with the supercharger in the low blower position. In this mode, the engine performs as a ground-boosted engine, and the power output decreases as the aircraft gains altitude. However, once the aircraft reaches a specified altitude, a power reduction is made and the supercharger control is switched to the high blower position. The throttle is then reset to the desired manifold pressure. An engine equipped with this type of supercharger is called an altitude engine. See Figure 6-14. Turbosuperchargers. The most efficient method of increasing horsepower in an engine is by use of a turbosupercharger or turbocharger. Installed on an engine, this booster uses the engine's exhaust gases to drive an air compressor to increase the pressure of the air going into the engine through the carburetor or fuel injection system to boost power at higher altitude. The major disadvantage of a gear-driven supercharger, use of a large amount of the engine's power output for the amount of power increase produced, is avoided with a turbocharger because turbochargers are powered by the engine's exhaust gases. This means a turbocharger recovers energy from hot exhaust gases that would otherwise be lost. A second advantage of turbochargers over superchargers is the ability to maintain control over an engine's rated sea level horsepower from sea level up to the engine's critical altitude. Critical altitude is the maximum altitude at which a turbocharged engine can produce its rated horsepower. Above the critical altitude, power output begins to decrease like it does for a normally aspirated engine. Turbochargers increase the pressure of the engine's induction air, which allows the engine to develop sea level or greater horsepower at higher altitudes. A turbocharger is comprised of 2 main elements, a compressor and turbine. The compressor section houses an impeller that turns at a high rate of speed. As induction air is drawn across the impeller blades, the impeller accelerates the air, allowing a large volume of air to be drawn into the compressor housing. The impeller's action subsequently produces high-pressure, high-density air, which is delivered to the engine. To turn the impeller, the engine's exhaust gases are used to drive a turbine wheel that is mounted on the opposite end of the impeller's drive shaft. By directing different amounts of exhaust gases to flow over the turbine, more energy can be extracted, causing the impeller to deliver more compressed air to the engine. The wastegate, essentially an adjustable butterfly valve installed in the exhaust system, is used to vary the mass of exhaust gas flowing into the turbine. When closed, most of the exhaust gases from the engine are forced to flow through the turbine. When open, the exhaust gases are allowed to bypass the turbine by flowing directly through the engine's exhaust pipe. See Figure 6-15. Since the temperature of a gas rises when it is compressed, turbocharging causes the temperature of the induction air to increase. To reduce this temperature and to lower the risk of detonation, many turbocharged engines use an intercooler. This small heat exchanger uses outside air to cool the hot compressed air before it enters the fuel metering device. System operation. On most modern turbocharged engines, the position of the wastegate is governed by a pressure-sensing control mechanism coupled to an actuator. Engine oil directed into or away from this actuator moves the wastegate position. On these systems, the actuator is automatically positioned to produce the desired MAP simply by changing the position of the throttle control. Other turbocharging system designs use a separate manual control to position the wastegate. With manual control, the manifold pressure gauge must be closely monitored to determine when the desired MAP has been achieved. Manual systems are often found on aircraft that have been modified with aftermarket turbocharging systems. These systems require special operating considerations. For example, if the wastegate is left closed after descending from a high altitude, it is possible to produce a manifold pressure that exceeds the engine's limitations. This condition, called an overboost, may produce severe detonation because of the leaning effect resulting from increased air density during descent. Although an automatic wastegate system is less likely to experience an overboost condition, it can still occur. If takeoff power is applied while the engine oil temperature is below its normal operating range, the cold oil may not flow out of the wastegate actuator quickly enough to prevent an overboost. To prevent overboosting, Advance the throttle cautiously to prevent exceeding the maximum manifold pressure limits. A pilot flying an aircraft with a turbocharger should be aware of system limitations. For example, a turbocharger turbine and impeller can operate at rotational speeds in excess of 80,000 RPM while at extremely high temperatures. To achieve high rotational speed, the bearings within the system must be constantly supplied with engine oil to reduce the frictional forces and high temperature. To obtain adequate lubrication, the oil temperature should be applied in the normal operating range before high throttle settings are applied. In addition, allow the turbocharger to cool and the turbine to slow down before shutting the engine down. Otherwise, the remaining oil in the bearing housing will boil, causing high carbon deposits to form on the bearings and shaft. These deposits rapidly deteriorate the turbocharger's efficiency and service life. For further limitations, refer to the AFM/POH. High altitude performance. As an aircraft equipped with a turbocharging system climbs, the wastegate is gradually closed to maintain the maximum allowable manifold pressure. At some point, the wastegate will be fully closed, and further increases in altitude will cause the manifold pressure to decrease. This is the critical altitude, which is established by the aircraft or engine manufacturer. When evaluating the performance of a turbocharging system, be aware if the manifold pressure begins decreasing before the specified critical altitude. The engine and turbocharging system should be inspected by a qualified aviation maintenance technician to verify the system's proper operation. Ignition system. In a spark ignition engine, the ignition system provides a spark that ignites the fuel/air mixture in the cylinders and is made up of magnetos, spark plugs, high-tension leads, and the ignition switch. See Figure 6-16. A magneto uses a permanent magnet to generate an electrical current completely independent of the aircraft's electrical system. The magneto generates sufficiently high voltage to jump a spark across the spark plug gap in each cylinder. The system begins to fire when the starter engine is engaged and the crankshaft begins to turn. It continues to operate whenever the crankshaft is rotating. Most standard certified aircraft incorporate a dual ignition system with two individual magnetos, separate sets of wires, and spark plugs to increase reliability of the ignition system. Each magneto operates independently to fire one of the two spark plugs in each cylinder. The firing of two spark plugs improves combustion of the fuel/air mixture and results in a slightly higher power output. If one of the magnetos fails, the other is unaffected. The engine will continue to operate normally, although a slight decrease in engine power can be expected. The same is true if one of the two spark plugs in a cylinder fails. The operation of the magneto is controlled in the flight deck by the ignition switch. The switch has 5 positions. 1. Off. 2. R, or right. 3. L, or left. 4. Both. And 5. Start. With right or left selected, only the associated magneto is activated. The system operates on both magnetos with both selected. A manufacturing ignition system can be identified during the pre-takeoff check by observing the decrease in RPM that occurs when the ignition switch is first moved from both to right and then from both to left. A small decrease in engine RPM is normal during this check. The permissible decrease is listed in the AFM or POH. If the engine stops running when switched to one magneto, or if the RPM drop exceeds the allowable limit, do not fly the aircraft until the problem is corrected. The cause could be fouled plugs, broken or shorted wires between the magneto and the plugs, or improperly timed firing of the plugs. It should be noted that no drop in RPM is not normal, and in that instance, the aircraft should not be flown. Following engine shutdown, turn the ignition switch to the off position. Even with the battery and master switches off, the engine can fire and turn over if the ignition switch is left on and the propeller is moved because the magneto requires no outside source of electrical power. Be aware of the potential for serious injury in this situation. Even with the ignition switch in the off position, if the ground wire between the magneto and the ignition switch becomes disconnected or broken, the engine could accidentally start if the propeller is moved with residual fuel in the cylinder. If this occurs, the only way to stop the engine is to move the mixture lever to the idle cutoff position, then have the system checked by a qualified aviation maintenance technician. Oil systems. The engine oil system performs several important functions: lubrication of the engine's moving parts, cooling of the engine by reducing friction, removing heat from the cylinders, providing a seal between the cylinder walls and pistons, carrying away contaminants. Reciprocating engines use either a wet sump or a dry sump oil system. In a wet sump system, the oil is located in a sump, which is an integral part of the engine. In a dry sump system, the oil is contained in a separate tank and circulated through the engine by pumps. See Figure 6-17. The main component of a wet sump system is the oil pump, which draws oil from the sump and routes it to the engine. After the oil passes through the engine, it returns to the sump. In some engines, additional lubrication is supplied by the rotating crankshaft, which splashes oil onto portions of the engine. An oil pump also supplies oil pressure in a dry sump system, but the source of the oil is located external to the engine in a separate oil tank. After oil is routed through the engine, it is pumped from the various locations in the engine back to the oil tank by scavenge pumps. Dry sump systems allow for a greater volume of oil to be supplied to the engine, which makes them more suitable for very large reciprocating engines. The oil pressure gauge provides a direct indication of the oil system operation. It ensures that the pressure in pounds per square inch, or psi, of the oil is supplied to the engine. Green indicates the normal operating range, while red indicates the minimum and maximum pressures. There should be an indication of the oil pressure during engine start. Refer to the AFM/POH for manufacturer limitations. The oil temperature gauge measures the temperature of oil. A green area shows the normal operating range, and the red line indicates the maximum allowable temperature. Unlike oil pressure, changes in oil temperature occur more slowly. This is particularly noticeable after starting a cold engine, when it may take several minutes or longer for the gauge to show any increase in oil temperature. Check oil temperature periodically during flight, especially when operating in a high or low ambient air temperature. High oil temperature indications may signal a plugged oil line, a low oil quantity, a blocked oil cooler, or a defective temperature gauge. Low oil temperature indications may signal improper oil viscosity during cold weather operations. The oil filter cap and dipstick, for measuring the oil quantity, are usually accessible through a panel in the engine cowling. If the quantity does not meet the manufacturer's recommended operating levels, oil should be added. The AFM/POH or placards near the access panel provide information about the correct oil type and weight, as well as the minimum and maximum oil quantity. See Figure 6-18. End of Part 3 of Chapter 6. Part 4 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 6. Part 4. Engine Cooling Systems. The burning fuel within the cylinders produces intense heat, most of which is expelled through the exhaust system. Much of the remaining heat, however, must be removed, or at least dissipated, to prevent the engine from overheating. Otherwise, the extremely high engine temperatures can lead to loss of power, excessive oil consumption, detonation, and serious engine damage. While the oil system is vital to the internal cooling of the engine, an additional method of cooling is necessary for the engine's external surface. Most small aircraft are air-cooled, although some are liquid-cooled. Air cooling is accomplished by air flowing into the engine compartment through openings in the front of the engine cowling. Baffles route this air over fins attached to the engine cylinders and other parts of the engine, where the air absorbs the engine heat. Expulsion of the hot air takes place through one or more openings in the lower, aft portion of the engine cowling. See Figure 6-19. The outside air enters the engine compartment through an inlet behind the propeller hub. Baffles direct it to the hottest parts of the engine, primarily the cylinders, which have fins that increase the area exposed to the airflow. The air cooling system is less effective during ground operations, takeoffs, go-arounds, and other periods of high-power, low airspeed operation. Conversely, high-speed descents provide excess air and can shock cool the engine, subjecting it to abrupt temperature fluctuations. Operating the engine at higher than its design temperature can cause loss of power, excessive oil consumption, and detonation. It will also lead to serious permanent damage, such as scoring the cylinder walls, damaging the pistons and rings, and burning and warping the valves. Monitoring the flight deck engine temperature instruments will aid in avoiding high operating temperature. Under normal operating conditions in aircraft not equipped with cowl flaps, the engine temperature can be controlled by changing the airspeed or the power output of the engine. High engine temperatures can be decreased by increasing the airspeed and/or reducing the power. The oil temperature gauge gives an indirect and delayed indication of rising engine temperature, but can be used for determining engine temperature if this is the only means available. Most aircraft are equipped with a cylinder head temperature gauge, which indicates a direct and immediate cylinder temperature change. This instrument is calibrated in degrees Celsius or Fahrenheit and is usually color-coded with a green arc to indicate the normal operating range. A red line on the instrument indicates maximum allowable cylinder head temperature. To avoid excessive cylinder head temperatures, increase airspeed, enrich the mixture, and/or reduce power. Any of these procedures help to reduce the engine temperature. On aircraft equipped with cowl flaps, use the cowl flap positions to control the temperature. Cowl flaps are hinged covers that fit over the opening through which the hot air is expelled. If engine temperature is low, the cowl flaps can be closed, thereby restricting the flow of expelled hot air and increasing engine temperature. If the engine temperature is high, the cowl flaps can be opened to permit a greater flow of air through the system, thereby decreasing the engine temperature. Exhaust systems. Engine exhaust systems vent the burned combustion gases overboard, provide heat for the cabin, defrost the windscreen. An exhaust system has exhaust piping attached to the cylinders, as well as a muffler and a muffler shroud. The exhaust gases are pushed out of the cylinder through the exhaust valve, and then through the exhaust pipe system to the atmosphere. For cabin heat, outside air is drawn into the air inlet and is ducted through a shroud around the muffler. The muffler is heated by the exiting exhaust gases and, in turn, heats the air around the muffler. This heated air is then ducted to the cabin for heat and defrost applications. The heat and defrost are controlled in the flight deck and can be adjusted to the desired level. Exhaust gases contain large amounts of carbon monoxide, which is odorless and colorless. Carbon monoxide is deadly, and its presence is virtually impossible to detect. The exhaust system must be in good condition and free of cracks. Some exhaust systems have an EGT probe. This probe transmits the EGT to an instrument in the flight deck. The EGT gauge measures the temperature of the gases at the exhaust manifold. This temperature varies with the ratio of fuel to air entering the cylinders, and can be used as a basis for regulating the fuel/air mixture. The EGT gauge is highly accurate in indicating the correct mixture setting. When using the EGT to aid in leaning the fuel/air mixture, fuel consumption can be reduced. For specific procedures, refer to the manufacturer's recommendations for leaning the mixture. Starting system. Most small aircraft use a direct cranking electric starter system. This system consists of a source of electricity, wiring, switches, and solenoids to operate the starter and a starter motor. Most aircraft have starters that automatically engage and disengage when operated, but some older aircraft have starters that are mechanically engaged by a lever actuated by the pilot. The starter engages the aircraft flywheel, rotating the engine at a speed that allows the engine to start and maintain operation. Electrical power for starting is usually supplied by an onboard battery, but can also be supplied by an external power through an external power receptacle. When the battery switch is turned on, electricity is supplied to the main power bus bar through the battery solenoid. Both the starter and the starter switch draw current from the main bus bar, but the starter will not operate until the starting solenoid is energized by the starter switch being turned to the start position. When the starter switch is released from the start position, the solenoid removes power from the starting motor. The starter motor is protected from being driven by the engine through a clutch in the starter drive that allows the engine to run faster than the starter motor. See Figure 6-20 and errata. When starting an engine, the rules of safety and courtesy should be strictly observed. One of the most important is to make sure that there is no one near the propeller. In addition, the wheels should be chalked and the brakes set to avoid hazards caused by unintentional movement. To avoid damage to the propeller and property, the aircraft should be in an area where the propeller will not stir up gravel or dust. Combustion. During normal combustion, the fuel/air mixture burns in a very controlled and predictable manner. In a spark ignition engine, the process occurs in a fraction of a second. The mixture actually begins to burn at the point where it is ignited by the spark plugs, then burns away from the plugs until it is all consumed. This type of combustion causes a smooth buildup of temperature and pressure, and ensures that the expanding gases deliver the maximum force to the piston at exactly the right time in the power stroke. See Figure 6-21. Detonation is an uncontrolled explosive ignition of the fuel/air mixture within the cylinder's combustion chamber. It causes excessive temperatures and pressures which, if not corrected, can quickly lead to the failure of the piston, cylinder, or valves. In less severe cases, detonation causes engine overheating, roughness, or loss of power. Detonation is characterized by high cylinder head temperatures and is most likely to occur when operating at high power settings. Common operational causes of detonation are use of a lower fuel grade than that specified by the aircraft manufacturer, operation of the engine with extremely high manifold pressures in conjunction with low RPM, operation of the engine at high power settings with an excessively lean mixture, maintaining extended ground operations or steep climbs in which cylinder cooling is reduced. Detonation may be avoided by following these basic guidelines during the various phases of ground and flight operations. Make sure the proper grade of fuel is used. Keep the cowl flaps, if available, in the full open position while on the ground to provide the maximum airflow through the cowling. Use an enriched fuel mixture as well as a Schauler climb angle to increase cylinder cooling during takeoff and initial climb. Avoid extended high-power steep climbs. Develop the habit of monitoring the engine's instruments to verify proper operation according to the procedures established by the manufacturer. Pre-ignition occurs when the fuel/air mixture ignites prior to the engine's normal ignition event. Premature burning is usually caused by a residual hot spot in the combustion chamber, often created by a small carbon deposit on a spark plug, a cracked spark plug insulator, or other damage in the cylinder that causes a part to heat sufficiently to ignite the fuel/air charge. Pre-ignition causes the engine to lose power and produces high operating temperature. As with detonation, pre-ignition may also cause severe engine damage because the expanding gases exert excessive pressure on the piston while it is in the compression stroke. Detonation and pre-ignition often occur simultaneously, and one may cause the other. Since either condition causes high engine temperature accompanied by a decrease in engine performance, it is often difficult to distinguish between the two. Using the recommended grade of fuel and operating the engine within its proper temperature, pressure, and RPM ranges reduce the chance of detonation or pre-ignition. Full Authority Digital Engine Control, or FADEC. FADEC is a system consisting of a digital computer and ancillary components that control the aircraft's engine and propeller. First used in turbine-powered aircraft and referred to as Full Authority Digital Electronic Control, these sophisticated control systems are increasingly being used in piston-powered aircraft. In a spark ignition reciprocating engine, the FADEC uses speed, temperature, and pressure sensors to monitor the status of each cylinder. A digital computer calculates the ideal pulse for each injector and adjusts ignition timing as necessary to achieve optimal performance. In a compression ignition engine, the FADEC operates similarly and performs all the same functions, excluding those specifically related to the spark ignition process. The FADEC systems eliminate the need for magnetos, carburetor heat, mixture controls, and engine priming. A single throttle lever is characteristic of an aircraft equipped with an FADEC system. The pilot simply positions the throttle lever to a desired detent, such as start, idle, cruise power, or max power, and the FADEC system adjusts the engine and propeller automatically for the mode selected. There is no need for the pilot to monitor or control the fuel/air mixture. During aircraft starting, the FADEC primes the cylinders, adjusts the mixture, and positions the throttle based on engine temperature and ambient pressure. During cruise flight, the FADEC constantly monitors the engine and adjusts fuel flow and ignition timing individually in each cylinder. This precise control of the combustion process often results in decreased fuel consumption and increased horsepower. FADEC systems are considered an essential part of the engine and propeller control and may be powered by the aircraft's main electrical system. In many aircraft, FADEC uses power from a separate generator connected to the engine. In either case, there must be a backup electrical source available because failure of an FADEC system could result in a complete loss of engine thrust. To prevent loss of thrust, two separate and identical digital channels are incorporated for redundancy, each channel capable of providing all engine and propeller functions without limitations. End of Part 4 of Chapter 6. Part 5 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 6, Part 5. Turbine Engines. An aircraft turbine engine consists of an air inlet, compressor, combustion chambers, a turbine section, and exhaust. Thrust is produced by increasing the velocity of air flowing through the engine. Turbine engines are highly desirable aircraft power plants. They are characterized by smooth operation and a high power-to-weight ratio, and they use readily available jet fuel. Prior to recent advances in material, engine design, and manufacturing process, the use of turbine engines in small/light production aircraft was cost prohibitive. Today, several aviation manufacturers are producing or plan to produce small/light turbine-powered aircraft. These smaller turbine-powered aircraft typically seat between 3 and 7 passengers and are referred to as very light jets, VLJs, or microjets. See Figure 6-22. Types of turbine engines. Turbine engines are classified according to the type of compressors they use. There are 3 types of compressors: centrifugal flow, axial flow, and centrifugal axial flow. Compression of inlet air is achieved in a centrifugal flow engine by accelerating air outward perpendicular to the longitudinal axis of the machine. The axial flow engine compresses air by a series of rotating and stationary airfoils, moving the air parallel to the longitudinal axis. The centrifugal axial flow design uses both kinds of compressors to achieve the desired compression. The path the air takes through the engine and how power is produced determines the type of engine. There are 4 types of aircraft turbine engines: turbojet, turboprop, turbofan, and turboshaft. Turbojet. The turbojet engine consists of 4 sections: compressor, combustion chamber, turbine section, and exhaust. The compressor section passes inlet air at a high rate of speed to the combustion chamber. The combustion chamber contains the fuel inlet and igniter for combustion. The expanding air drives a turbine, which is connected by a shaft to the compressor, sustaining engine operation. The accelerated exhaust gases from the engine provide thrust. This is a basic application of compressing air, igniting the fuel-air mixture, producing power to self-sustain the engine operation, and exhaust for propulsion. See Figure 6-23. Turbojet engines are limited in range and endurance. They are also slow to respond to throttle applications at slow compressor speeds. Turboprop. A turboprop engine is a turbine engine that drives a propeller through a reduction gear. The exhaust gases drive a power turbine connected by a shaft that drives the reduction gear assembly. Reduction gearing is necessary in turboprop engines because optimum propeller performance is achieved at much slower speeds than the engine's operating RPM. Turboprop engines are a compromise between turbojet engines and reciprocating power plants. Turboprop engines are most efficient at speeds between 250 and 400 miles per hour and altitudes between 18,000 and 30,000 feet. They also perform well at slow airspeeds required for takeoff and landing and are fuel efficient. The minimum specific fuel consumption of a turboprop engine is normally available at the altitude range of 25,000 feet to the tropopause. See Figure 6-24. Turbofan. Turbofans were developed to combine some of the best features of the turbojet and the turboprop. Turbofan engines are designed to create additional thrust by diverting a secondary airflow around the combustion chamber. The turbofan bypass air generates increased thrust, cools the engine, and aids in exhaust noise suppression. This provides turbojet-type cruise speed and lower fuel consumption. The inlet air that passes through a turbofan engine is usually divided into 2 separate streams of air. One stream passes through the engine core, while a second stream bypasses the engine core. It is this bypass stream of air that is responsible for the term bypass engine. A turbofan's bypass ratio refers to the ratio of mass airflow that passes through the fan divided by the mass airflow that passes through the engine core. See Figure 6-25. Turboshaft. The fourth common type of jet engine is the turboshaft. See Figure 6-26. It delivers power to a shaft that drives something other than a propeller. The biggest difference between a turbojet and turboshaft engine is that on a turboshaft engine, most of the energy produced by the expanding gases is used to drive a turbine rather than produce thrust. Many helicopters use a turboshaft gas turbine engine. In addition, turboshaft engines are widely used as auxiliary power units on large aircraft. Turbine engine instruments. Engine instruments that indicate oil pressure, oil temperature, engine speed, exhaust gas temperature, and fuel flow are common to both turbine and reciprocating engines. However, there are some instruments that are unique to turbine engines. These instruments produce indications of the engine pressure ratio, turbine discharge pressure, and torque. In addition, most gas turbine engines have multiple temperature sensing instruments called thermocouples, which provide pilots with temperature readings in and around the turbine section. Engine pressure ratio, EPR. An engine pressure ratio, EPR, gauge is used to indicate the power output of the turbojet/turbofan engine. EPR is the rate of turbine discharge to compressor inlet pressure. Pressure measurements are recorded by probes installed in the engine inlet and at the exhaust. Once collected, the data is sent to a differential pressure transducer, which is then indicated on a flight deck EPR gauge. EPR system design automatically compensates for the effects of airspeed and altitude. Changes in ambient temperature require a correction be applied to EPR indications to provide accurate engine power settings. Exhaust gas temperature, EGT. A limiting factor in a gas turbine engine is the temperature of the turbine section. The temperature of a turbine section must be monitored closely to prevent overheating the turbine blades and other exhaust section components. One common way of monitoring the temperature of a turbine section is with an EGT gauge. EGT is an engine operating limit used to monitor overall engine operating conditions. Variations of EGT systems bear different names based on the location of the temperature sensors. Common turbine temperature sensing gauges include the turbine inlet temperature, TIT gauge, turbine outlet temperature, TOT gauge, interstage turbine temperature, ITT gauge, and turbine gas temperature, TGT gauge. Torque meter. Turboprop/turboshaft engine power output is measured by the torque meter. Torque is a twisting force applied to a shaft. The torque meter measures power applied to the shaft. Turboprop and turboshaft engines are designed to produce torque for driving a propeller. Torque meters are calibrated in percentage units, foot-pounds, or PSI. N1 indicator. N1 represents the rotational speed of the low-pressure compressor and is presented on the indicator as a percentage of design RPM. After start, the speed of the low-pressure compressor is governed by the N1 turbine wheel. The N1 turbine wheel is connected to the low-pressure compressor through a concentric shaft. N2 indicator. N2 represents the rotational speed of the high-pressure compressor and is presented on the indicator as a percentage of design RPM. The high-pressure compressor is governed by the N2 turbine wheel. The N2 turbine wheel is connected to the high-pressure compressor through a concentric shaft. See Figure 6-17. Turbine engine operational considerations. The great variety of turbine engines makes it impractical to cover specific operational procedures, but there are certain operational considerations common to all turbine engines. They are engine temperature limits, foreign object damage, hot start, compressor stall, and flame out. Engine temperature limitations. The highest temperature in any turbine engine occurs at the turbine inlet. Turbine inlet temperature is therefore usually the limiting factor in turbine engine operation. Thrust variations. Turbine engine thrust varies directly with air density. As air density decreases, so does thrust. Additionally, because air density decreases with an increase in temperature, increased temperatures will also result in decreased thrust. While both turbine and reciprocating powered engines are affected to some degree by high relative humidity, turbine engines will experience a negligible loss of thrust, while reciprocating engines a significant loss of brake horsepower. Foreign object damage, FOD. Due to the design and function of a turbine engine's air inlet, the possibility of ingestion of debris always exists. This causes significant damage, particularly to the compressor and turbine sections. When ingestion of debris occurs, it is called foreign object damage, FOD. Typical FOD consists of small nicks and dents caused by the ingestion of small objects from the ramp, taxiway, or runway, but FOD damage caused by bird strikes or ice ingestion also occur. Sometimes FOD results in total destruction of an engine. Prevention of FOD is a high priority. Some engine inlets have a tendency to form a vortex between the ground and inlet during ground operations. A vortex dissipator may be installed on these engines. Other devices, such as screens and/or deflectors, may also be utilized. Pre-flight procedures include a visual inspection of any sign of FOD. Turbine engine hot/hung start. When the EGT exceeds the safe limit of an aircraft, it experiences a hot start. It is caused by too much fuel entering the combustion chamber or insufficient turbine RPM. Anytime an engine has a hot start, refer to the AFM/POH or an appropriate maintenance manual for inspection requirements. If the engine fails to accelerate to the proper speed after ignition or does not accelerate to idle RPM, a hung or false start has occurred. A hung start may be caused by an insufficient starting power source or fuel control malfunction. Compressor stalls. Compressor blades are small airfoils and are subject to the same aerodynamic principles that apply to any airfoil. A compressor blade has an angle of attack which is a result of the inlet air velocity and the compressor's rotational velocity. These two forces combine to form a vector, which defines the airfoil's actual angle of attack to the approaching inlet air. A compressor stall is an imbalance between the two vector quantities, inlet velocity and compressor rotational speed. Compressor stalls occur when the compressor blade's angle of attack exceeds the critical angle of attack. At this point, smooth airflow is interrupted and turbulence is created with pressure fluctuations. Compressor stalls cause air flowing in the compressor to slow down and stagnate, sometimes reversing direction. See Figure 6-28. Compressor stalls can be transient and intermittent or steady and severe. Indications of a transient/intermittent stall are usually an intermittent bang as backfire and flow reversal take place. If the stall develops and becomes steady, strong vibration and a loud roar may develop from the continuous flow reversal. Often, the flight deck gauges do not show a mild or transient stall, but they do indicate a developed stall. Typical instrument indications include fluctuations in RPM and an increase in exhaust gas temperature. Most transient stalls are not harmful to the engine and often correct themselves after 1 or 2 pulsations. The possibility of severe engine damage from a steady-state stall is immediate. Recovery must be accomplished by quickly reducing power, decreasing the aircraft's angle of attack, and increasing airspeed. Although all gas turbine engines are subject to compressor stalls, most models have systems that inhibit them. One system uses a variable inlet guide vane, VIGV, and variable stator vanes, which direct the incoming air into the rotor blades at an appropriate angle. To prevent air pressure stalls, operate the aircraft within the parameters established by the manufacturer. If a compressor stall does develop, follow the procedures recommended in the AFM/POH. Flameout. A flameout occurs in the operation of a gas turbine engine in which the fire in the engine unintentionally goes out. If the rich limit of the fuel/air ratio is exceeded in the combustion chamber, the flame will blow out. This condition is often referred to as a rich flameout. It generally results from very fast engine acceleration, in which an overly rich mixture causes the fuel temperature to drop below the combustion temperature. It may also be caused by insufficient airflow to support combustion. A more common flameout occurrence is due to low fuel pressure and low engine speeds, which typically are associated with high altitude flight. This situation may also occur with the engine throttled back during a descent, which can set up the lean condition flameout. A weak mixture can easily cause the flame to die out, even with a normal airflow through the engine. Any interruption of the fuel supply can result in a flameout. This may be due to prolonged unusual attitudes, a malfunctioning fuel control system, turbulence, icing, or running out of fuel. Symptoms of a flameout normally are the same as those following an engine failure. If the flameout is due to a transitory condition, such as an imbalance between fuel flow and engine speed, an air start may be attempted once the condition is corrected. In any case, pilots must follow the applicable emergency procedures outlined in the AFM/BOH. Generally, these procedures contain recommendations concerning altitude and airspeed where the air start is most likely to be successful. Performance comparison. It is possible to compare the performance of a reciprocating power plant and different types of turbine engines. For the comparison to be accurate, thrust horsepower, usable horsepower, for the reciprocating power plant must be used rather than the brake horsepower, and net thrust must be used for the turbine-powered engines. In addition, aircraft design configuration and size must be approximately the same. When comparing performance, the following definitions are useful. Brake horsepower, bhp. The horsepower actually delivered to the output shaft. Brake horsepower is the actual usable horsepower. Net thrust. The thrust produced by a turbojet or turbofan engine. Thrust horsepower, THP. The horsepower equivalent of the thrust produced by a turbojet or turbofan engine. Equivalent shaft horsepower, ESHP. With respect to turboprop engines, the sum of the shaft horsepower, SHP, delivered to the propeller, and THP produced by the exhaust gases. Figure 6-29 shows how 4 types of engines compare in net thrust as airspeed is increased. This figure is for explanatory purposes only, and is not for specific models of engines. The following are the 4 types of engines: reciprocating power plant, turbine, propeller combination, turboprop, turbine engine incorporating a fan, turbofan, and turbojet, pure jet. By plotting the performance curve for each engine, a comparison can be made of maximum aircraft speed variation with the type of engine used. Since the graph is only a means of comparison, numerical values for net thrust, aircraft speed, and drag are not included. Comparison of the 4 power plants on the basis of net thrust makes certain performance capabilities evident. In the speed range shown to the left of line A, the reciprocating power plant outperforms the other 3 types. The turboprop outperforms the turbofan in the range to the left of line C. The turbofan engine outperforms the turbojet in the range of the left of line F. The turbofan engine outperforms the reciprocating power plant to the right of line B and the turboprop to the right of line C. The turbojet outperforms the reciprocating power plant to the right of line D, the turboprop to the right of line E, and the turbofan to the right of line F. The points where the aircraft drag curve intersects the net thrust curves are the maximum aircraft speeds. The vertical lines from each of the points to the baseline of the graph indicate that the turbojet aircraft can attain a higher maximum speed than aircraft equipped with the other types of engines. Aircraft equipped with the turbofan engine will attain a higher maximum speed than aircraft equipped with a turboprop or reciprocating power plant. End of Part 5 of Chapter 6. Part 6 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 6, Part 6. Airframe Systems. Fuel, electrical, hydraulic, and oxygen systems make up the airframe systems. Fuel systems. The fuel system is designed to provide an uninterrupted flow of clean fuel from the fuel tanks to the engine. The fuel must be available to the engine under all conditions of engine power, altitude, attitude, and during all approved flight maneuvers. 2 common classifications apply to fuel systems in small aircraft: gravity feed and fuel pump systems. Gravity feed system. The gravity feed system utilizes the force of gravity to transfer the fuel from the tanks to the engine. For example, on high-wing airplanes, the fuel tanks are installed in the wings. This places the fuel tanks above the carburetor, and the fuel is gravity-fed through the system and into the carburetor. If the design of the aircraft is such that gravity cannot be used to transfer fuel, fuel pumps are installed. For example, on low-wing airplanes, the fuel tanks in the wings are located below the carburetor. See Figure 6-30. Fuel pump system. Aircraft with fuel pump systems have two fuel pumps. The main pump system is engine-driven with an electrically driven auxiliary pump provided for use in engine starting and in the event the engine pump fails. The auxiliary pump, also known as a boost pump, provides added reliability to the fuel system. The electrically driven auxiliary pump is controlled by a switch in the flight deck. Fuel primer. Both gravity-fed and fuel pump systems may incorporate a fuel primer into the system. The fuel primer is used to draw fuel from the tanks to vaporize fuel directly into the cylinders prior to starting the engine. During cold weather, when engines are difficult to start, the fuel primer helps because there is not enough heat available to vaporize the fuel in the carburetor. It is important to lock the primer in place when it is not in use. If the knob is free to move, it may vibrate out during flight and can cause an excessively rich mixture. To avoid overpriming, read the priming instructions for the aircraft. Fuel tanks. The fuel tanks, normally located inside the wings of an airplane, have a filter opening on top of the wing through which they can be filled. A filler cap covers this opening. The tanks are vented to the outside to maintain atmospheric pressure inside the tank. They may be vented through the filler cap or through a tube extending through the surface of the wing. Fuel tanks also include an overflow drain that may stand alone or be co-located with a fuel tank vent. This allows fuel to expand with increases in temperature without damage to the tank itself. If the tanks have been filled on a hot day, it is not unusual to see fuel coming from the overflow drain. Fuel gauges. The fuel quantity gauges indicate the amount of fuel measured by a sensing unit in each fuel tank and is displayed in gallons or pounds. Aircraft certification rules require accuracy in fuel gauges only when they read empty. Any reading other than empty should be verified. Do not depend solely on the accuracy of fuel quantity gauges. Always visually check the fuel level in each tank during the pre-flight inspection and then compare it with the corresponding fuel quantity indication. If a fuel pump is installed in the fuel system, a fuel pressure gauge is also included. This gauge indicates the pressure in the fuel lines. The normal operating pressure can be found in the AFM/POH or on the gauge by color coding. Fuel selectors. The fuel selector valve allows selection of fuel from various tanks. A common type of selector valve contains 4 positions: left, right, both, and off. Selecting the left or right position allows fuel to feed only from that tank, while selecting the both position feeds fuel from both tanks. The left or right position may be used to balance the amount of fuel remaining in each wing tank. See Figure 6-31. Fuel placards will show any limitations on fuel tank usage, such as level flight only and/or both for landings and takeoffs. Regardless of the type of fuel selector in use, fuel consumption should be monitored closely to ensure that a tank does not run completely out of fuel. Running a fuel tank dry will not only cause the engine to stop, but running for prolonged periods on one tank causes an unbalanced fuel load between tanks. Running a tank completely dry may allow air to enter the fuel system and cause vapor lock, which makes it difficult to restart the engine. On fuel-injected engines, the fuel becomes so hot it vaporizes in the fuel line, not allowing fuel to reach the cylinders. Fuel strainers, sumps, and drains. After leaving the fuel tank and before it enters the carburetor, the fuel passes through a strainer which removes any moisture and other sediments in the system. Since these contaminants are heavier than aviation fuel, they settle in a sump at the bottom of the strainer assembly. A sump is a low point in a fuel system and/or fuel tank. The fuel system may contain sump, fuel strainer, and fuel tank drains, which may be co-located. The fuel strainer should be drained before each flight. Fuel samples should be drained and checked visually for water and contaminants. Water in the sump is hazardous because in cold weather, the water can freeze and block fuel lines. In warm weather, it can flow into the carburetor and stop the engine. If water is present in the sump, more water in the fuel tanks is probable, and they should be drained until there is no evidence of water. Never take off until all water and contaminants have been removed from the engine fuel system. Because of the variation in fuel systems, become thoroughly familiar with the systems that apply to the aircraft being flown. Consult the AFM/POH for specific operating procedures. Fuel grades. Aviation gasoline, AVGAS, is identified by an octane or performance number. Grade. which designates the anti-knock value or knock resistance of the fuel mixture in the engine cylinder. The higher the grade of gasoline, the more pressure the fuel can withstand without detonating. Lower grades of fuel are used in lower compression engines because these fuels ignite at a lower temperature. Higher grades are used in higher compression engines because they ignite at higher temperatures, but not prematurely. If the proper grade of fuel is not available, use the next higher grade as a substitute. Never use a grade lower than recommended. This can cause the cylinder head temperature and engine oil temperature to exceed their normal operating ranges, which may result in detonation. Several grades of AV gas are available. Care must be exercised to ensure that the correct aviation grade is being used for the specific type of engine. The proper fuel grade is stated in the AFM/POH on placards in the flight deck and next to the filler caps. Auto gas should never be used in aircraft systems unless the aircraft has been modified with a Supplemental Type Certificate, STC, issued by the Federal Aviation Administration, FAA. The current method identifies AV gas for aircraft with reciprocating engines by the octane and performance number, along with the abbreviation AV gas. These aircraft use AV gas 80, 100, and 100 LL. Although AV gas 100 LL performs the same as grade 100, the LL indicates that it has low lead content. Fuel for aircraft with turbine engines is classified as Jet A, Jet A-1, and Jet B. Jet fuel is basically kerosene and has a distinctive kerosene smell. Since use of the correct fuel is critical, dyes are added to help identify the type and grade of fuel. See Figure 6-32. In addition to the color of the fuel itself, the color coding system extends to decals and various fuel handling equipment. For example, all AV gas is identified by name using the white letters on a red background. In contrast, turbine fuels are identified by white letters on a black background. Fuel contamination. Accidents attributed to power plant failure from fuel contamination have often been traced to inadequate pre-flight inspection by the pilot, servicing aircraft with improperly filtered fuel from small tanks or drums, storing aircraft with partially filled fuel tanks, lack of proper maintenance. Fuel should be drained from the fuel strainer quick drain and from each fuel tank sump into a transparent container, and then checked for dirt and water. When the fuel strainer is being drained, water in the tank may not appear until all the fuel has been drained from the lines leading to the tank. This indicates that the water remains in the tank and is not forcing the fuel out of the fuel lines leading to the fuel strainer. Therefore, drain enough fuel from the fuel strainer to be certain that the fuel is being drained from the tank. The amount will depend on the length of the fuel line from the tank to the drain. If water or other contaminants are found in the first sample, drain further samples until no trace appears. Water may also remain in the fuel tanks after the drainage from the fuel strainer has ceased to show any trace of water. This residual water can be removed only by draining the fuel tank sump drains. Water is the principal fuel contaminant. Suspended water droplets in the fuel can be identified by a cloudy appearance of the fuel or by the clear separation of water from the colored fuel, which occurs after the water has settled to the bottom of the tank. As a safety measure, the fuel sumps should be drained before every flight during the pre-flight inspection. Fuel tanks should be filled after each flight or after the last flight of the day to prevent moisture condensation within the tank. To prevent fuel contamination, avoid refueling from cans and drums. In remote areas or in emergency situations, there may be no alternative to refueling from sources with inadequate anti-contamination systems. While a cami skin and funnel may be the only possible means of filtering fuel, using them is hazardous. Remember, the use of a cami will not always ensure decontaminated fuel. Worn out camis will not filter water, neither will a new clean cami that is already water wet or damp. Most imitation chamois skins will not filter water. Refueling procedures. Static electricity is formed by the friction of air passing over the surfaces of an aircraft in flight and by the flow of fuel through the hose and nozzle during refueling. Nylon, Dacron, or wool clothing is especially prone to accumulate and discharge static electricity from the person to the funnel or nozzle. To guard against the possibility of static electricity igniting fuel fumes, a ground wire should be attached to the aircraft before the fuel cap is removed from the tank. Because both the aircraft and refueler have different static charges, bonding both components to each other is critical. By bonding both components to each other, the static differential charge is equalized. The refueling nozzle should be bonded to the aircraft before refueling begins, and should not remain bonded throughout the refueling process. While a fuel tank is used, it should be grounded prior to the fuel nozzle contacting the aircraft. If fueling from drums or cans is necessary, proper bonding and grounding connections are important. Drums should be placed near grounding posts and the following sequence of connections observed. 1. Drum to ground. 2. Ground to aircraft. 3. Bond drum to aircraft or nozzle to aircraft before the fuel cap is removed. When disconnecting, reverse the order. Passage of fuel through a chamois increases the charge of static electricity and the danger of sparks. The aircraft must be properly grounded and the nozzle, chamois filter, and funnel bonded to the aircraft. If a can is used, it should be connected to either the grounding post or the funnel. Under no circumstances should a plastic bucket or similar non-conductive container be used in this operation. Electrical system. Most aircraft are equipped with either a 14 or a 28 volt direct current electrical system. A basic aircraft electrical system consists of the following components: alternator/generator, battery, master/battery switch, alternator/generator switch, bus bar, fuses and circuit breakers, voltage regulator, ammeter/load meter, associated electrical wiring. Engine-driven alternators or generators supply electrical current to the electrical system. They also maintain a sufficient electrical charge in the battery. Electrical energy stored in a battery provides a source of electrical power for starting the engine and a limited supply of electrical power for use in the event the alternator or generator fails. Most direct current generators will not produce a sufficient amount of electrical current at low engine RPM to operate the entire electrical system. During operations at low energy RPM, the electrical needs must be drawn from the battery, which can quickly be depleted. Alternators have several advantages over generators. Alternators produce sufficient current to operate the entire electrical system, even at slower engine speeds, by producing alternating current, which is converted to direct current. The electrical output of an alternator is more constant throughout the wide range of engine speeds. Some aircraft have receptacles to which an external ground power unit, GPU, may be connected to provide electrical energy for starting. These are very useful, especially during cold weather starting. Follow the manufacturer's recommendations for engine starting using a GPU. The electrical system is turned on or off with a master switch. Turning the master switch to the on position provides electrical energy to all the electrical equipment circuits, except the ignition system. Equipment that commonly uses the electrical system for its source of energy includes position lights, anti-collision lights, landing lights, taxi lights, interior cabin lights, instrument lights, radio equipment, turn indicator, fuel gauges, electric fuel pump, stall warning system, pilot heat, starting motor. Many aircraft are equipped with a battery switch that controls the electrical power to the aircraft in a manner similar to the master switch. In addition, an alternator switch is installed, which permits the pilot to exclude the alternator from the electrical system in the event of an alternator failure. See Figure 6-33. While the alternator half of the switch is in the off position, the entire electrical load is placed on the battery. All non-essential electrical equipment should be turned off to conserve battery power. A bus bar is used as a terminal in the aircraft electrical system to connect the main electrical system to the equipment using electricity as a source of power. This simplifies the wiring system and provides a common point from which voltage can be distributed throughout the system. See Figure 6-34. Fuses or circuit breakers are used in the electrical system to protect the circuits and equipment from electrical overload. Spare fuses of the proper amperage limit should be carried in the aircraft to replace defective or blown fuses. Circuit breakers have the same function as a fuse but can be manually reset rather than replaced if an overload condition occurs in the electrical system. Placards at the fuse or circuit breaker panel identify the circuit by name and show the amperage limit. An ammeter is used to monitor performance of the aircraft electrical system. The ammeter shows if the alternator/generator is producing an adequate supply of electrical power. It also indicates whether or not the battery is receiving an electrical charge. Ammeters are designed with the 0 point in the center of the face and a negative or positive indication on either side. See Figure 6-35. When the pointer of the ammeter is on the plus side, it shows the charging rate of the battery. A minus indication means more current is being drawn from the battery than is being replaced. A full-scale minus deflection indicates a malfunction in the alternator/generator. A full-scale positive deflection indicates a malfunction of the regulator. In either case, consult the AFM or POH for appropriate action to be taken. Not all aircraft are equipped with an ammeter. Some have a warning light that, when lighted, indicates a discharge in the system as a generator/alternator malfunction. Refer to the AFM or POH for appropriate action to be taken. Another electrical monitoring indicate is a load meter. This type of gauge has a scale beginning with 0 and shows the load being placed on the alternator/generator. See Figure 6-35. The load meter reflects the total percentage of the load placed on the generating capacity of the electrical system by the electrical accessories and battery. When all electrical components are turned off, it reflects only the amount of charging current demanded by the battery. A voltage regulator controls the rate of charge to the battery by stabilizing the generator or alternator electrical output. The generator/alternator voltage output should be higher than the battery voltage. For example, a 12-volt battery should be fed by a generator/alternator system of approximately 14 volts. The difference in voltage keeps the battery charged. End of Part 6 of Chapter 6. Part 7 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 7. Hydraulic Systems. There are multiple applications for hydraulic use in aircraft, depending on the complexity of the aircraft. For example, hydraulics is often used on small airplanes to operate wheel brakes, retractable landing gear, and some constant speed propellers. On large airplanes, hydraulics is used for flight control systems, wing flaps, spoilers, and other systems. A basic hydraulic system consists of a reservoir, pump, either hand, electric, or engine-driven, a filter to keep the fluid clean, selector valve to control the direction of flow, relief valve to relieve excess pressure, and an actuator. See Figure 6-36. The hydraulic fluid is pumped through the system to an actuator or servo. A servo is a cylinder with a piston inside that turns fluid power into work and creates the power needed to move an aircraft system or flight control. Servos can be either single-acting or double-acting based on the needs of the system. This means that the fluid can be applied to one or both sides of the servo, depending on the servo type. A single-acting servo provides power in one direction. The selector valve allows the fluid direction to be controlled. This is necessary for operations such as the extension and retraction of landing gear, during which the fluid must work in two different directions. The relief valve provides an outlet for the system in the event of excess fluid pressure in the system. Each system incorporates different components to meet the individual needs of different aircraft. A mineral-based hydraulic fluid is the most widely used type for small aircraft. This type of hydraulic fluid, a kerosene-like petroleum product, has good lubricating properties as well as additives to inhibit foaming and prevent the formation of corrosion. It is chemically stable, has very little viscosity change with temperature, and is dyed for identification. Since several types of hydraulic fluids are commonly used, an aircraft must be serviced with the type specified by the manufacturer. Refer to the AFM/POH or the maintenance manual. Landing gear. The landing gear forms the principal support of an aircraft on the surface. The most common type of landing gear consists of wheels, but aircraft can be equipped with floats for water operations or skis for landing on snow. See Figure 6-37. The landing gear on small aircraft consists of 3 wheels, 2 main wheels, one located on each side of the fuselage, and a third wheel positioned at either the front or the rear of the airplane. Landing gear employing a rear-mounted wheel is called conventional landing gear. Airplanes with conventional landing gear are often referred to as tailwheel airplanes. When the third wheel is located on the nose, it is called a nose wheel, and the design is referred to as a tricycle gear. A steerable nose wheel or tail wheel permits the airplane to be controlled throughout all operations while on the ground. Tricycle landing gear airplanes. A tricycle gear airplane has 3 advantages. 1. It allows more forceful application of the brakes during landings at high speeds without causing the aircraft to nose over. 2. It permits better forward visibility for the pilot during takeoff, landing, and taxiing. 3. It tends to prevent ground looping, or swerving, by providing more directional stability during ground operations since the aircraft's center of gravity, CG, is forward of the main wheels. The forward CG keeps the aircraft moving forward in a straight line rather than ground looping. Nose wheels are either steerable or castering. Steerable nose wheels are linked to the rudders by cables or rods, while castering nose wheels are free to swivel. In both cases, the aircraft is steering using the rudder pedals. Aircraft with a castering nose wheel may require the pilot to combine the use of the rudder pedals with independent use of the brakes. Tailwheel landing gear airplanes. Tailwheel landing gear aircraft have 2 main wheels attached to the airframe ahead of its CG that support most of the weight of the structure. A tailwheel at the very back of the fuselage provides a third point of support. This arrangement allows adequate ground clearance for a larger propeller and is more desirable for operations on unimproved fields. See Figure 6-38. With the CG located behind the main gear, directional control of this type aircraft becomes more difficult while on the ground. This is the main disadvantage of the tailwheel landing gear. For example, if the pilot allows the aircraft to swerve while rolling on the ground at a low speed, he or she may not have sufficient rudder control, and the CG will attempt to get ahead of the main gear, which may cause the airplane to ground loop. Lack of good forward visibility when the tailwheel is on or near the ground is a second disadvantage of tailwheel landing gear aircraft. These inherent problems mean specific training is required in tailwheel aircraft. Fixed and retractable landing gear. Landing gear can also be classified as either fixed or retractable. A fixed gear always remains extended and has the advantage of simplicity combined with low maintenance. A retractable gear is designed to streamline the airplane by allowing the landing gear to be stowed inside the structure during cruising flight. See Figure 6-39. Brakes. Airplane brakes are located on the main wheels and are applied by either a hand control or by foot pedals, toe or heel. Foot pedals operate independently and allow for differential braking. During ground operations, differential braking can supplement nose wheel/tail wheel steering. Pressurized aircraft. Aircraft are flown at high altitudes for 2 reasons. First, an aircraft flown at high altitude consumes less fuel for a given airspeed than it does for the same speed at a lower altitude because the aircraft is more efficient at a high altitude. Second, bad weather and turbulence may be avoided by flying in relatively smooth air above the storms. Many modern aircraft are designed to operate at high altitudes, taking advantage of that environment. In order to fly at higher altitudes, the aircraft must be pressurized. It is important for pilots who fly these aircraft to be familiar with the basic operating principles. In a typical pressurization system, the cabin, flight compartment, and baggage compartments are incorporated in a sealed unit capable of containing air under a pressure higher than outside atmospheric pressure. On aircraft powered by turbine engines, bleed air from the engine compressor section is used to pressurize the cabin. Superchargers may be used on older model turbine-powered aircraft to pump air into the sealed fuselage. Piston-powered aircraft may use air supplied from each engine turbocharger through a sonic venturi, or flow limiter. Air is released from the fuselage by a device called an outflow valve. By regulating the air exit, the outflow valve allows for a constant inflow of air to the pressurized area. See Figure 6-40. A cabin pressurization system typically maintains a cabin pressure altitude of approximately 8,000 feet at the maximum designed cruising altitude of an aircraft. This prevents rapid changes of cabin altitude that may be uncomfortable or cause injury to passengers and crew. In addition, the pressurization system permits a reasonably fast exchange of air from the inside to the outside of the cabin. This is necessary to eliminate odors and to remove stale air. See Figure 6-41. Pressurization of the aircraft cabin is an accepted method of protecting occupants against the effects of hypoxia. Within a pressurized cabin, occupants can be transported comfortably and safely for long periods of time, particularly if the cabin altitude is maintained at 8,000 feet or below, where the use of oxygen equipment is not required. The flight crew in this type of aircraft must be aware of the danger of accidental loss of cabin pressure and be prepared to deal with such an emergency whenever it occurs. The following terms will aid in understanding the operating principles of pressurization and air conditioning systems. Aircraft altitude, the actual height above sea level at which the aircraft is flying. Ambient temperature, the temperature in the area immediately surrounding the aircraft. Ambient pressure, pressure in the area immediately surrounding the aircraft. Cabin altitude, cabin pressure in terms of equivalent altitude above sea level. Differential pressure, the difference in pressure between the pressure acting on one side of a wall and the pressure acting on the other side of the wall. In aircraft air conditioning and pressurizing systems, it is the difference between cabin pressure and atmospheric pressure. The cabin pressure control system provides cabin pressure regulation, pressure relief, vacuum relief, and the means for selecting the desired cabin altitude in the isobaric and differential range. In addition, dumping of the cabin pressure is a function of the pressure control system. A cabin pressure regulator, an outflow valve, and a safety valve are used to accomplish these functions. The cabin pressure regulator controls cabin pressure to a selected valve in the isobaric range and limits cabin pressure to a preset differential value in the differential range. When an aircraft reaches the altitude at which the difference between the pressure inside and outside the cabin is equal to the highest differential pressure from which the fuselage structure is designed, a further increase in aircraft altitude will result in a corresponding increase in cabin altitude. Differential control is used to prevent the maximum differential pressure, for which the fuselage was designed, from being exceeded. This differential pressure is determined by the structural strength of the cabin and is often by the relationship of the cabin size to the probable areas of rupture, such as window areas and doors. The cabin air pressure safety valve is a combination pressure relief, vacuum relief, and dump valve. The pressure relief valve prevents cabin pressure from exceeding a predetermined differential pressure above ambient pressure. The vacuum relief prevents ambient pressure from exceeding cabin pressure by allowing external air to enter the cabin when ambient pressure exceeds cabin pressure. The flight deck control switch actuates the dump valve. When this switch is positioned to ram, a solenoid valve opens, causing the valve to dump cabin air to atmosphere. The degree of pressurization and the operating altitude of the aircraft are limited by several critical design factors. Primarily, the fuselage is designed to withstand a particular maximum cabin differential pressure. Several instruments are used in conjunction with the pressurization controller. The cabin differential pressure gauge indicates the difference between inside and outside pressure. This gauge should be monitored to assure that the cabin does not exceed the maximum allowable differential pressure. A cabin altimeter is provided as a check on the performance of the system. In some cases, these two instruments are combined into one. A third instrument indicates the cabin rate of climb or descent. A cabin rate of climb instrument and a cabin altimeter are illustrated in Figure 6-42. Decompression is defined as the inability of the aircraft's pressurization system to maintain its design pressure differential. This can be caused by a malfunction in the pressurization system or structural damage to the aircraft. Physiologically, decompressions fall into two categories. Explosive decompression, a change in cabin pressure faster than the lungs can decompress, possibly causing lung damage. Normally, the time required to release air from the lungs without restrictions, such as masks, is 0.2 seconds. Most authorities consider any decompression that occurs in less than 0.5 seconds to be explosive and potentially dangerous. Rapid decompression, a change in cabin pressure in which the lungs decompress faster than the cabin, resulting in no likelihood of lung damage. During an explosive decompression, there may be noise, and one may feel dazed for a moment. The cabin air fills with fog, dust, or flying debris. Fog occurs due to the rapid drop in temperature and the change in relative humidity. Normally, the ears clear automatically. Air rushes from the mouth and the nose due to the escape of air from the lungs, and may be noticed by some individuals. Rapid decompression decreases the period of useful consciousness because oxygen in the lungs is exhaled rapidly, reducing pressure on the body. This decreases the partial pressure of the oxygen in the blood and reduces the pilot's effective performance time by 1/3 to 1/4 of its normal time. For this reason, an oxygen mask should be worn when flying at very high altitudes, 35,000 feet or higher. It is recommended that the crew members select the 100% oxygen setting on the oxygen regulator at high altitude if the aircraft is equipped with a demand or pressure demand oxygen system. The primary danger of decompression is hypoxia. Quick, proper utilization of oxygen equipment is necessary to avoid unconsciousness. Another potential danger that pilots, crew, and passengers face during high-altitude decompressions is evolved gas decompression sickness. This occurs when the pressure on the body drops sufficiently, nitrogen comes out of solution, and forms bubbles that can have adverse effects on some body tissues. Decompression caused by structural damage to the aircraft presents another type of danger to the pilots, crew, and passengers, being tossed or blown out of the aircraft if they are located near openings. Individuals near openings should wear safety harnesses or seatbelts at all times when the aircraft is pressurized and they are seated. Structural damage also has potential to expose them to wind blasts and extremely cold temperatures. Rapid descent from altitude is necessary if these problems are to be minimized. Automatic visual and aural warning systems are included in the equipment of all pressurized aircraft. End of Part 7 of Chapter 6. Part 8 of Chapter 6 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Stefan Schweigert. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 8. Oxygen Systems. Most high-altitude aircraft come equipped with some type of fixed oxygen installation. If the aircraft does not have a fixed installation, portable oxygen equipment must be readily accessible during flight. The portable equipment usually consists of a container, regulator, mask outlet, and pressure gauge. Aircraft oxygen is usually stored in a high-pressure system containers of 1800 to 2200 psi. When the ambient temperature surrounding an oxygen cylinder decreases, pressure within that cylinder decreases because pressure varies directly with temperature if the volume of a gas remains constant. If a drop in indicated pressure on a supplemental oxygen cylinder is noted, there is no reason to suspect depletion of the oxygen supply, which has been compacted due to storage of containers in an unheated area of the aircraft. High-pressure oxygen containers should be marked with the PSI tolerance, i.e. 1800 psi, before filling the container to that pressure. The containers should be supplied with aviation oxygen only, which is 100% pure oxygen. Industrial oxygen is not intended for breathing and may contain impurities, and medical oxygen contains water vapor that can freeze in the regulator when exposed to cold temperatures. To assure safety, periodic inspection and servicing of the oxygen system should be done. An oxygen system consists of a mask or cannula and a regulator that supplies a flow of oxygen dependent upon cabin altitude. Cannulas are not approved for flights above 18,000 feet. Regulators approved for use up to 40,000 feet are designed to provide 0% cylinder oxygen and 100% cabin air at cabin altitudes of 8,000 feet or less, with the ratio changing to 100% oxygen and 0% cabin air at approximately 34,000 feet cabin altitude. See Figure 6-43. Regulators approved up to 45,000 feet are designed to provide 40% cylinder oxygen and 60% cabin air at low altitudes, with the ratio changing to 100% at the higher altitude. Pilots should avoid flying above 10,000 feet without oxygen during the day and above 8,000 feet at night. Pilots should be aware of the danger of fire when using oxygen. Materials that are nearly fireproof in ordinary air may be susceptible to combustion in oxygen. Oils and greases may ignite if exposed to oxygen and cannot be used for sealing the valves and fittings of oxygen equipment. Smoking during any kind of oxygen equipment use is prohibited. Before each flight, The pilot should thoroughly inspect and test all oxygen equipment. The inspection should include a thorough examination of the aircraft oxygen equipment, including available supply, an operational check of the system, and assurance that the supplemental oxygen is readily accessible. The inspection should be accomplished with clean hands and should include a visual inspection of the mask and tubing for tears, cracks, or deterioration, the regulator for valve and lever condition and positions, oxygen quantity, and the location and functioning of oxygen pressure gauges, flow indicators, and connections. The mask should be donned and the system should be tested. After any oxygen use, verify that all components and valves are shut off. Oxygen masks. There are numerous types and designs of oxygen masks in use. The most important in oxygen mask use is to ensure the masks and oxygen system are compatible. Crew masks are fitted to the user's face with a minimum of leakage and usually contain a microphone. Most masks are the oral-nasal type, which covers only the mouth and nose. A passenger mask may be a simple cup-shaped rubber molding sufficiently flexible to obviate individual fitting. It may have a simple elastic head strap, or the passenger may hold it to his or her face. All oxygen masks should be kept clean to reduce the danger of infection and prolong the life of the mask. To clean the mask, wash it with a mild soap and water solution, and rinse it with clear water. If a microphone is installed, use a clean swab instead of running water to wipe off the soapy solution. The mask should also be disinfected. A gauze pad that has been soaked in a water solution of merthiolate can be used to swab out the mask. This solution should contain 1/5 teaspoon of merthiolate per quart of water. Wipe the mask with a clean cloth and air dry. Cannula. A cannula is an ergonomic piece of plastic tubing which runs under the nose and is often used to administer oxygen in non-pressurized aircraft. See Figure 6-44. Cannulas are typically more comfortable than masks and can be used up to 18,000 feet. Altitudes greater than 18,000 feet require the use of an oxygen mask. Many cannulas have a flow meter in the line. If equipped, a periodic check of the green flow detector should be part of a pilot's regular scan. Diluter demand oxygen systems. Diluter demand oxygen systems supply oxygen only when the user inhales through the mask. An auto mix lever allows the regulators to automatically mix cabin air and oxygen or supply 100% oxygen, depending on the altitude. The demand mask provides a tight seal over the face to prevent dilution with outside air and can be used safely up to 40,000 feet. A pilot who has a beard or mustache should be sure it is trimmed in a manner that will not interfere with the sealing of the oxygen mask. The fit of the mask around the beard or mustache should be checked on the ground for proper sealing. Pressure demand oxygen systems. Pressure demand oxygen systems are similar to diluter demand oxygen equipment, except that the oxygen is supplied to the mask under pressure at cabin altitudes above 34,000 feet. Pressure demand regulators create airtight and oxygen-tight seals, but they also provide a positive pressure application of oxygen to the mask facepiece that allows the user's lungs to be pressurized with oxygen. This feature makes pressure demand regulators safe at altitudes above 40,000 feet. Some systems may have a pressure demand mask with the regulator attached directly to the mask, rather than mounted on the instrument panel or other area within the flight deck. The mask-mounted regulator eliminates the problem of a long hose that must be purged of air before 100% oxygen begins flowing into the mask. Continuous flow oxygen system. Continuous flow oxygen systems are usually provided for passengers. The passenger mask typically has a reservoir bag, which collects oxygen from the continuous flow oxygen system during the time when the mask user is inhaling. The oxygen collected in the reservoir bag allows a higher aspiratory flow rate during the inhalation cycle, which reduces the amount of air dilution. Ambient air is added to the supplied oxygen during inhalation after the reservoir bag oxygen supply is depleted. The exhaled air is released to the cabin. See Figure 6-45. Electrical pulse demand oxygen system. Portable electrical pulse demand oxygen systems deliver oxygen by detecting an individual's inhalation effort and provide oxygen flow during the initial portion of inhalation. Pulse demand systems do not waste oxygen during the breathing cycle because oxygen is only delivered during inhalation. Compared to continuous flow systems, the pulse demand method of oxygen delivery can reduce the amount of oxygen needed by 50 to 85%. Most pulse demand oxygen systems also incorporate an internal barometer that automatically compensates for changes in altitude by increasing the amount of oxygen delivered for each pulse as altitude is increased. See Figure 6-46. Pulse oximeters. A pulse oximeter is a device that measures the amount of oxygen in an individual's blood, in addition to heart rate. This non-invasive device measures the color changes that red blood cells undergo when they become saturated with oxygen. By transmitting a special light beam through a fingertip to evaluate the color of red cells, a pulse oximeter can calculate the degree of oxygen saturation within 1% of directly measured blood oxygen. Because of their portability and speed, pulse oximeters are useful for pilots operating in a non-pressurized aircraft above 12,500 feet, where supplemental oxygen is required. A pulse oximeter permits crew members and passengers of an aircraft to evaluate their actual need for supplemental oxygen. See Figure 6-47. Servicing of oxygen systems. Before servicing any aircraft with oxygen, consult the specific aircraft service manual to determine the type of equipment required and the procedures to be used. Certain precautions should be observed whenever aircraft oxygen systems are to be serviced. Oxygen system servicing should be accomplished only when the aircraft is located outside of the hangars. Personal cleanliness and good housekeeping are imperative when working with oxygen. Oxygen under pressure and petroleum products create spontaneous results when they are brought in contact with each other. Service people should be certain to wash dirt, oil, and grease, including lip salves and hair oil, from their hands before working around oxygen equipment. It is also essential that clothing and tools are free of oil, grease, and dirt. Aircraft with permanently installed oxygen tanks usually require 2 persons to accomplish servicing of the system. One should be stationed at the service equipment control valves, and the other stationed where he or she can observe the aircraft system pressure gauges. Oxygen system servicing is not recommended during aircraft fueling operations or while other work is performed that could provide a source of ignition. Oxygen system servicing while passengers are on board the aircraft is not recommended. Anti-ice and de-ice systems. Anti-icing equipment is designed to prevent the formation of ice, while de-icing equipment is designed to remove ice once it has formed. These systems protect the leading edge of wing and tail surfaces, pilot and static port openings, fuel tank vents, stall warning devices, windshields, and propeller blades. Ice detection lighting may also be installed on some aircraft to determine the extent of structural icing during night flights. Most light aircraft have only a heated pilot tube and are not certified for flight in icing. These light aircraft have limited cross-country capability in the cooler climates during late fall, winter, and early spring. Non-certified aircraft must exit icing conditions immediately. Refer to the AFM/POH for details. Airfoil anti-ice and de-ice. Inflatable de-icing boots consist of a rubber sheet bonded to the leading edge of the airfoil. When ice builds up on the leading edge, an engine-driven pneumatic pump inflates the rubber boots. Many turboprop aircraft divert engine bleed air to the wing to inflate the rubber boots. Upon inflation, the ice is cracked and should fall off the leading edge of the wing. De-icing boots are controlled from the flight deck by a switch and can be operated in a single cycle or allowed to cycle at automatic, timed intervals. See Figure 6-48. In the past, it was believed that if the boots were cycled too soon after encountering ice, the ice layer would expand instead of breaking off, resulting in a condition referred to as ice bridging. Consequently, subsequent de-ice boot cycles would be ineffective at removing the ice buildup. Although some residual ice may remain after a boot cycle, bridging does not occur with any modern boots. Pilots can cycle the boots as soon as an ice accumulation is observed. Consult the AFM/POH for information on the operation of de-ice boots on an aircraft. Many de-icing boot systems use the instrument system suction gauge and a pneumatic pressure gauge to indicate proper boot operation. These gauges have range markings that indicate the operating limits for boot operation. Some systems may also incorporate an annunciator light to indicate proper boot operation. Proper maintenance and care of de-icing boots are important for continued operation of this system. They need to be carefully inspected during pre-flight. Another type of leading-edge protection is the thermal anti-ice system. Heat provides one of the most effective methods for preventing ice accumulation on an airfoil. High-performance turbine aircraft often direct hot air from the compressor section of the engine to the leading-edge surfaces. The hot air heats the leading edge surfaces sufficiently to prevent the formation of ice. A newer type of thermal anti-ice system, referred to as thermowing, uses electrically heated graphite foil laminate applied to the leading edge of the wing and the horizontal stabilizer. Thermowing systems typically have two zones of heat application. One zone on the leading edge receives continuous heat. The second zone further aft receives heat in cycles to dislodge the ice, allowing aerodynamic forces to remove it. Thermal anti-ice systems should be activated prior to entering icing conditions. An alternate type of leading edge protection that is not as common as thermal anti-ice and de-icing boots is known as a weeping wing. The weeping wing design uses small holes located in the leading edge of the wing to prevent the formation and buildup of ice. An antifreeze solution is pumped to the leading edge and weeps out through the holes. Additionally, the weeping wing is capable of de-icing an aircraft. When ice is accumulated on the leading edges, application of the antifreeze solution chemically breaks down the bond between the ice and airframe, allowing aerodynamic forces to remove the ice. See Figure 6-48. Windscreen anti-ice. There are two main types of windscreen anti-ice systems. The first system directs a flow of alcohol to the windscreen. If used early enough, the alcohol will prevent ice from building up on the windscreen. The rate of alcohol flow can be controlled by a dial in the flight deck, according to procedures recommended by the aircraft manufacturer. Another method of anti-icing equipment is the electrical heating method. Small wires or other conductive material is embedded in the windscreen. The heater can be turned on by a switch in the flight deck, causing an electrical current to be passed across the shield through the wires to provide sufficient heat to prevent the formation of ice on the windscreen. The heated windscreen should only be used during flight. Do not leave it on during ground operations, as it can overheat and cause damage to the windscreen. Warning: the electrical current can cause compass deviation errors by as much as 40 degrees. Propeller anti-ice. Propellers are protected from icing by use of alcohol or electrically heated elements. Some propellers are equipped with a discharge nozzle that is pointed towards the root of the blade. Alcohol is discharged from the nozzles, and the centrifugal force drives the alcohol down the leading edge of the blade. The boots are also grooved to help direct the flow of alcohol. This prevents ice from forming on the leading edge of the propeller. Propellers can also be fitted with propeller anti-ice boots. The propeller boot is divided into two sections, the inboard and the outboard sections. The boots are embedded with electrical wires that carry current for heating the propeller. The prop anti-ice system can be monitored for proper operation by monitoring the prop anti-ice ammeter. During the pre-flight inspection, check the propeller boots for proper operation. If a boot fails to heat one blade, an unequal blade loading can result and may cause severe propeller vibration. See Figure 6-49. Other anti-ice and de-ice systems. Pitot and static ports, fuel vents, stall warning sensors, and other operational equipment may be heated by electrical elements. Operational checks of the electrically heated systems are to be checked in accordance with the AFM/POH. Operation of aircraft anti-icing and de-icing systems should be checked prior to encountering icing conditions. Encounters with structural ice require immediate action. Anti-icing and de-icing equipment are not intended to sustain long-term flight in icing conditions. Chapter Summary. All aircraft have a requirement for essential systems such as the engine, propeller, induction, ignition systems, as well as the fuel, lubrication, cooling, electrical, landing gear, and environmental control systems to support flight. Understanding the aircraft systems of the aircraft being flown is critical to its safe operation and proper maintenance. Consult the AFM/POH for specific information pertaining to the aircraft being flown. Various manufacturer and owner group websites can also be a valuable source of additional information. End of Chapter 6.
Part 1 of Chapter 7 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 7, Part 1. Flight Instruments. Introduction. In order to safely fly any aircraft, a pilot must understand how to interpret and operate the flight instruments. The pilot also needs to be able to recognize associated errors and malfunctions of these instruments. This chapter addresses the pitot-static system and associated instruments, the vacuum system and related instruments, gyroscopic instruments, and the magnetic compass. When a pilot understands how each instrument works and recognizes when an instrument is malfunctioning, he or she can safely utilize the instruments to their fullest potential. Pitot-static flight instruments. The pitot-static system is a combined system that utilizes the static air pressure and the dynamic pressure due to the motion of the aircraft through the air. These combined pressures are utilized for the operation of the airspeed indicator, ASI, altimeter, and vertical speed indicator, VSI. Figure 7-1. Impact pressure chamber and lines. The pitot tube is utilized to measure the total combined pressures that are present when an aircraft moves through the air. Static pressure, also known as ambient pressure, is always present whether an aircraft is moving or at rest. It is simply the barometric pressure in the local area. Dynamic pressure is present only when an aircraft is in motion. Therefore, it can be thought of as a pressure due to motion. Wind also generates dynamic pressure. It does not matter if the aircraft is moving through still air at 70 knots, or if the aircraft is facing a wind with a speed of 70 knots. The same dynamic pressure is generated. When the wind blows from an angle less than 90 degrees off the nose of the aircraft, dynamic pressure can be depicted on the ASI. The wind moving across the airfoil at 20 knots is the same as the aircraft moving through calm air at 20 knots. The pitot tube captures the dynamic pressure, as well as the static pressure that is always present. The pitot tube has a small opening at the front which allows the total pressure to enter the pressure chamber. The total pressure is made up of dynamic pressure plus static pressure. In addition to the larger hole in the front of the pitot tube, there is a small hole in the back of the chamber, which allows moisture to drain from the system should the aircraft enter precipitation. Both openings in the pitot tube need to be checked prior to flight to ensure that neither is blocked. Many aircraft have pitot tube covers installed when they sit for extended periods of time. This helps to keep bugs and other objects from becoming lodged in the opening of the pitot tube. The one instrument that utilizes the pitot tube is the ASI. The total pressure is transmitted to the ASI from the pitot tube's pressure chamber via a small tube. The static pressure is also delivered to the opposite side of the ASI, which serves to cancel out the two static pressures, thereby leaving the dynamic pressure to be indicated on the instrument. When the dynamic pressure changes, the ASI shows either increase or decrease, corresponding to the direction of change. The two remaining instruments, altimeter and VSI, utilize only the static pressure, which is derived from the static port. Static pressure chamber and lines. The static chamber is vented through small holes to the free, undisturbed air on the sides of the aircraft. As the atmospheric pressure changes, the pressure is able to move freely in and out of the instruments through the small lines which connect the instruments into the static system. An alternate static source is provided in some aircraft to provide static pressure should the primary static source become blocked. The alternate static source is normally found inside of the flight deck. due to the Venturi effect of the air flowing around the fuselage. The air pressure inside the flight deck is lower than the exterior pressure. When the alternate static source pressure is used, the following instrument indications are observed. 1. The altimeter indicates a slightly higher altitude than actual. 2. The ASI indicates an airspeed greater than the actual airspeed. 3. The VSI shows a momentary climb and then stabilizes if the altitude is held constant. Each pilot is responsible for consulting the Aircraft Flight Manual, AFM, or the Pilot's Operating Handbook, POH, to determine the amount of error that is introduced into the system when utilizing the alternate static source. In an aircraft not equipped with an alternate static source, an alternate method of introducing static pressure into the system, should a blockage occur, is to break the glass face of the VSI. This most likely renders the VSI inoperative. The reason for choosing the VSI as the instrument to break is that it is the least important static source instrument for flight. Altimeter. The altimeter is an instrument that measures the height of an aircraft above a given pressure level. Pressure levels are discussed later in detail. Since the altimeter is the only instrument that is capable of indicating altitude, this is one of the most vital instruments installed in the aircraft. To use the altimeter effectively, the pilot must understand the operation of the instrument, as well as the errors associated with the altimeter and how each affect the indication. A stack of sealed aneroid wafers comprise the main component of the altimeter. An aneroid wafer is a sealed wafer that is evacuated to an internal pressure of 29.92 inches of mercury, 29.92 inches Hg. These wafers are free to expand and contract with changes to the static pressure. A higher static pressure presses down on the wafers and causes them to collapse. A lower static pressure, less than 29.92 inches of mercury, allows the wafers to expand. A mechanical linkage connects the wafer movement to the needles on the indicator face, which translates compression of the wafers into a decrease in altitude, and translates an expansion of the wafers into an increase in altitude. Figure 7-2 with errata. Notice how the static pressure is introduced into the rear of the sealed altimeter case. The altimeter's outer chamber is sealed, which allows the static pressure to surround the aneroid wafers. If the static pressure is higher than the pressure in the aneroid wafers, 29.92 inches of mercury, then the wafers are compressed until the pressure inside the wafers is equal to the surrounding static pressure. Conversely, if the static pressure is less than the pressure inside of the wafers are able to expand, which increases the volume. The expansion and contraction of the wafers moves the mechanical linkage, which drives the needles on the face of the altimeter. Principle of operation. The pressure altimeter is an aneroid barometer that measures the pressure of the atmosphere at the level where the altimeter is located, and presents an altitude indication in feet. The altimeter uses static pressure as its source of operation. Air is denser at sea level than aloft. As altitude increases, atmospheric pressure decreases. This difference in pressure at various levels causes the altimeter to indicate changes in altitude. The presentation of altitude varies considerably between different types of altimeters. Some have one pointer, while others have two or more. Only the multi-pointer type is discussed in this handbook. The dial of a typical altimeter is graduated with numerals arranged clockwise from 0 to 9. Movement of the aneroid element is transmitted through gears to the three hands that indicate altitude. In Figure 7-2, the long, thin needle with the inverted triangle at the end indicates tens of thousands of feet. The short, wide needle indicates thousands of feet, and the long needle on top indicates hundreds of feet. This indicated altitude is correct, however, only when the sea level barometric pressure is standard, 29.92 inches of mercury. The sea level free air temperature is standard, plus 15 degrees Celsius, or 59 degrees Fahrenheit, and the pressure and temperature decrease at a standard rate with an increase in altitude. Adjustments for non-standard pressures are accomplished by setting the corrected pressure into a barometric scale located on the face of the altimeter. The barometric pressure window is sometimes referred to as the Colesman window. Only after the altimeter is set does it indicate the correct altitude. The word correct will need to be better explained when referring to types of altitudes, but is commonly used in this case to denote the approximate altitude above sea level. In other words, the indicated altitude refers to the altitude read off of the altitude which is uncorrected, after the barometric pressure setting is dialed into the Colesman window. The additional types of altitudes are further explained later. Effect of non-standard pressure and temperature. It is easy to maintain a consistent height above ground if the barometric pressure and temperature remain constant, but this is rarely the case. The pressure and temperature can change between takeoff and landing, even on a local flight. If these changes are not taken into consideration, flight becomes dangerous. If altimeters could not be adjusted for non-standard pressure, a hazardous situation could occur. For example, if an aircraft is flown from a high-pressure area to a low-pressure area without adjusting the altimeter, a constant altitude will be displayed, but the actual height of the aircraft above the ground would be lower than the indicated altitude. There is an old aviation axiom: going from a high to a low, look out below. Conversely, if an aircraft is flown from a low-pressure area to a high-pressure area without an adjustment of the altimeter, the actual altitude of the aircraft is higher than the indicated altitude. Once in flight, it is important to frequently obtain current altimeter settings en route to ensure terrain and obstruction clearance. Many altimeters do not have an accurate means of being adjusted for barometric pressures in excess of 31.00 inches of mercury, inches Hg. When the altimeter cannot be set to the higher pressure setting, the aircraft actual altitude will be higher than the altimeter indicates. When low barometric pressure conditions occur, below 28.00, flight operations by aircraft unable to set the actual altimeter setting are not recommended. Adjustments to compensate for non-standard pressure do not compensate for non-standard temperature. Since cold air is denser than warm air, when operating in temperatures that are colder than standard, the altitude is lower than the altimeter indication. Figure 7-3. It is the magnitude of this difference that determines the magnitude of the error. It is the difference due to colder temperatures that concerns the pilot. When flying into a cooler air mass while maintaining a constant indicated altitude, true altitude is lower. If terrain or obstacle clearance is a factor in selecting a cruising altitude, particularly in mountainous terrain, remember to anticipate that a colder than standard temperature places the aircraft lower than the altimeter indicates. Therefore, a higher indicated altitude may be required to provide adequate terrain clearance. A variation of the memory aid used for pressure can be employed. From hot to cold, look out below. When the air is warmer than standard, the aircraft is higher than the altimeter indicates. Altitude corrections for temperature can be computed on the navigation computer. Extremely cold temperatures will also affect altimeter indications. Figure 7-4, which was derived from ICAO formulas, indicates how much error can exist when the temperature is extremely cold. Setting the altimeter. Most altimeters are equipped with a barometric pressure setting window, or Kollsman window, providing a means to adjust the altimeter. A knob is located at the bottom of the instrument for this adjustment. To adjust the altimeter for variation in atmospheric pressure, the pressure scale in the altimeter setting window, calibrated in inches of mercury, inches Hg, and/or millibars, MB, is adjusted to match the given altimeter setting. Altimeter setting is defined as station pressure reduced to sea level, but an altimeter setting is accurate only in the vicinity of the reporting station. Therefore, the altimeter must be adjusted as the flight progresses from one station to the next. Air Traffic Control, ATC, will advise when updated altimeter settings are available. If a pilot is not utilizing ATC assistance, local altimeter settings can be obtained by monitoring local automated weather observing system, automated surface observation system, AWOS/ASOS, or Automatic Terminal Information Service, ATIS, broadcasts. Many pilots confidently expect the current altimeter setting will compensate for irregularities in atmospheric pressure at all altitudes, but this is not always true. The altimeter setting broadcast by ground stations is the station pressure corrected to mean sea level. It does not account for the irregularities at higher levels, particularly the effect of non-standard temperature. If each pilot in a given area is using the same altimeter setting, each altimeter should be equally affected by temperature and pressure variation errors, making it possible to maintain the desired vertical separation between aircraft. This does not guarantee vertical separation, though. It is still imperative to maintain a regimented visual scan for intruding air traffic. When flying over high mountainous terrain, certain atmospheric conditions cause the altimeter to indicate an altitude of 1,000 feet or more higher than the actual altitude. For this reason, a generous margin of altitude should be allowed, not only for possible altimeter error, but also for possible downdrafts that might be associated with high winds. To illustrate the use of the altimeter setting system, follow a flight from Dallas Love Field, Texas, to Abilene Municipal Airport, Texas, via Mineral Wells. Before taking off from Love Field, the pilot receives a current altimeter setting of 29.85 inches of mercury from the control tower, or ATIS, and sets this value in the altimeter setting window. The altimeter indication should then be compared with the known airport elevation of 487 feet. Since most altimeters are not perfectly calibrated, an error may exist. When over mineral wells, assume the pilot receives a current altimeter setting of 29.94 inches of mercury and sets this in the altimeter window. Before entering the traffic pattern at Abilene Municipal Airport, a new altimeter setting of 29.69 inches of mercury is received from the Abilene Control Tower and set in the altimeter setting window. If the pilot desires to fly the traffic pattern at approximately 800 feet above the terrain, and the field elevation of Abilene is 1,791 feet, an indicated altitude of 2,600 feet should be maintained. 1,791 feet plus 800 feet equals 2,591 feet, rounded to 2,600 feet. The importance of properly setting the altimeter cannot be overemphasized. Assume the pilot did not adjust the altimeter at Abilene to the current setting and continued using the mineral well setting of 29.94 inches of mercury. When entering the Abilene traffic pattern at an indicated altitude of 2,600 feet, the aircraft would be approximately 250 feet below the proper traffic pattern altitude. Upon landing, the altimeter would indicate approximately 250 feet higher than the field elevation. Mineral wells altimeter setting, 29.94. Abilene altimeter setting, 29.69. Difference, 0.25. Since 1 inch of pressure is equal to approximately 1,000 feet of altitude, 0.25 times 1,000 feet equals 250 feet. When determining whether to add or subtract the amount of altimeter error, remember that when the actual pressure is lower than what is set in the altimeter window, the actual altitude of the aircraft is lower than what is indicated on the altimeter. The following is another method of computing the altitude deviation. Start by subtracting the current altimeter setting from 29.94 inches of mercury. Always remember to place the original setting as the top number. Then subtract the current altimeter setting. Mineral wells altimeter setting, 29.94. Abilene altimeter setting, 29.69. 29.94 minus 29.69 equals difference, 0.25. Since 1 inch of pressure is equal to approximately 1,000 feet of altitude, 0.25 times 1,000 feet equals 250 feet. Always subtract the number from the indicated altitude. 2,600 minus 250 equals 2,350. Now, try a lower pressure setting. Adjust from altimeter setting 29.94 to 30.56 inches of mercury. Mineral wells altimeter setting, 29.94. Altimeter setting, 30.56. 29.94 minus 30.56 equals difference, negative 0.62. Since 1 inch of pressure is equal to approximately 1,000 feet of altitude, 0.62 times 1,000 feet equals 620 feet. Always subtract the number from the indicated altitude. 2,600 minus negative 620 equals 3,220. The pilot will be 620 feet high. Notice the difference is a negative number. Starting with the current indicated altitude of 2,600 feet, subtracting a negative number is the same as adding the two numbers. By utilizing this method, a pilot should be able to better understand what is happening with the aircraft's altitude. This method always yields the correct result and tells a pilot what the altitude is and the direction. The implications of not understanding where the errors lie and in what direction are important to a safe flight. If the altitude was lower than actually indicated, an aircraft could be in danger of colliding with an obstacle. Altimeter operation. There are two means by which the altimeter pointers can be moved. The first is a change in air pressure, while the other is an adjustment to the barometric scale. When the aircraft climbs or descends, changing pressure within the altimeter case expands or contracts the aneroid barometer. This movement is transmitted through mechanical linkage to rotate the pointers. A decrease in pressure causes the altimeter to indicate an increase in altitude, and an increase in pressure causes the altimeter to indicate a decrease in altitude. Accordingly, if the aircraft is sitting on the ground with a pressure level of 29.98 inches of mercury, and the pressure level changes to 29.68 inches of mercury, the altimeter would show an increase of approximately 300 feet in altitude. This pressure change is most noticeable when the aircraft is left parked overnight. As the pressure falls, the altimeter interprets this as a climb. The altimeter indicates an altitude above the actual field elevation. If the barometric pressure setting is reset to the current altimeter setting of 29.68 inches of mercury, then the field elevation is again indicated on the altimeter. This pressure change is not as easily noticed in flight, since aircraft fly specific altitudes. The aircraft steadily decreases true altitude, while the altimeter is held constant through pilot action as discussed in the previous section. Knowing the aircraft's altitude is vitally important to a pilot. The pilot must be sure that the aircraft is flying high enough to clear the highest terrain or obstruction along the intended route. It is especially important to have accurate altitude information when visibility is restricted. To clear obstructions, the pilot must constantly be aware of the altitude of the aircraft and the elevation of the surrounding terrain. To reduce the possibility of a mid-air collision, it is essential to maintain altitude in accordance with air traffic rules. Types of altitude. Altitude in itself is a relevant term only when it is specifically stated to which type of altitude a pilot is referring. Normally, when the term altitude is used, it is referring to altitude above sea level, since this is the altitude which is used to depict obstacles and airspace, as well as to separate air traffic. Altitude is vertical distance above some point or level used as a reference. There are as many kinds of altitude as there are reference levels from which altitude is measured, and each may be used for specific reasons. Pilots are mainly concerned with 5 types of altitudes. 1. Indicated altitude. Read directly from the altimeter, uncorrected, when it is set to the current altimeter setting. 2. True altitude. The vertical distance of the aircraft above sea level, the actual altitude. It is often expressed as feet above mean sea level, MSL. Airport, terrain, and obstacle elevations on aeronautical charts are true altitudes. 3. Absolute altitude. The vertical distance of an aircraft above the terrain, or above ground level, AGL. 4. Pressure altitude. The altitude indicated when the altimeter setting window, barometric scale, is adjusted to 29.92 inches of mercury. This is the altitude above the standard datum plane, which is a theoretical plane where air pressure, corrected to 15 degrees Celsius, equals 29.92 inches of mercury. Pressure altitude is used to compute density altitude, true airspeed, TAS, and other performance data. 5. Density altitude. Pressure altitude corrected for variations from standard temperature. When conditions are standard, pressure altitude and density altitude are the same. If the temperature is above standard, the density altitude is higher than pressure altitude. If the temperature is below standard, the density altitude is lower than pressure altitude. This is an important altitude because it is directly related to the aircraft's performance. A pilot must understand how the performance of the aircraft is directly related to the density of the air. The density of the air affects how much power a naturally aspirated engine produces, as well as how efficient the airfoils are. If there are fewer air molecules, lower pressure, to accelerate through the propeller, the acceleration to rotation speed is longer, and thus produces a longer takeoff roll, which translates to a decrease in performance. As an example, consider an airport with a field elevation of 5,048 feet MSL, where the standard temperature is 5 degrees Celsius. Under these conditions, pressure altitude and density altitude are the same, 5,048 feet. If the temperature changes to 30 degrees Celsius, the density altitude increases to 7,855 feet. This means an aircraft would perform on takeoff as though the field elevation were 7,855 feet at standard temperature. Conversely, a temperature of negative 25 degrees Celsius would result in a density altitude of 1,232 feet. An aircraft would perform much better under these conditions. Instrument check. Prior to each flight, a pilot should examine the altimeter for proper indications in order to verify its validity. To determine the condition of an altimeter, set the barometric scale to the current reported altimeter setting transmitted by the local automated flight service station, AFSS, or any other reliable source, such as ATIS, AWOS, or ASOS. The altimeter pointer should indicate the surveyed field elevation of the airport. If the indication is off more than 75 feet from the surveyed field elevation, the instrument should be referred to a certificated instrument repair station for recalibration. End of Chapter 7, Part 1. Part 2 of Chapter 7 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 7, Part 2. Vertical Speed Indicator, VSI. The VSI, which is sometimes called a vertical velocity indicator, VVI, indicates whether the aircraft is climbing, descending, or in level flight. The rate of climb or descent is indicated in feet per minute, FPM. If properly calibrated, the VSI indicates 0 in level flight. Figure 7-5. Principle of operation. Although the VSI operates solely from static pressure, it is a differential pressure instrument. It contains a diaphragm with connecting linkage and gearing to the indicator pointer inside an airtight case. The inside of the diaphragm is connected directly to the static line of the pitot static system. The area outside the diaphragm, which is inside the instrument case, is also connected to the static line, but through a restricted orifice, calibrated leak. Both the diaphragm and the case receive air from the static line at existing atmospheric pressure. The diaphragm receives unrestricted air while the case receives the static pressure via the metered leak. When the aircraft is on the ground, or in level flight, the pressures inside the diaphragm and the instrument case are equal, and the pointer is at the 0 indication. When the aircraft climbs or descends, the pressure inside the diaphragm changes immediately, but due to the metering action of the restricted passage, the case pressure remains higher or lower for a short time, causing the diaphragm to contract or expand. This causes a pressure differential that is indicated on the instrument needle as a climb or descent. When the pressure differential stabilizes at a definite ratio, the needle indicates the rate of altitude change. The VSI displays two different types of information. Trend information shows an immediate indication of an increase or decrease in the aircraft's rate of climb or descent. Rate information shows a stabilized rate of change in altitude. The trend information is the direction of movement of the VSI needle. For example, if an aircraft is maintaining level flight and the pilot pulls back on the control yoke, causing the nose of the aircraft to pitch up, the VSI needle moves upward to indicate a climb. If the pitch attitude is held constant, the needle stabilizes after a short period, 6 to 9 seconds, and indicates the rate of climb in hundreds of FPM. The time period from the initial change in the rate of climb until the VSI displays an accurate indication of the new rate is called the lag. Rough control technique and turbulence can extend the lag period and cause erratic and unstable rate indications. Some aircraft are equipped with an instantaneous vertical speed indicator, IVSI, which incorporates accelerometers to compensate for the lag in the typical VSI. Figure 7-6. Instrument check. As part of a pre-flight check, proper operation of the VSI must be established. Make sure the VSI indicates near 0 prior to leaving the ramp area, and again just before takeoff. If the VSI indicates anything other than 0, that indication can be referenced as the 0 mark. Normally, if the needle is not exactly 0, it is only slightly above or below the 0 line. After takeoff, the VSI should trend upward to indicate a positive rate of climb, and then, once a stabilized climb is established, a rate of climb can be referenced. Airspeed indicator, ASI. The ASI is a sensitive differential pressure gauge, which measures and promptly indicates the difference between pitot, impact/dynamic pressure, and static pressure. These two pressures are equal when the aircraft is parked on the ground in calm air. When the aircraft moves through the air, the pressure on the pitot line becomes greater than the pressure in the static lines. This difference in pressure is registered by the airspeed pointer on the face of the instrument, which is calibrated in miles per hour, knots, nautical miles per hour, or both. Figure 7-7. The ASI is the one instrument that utilizes both the pitot as well as the static system. the ASI introduces the static pressure into the airspeed case, while the pitot pressure, dynamic, is introduced into the diaphragm. The dynamic pressure expands or contracts one side of the diaphragm, which is attached to an indicating system. The system drives the mechanical linkage in the airspeed needle. Just as in altitudes, there are multiple types of airspeeds. Pilots need to be very familiar with each type. Indicated airspeed, IAS. The direct instrument reading obtained from the ASI, uncorrected for variations in atmospheric density, installation error, or instrument error. Manufacturers use this airspeed as the basis for determining aircraft performance. Takeoff, landing, and stall speeds listed in the AFM/POH are IAS and do not normally vary with altitude or temperature. Calibrated airspeed, CAS. IAS corrected for installation error and instrument error. Although manufacturers attempt to keep airspeed errors to a minimum, it is not possible to eliminate all errors throughout the airspeed operating range. At certain airspeeds, and with certain flap settings, the installation and instrument errors may total several knots. This error is generally greatest at low airspeeds. In the cruising and higher airspeed ranges, IAS and CAS are approximately the same. Refer to the airspeed calibration chart to correct for possible airspeed errors. True airspeed, TAS. CAS corrected for altitude and non-standard temperature. Because air density decreases with an increase in altitude, an aircraft has to be flown faster at higher altitudes to cause the same pressure difference between pitot impact pressure and static pressure. Therefore, for a given CAS, TAS increases as altitude increases, or for a given TAS, CAS decreases as altitude increases. A pilot can find TAS by two methods. The most accurate method is to use a flight computer. With this method, the CAS is corrected for temperature and pressure variation by using the airspeed correction scale on the computer. Extremely accurate electronic flight computers are also available. Just enter the CAS, pressure altitude, and temperature, and the computer calculates the TAS. A second method, which is a rule of thumb, provides the approximate TAS. Simply add 2% to the CAS for each 1,000 feet of altitude. The TAS is the speed which is used for flight planning and is used when filing a flight plan. Ground speed, GS. The actual speed of the airplane over the ground. It is TAS adjusted for wind. GS decreases with a headwind and increases with a tailwind. Airspeed indicator markings. Aircraft weighing 12,500 pounds or less, manufactured after 1945, and certificated by the FAA, are required to have ASIs marked in accordance with the standard color-coded marking system. This system of color-coded markings enables a pilot to determine at a glance certain airspeed limitations that are important to the safe operation of the aircraft. For example, if during the execution of a maneuver, it is noted that the airspeed needle is in the yellow arc and rapidly approaching the red line, the immediate reaction should be to reduce airspeed. As shown in Figure 7-8, ASIs on single-engine small aircraft include the following standard color-coded markings. White arc, commonly referred to as the flap operating range, since its lower limit represents the full flap stall speed, and its upper limit provides the maximum flap speed. Approaches and landings are usually flown at speeds within the white arc. Lower limit of white arc, VS0. The stalling speed or the minimum steady flight speed in the landing configuration. In small aircraft, this is the power-off stall speed at the maximum landing weight in the landing configuration, gear and flaps down. Upper limit of the white arc, VFE. The maximum speed with the flaps extended. Green arc. The normal operating range of the aircraft. Most flying occurs within this range. Lower limit of green arc, VS1. The stalling speed or the minimum steady flight speed obtained in a specified configuration. For most aircraft, this is the power-off stall speed at the maximum takeoff weight in the clean configuration, gear up if retractable, and flaps up. Upper limit of green arc, VNO. The maximum structural cruising speed. Do not exceed this speed except in smooth air. Yellow arc, caution range. Fly within this range only in smooth air, and then only with caution. Red line, VNE. Never exceed speed. Operating above this speed is prohibited, since it may result in damage or structural failure. Other airspeed limitations. Some important airspeed limitations are not marked on the face of the ASI, but are found on placards and in the AFM/POH. These airspeeds include Design Maneuvering Speed, VA. The maximum speed at which the structural design's limit load can be imposed, either by gusts or full deflection of the control surfaces, without causing structural damage. It is important to consider weight when referencing this speed. For example, VA may be 100 knots when an airplane is heavily loaded, but only 90 knots when the load is light. Landing Gear Operating Speed, VLO. The maximum speed for extending or retracting the landing gear, if flying an aircraft with retractable landing gear. Landing Gear Extended Speed, VLE. The maximum speed at which an aircraft can be safely flown with the landing gear extended. Best Angle of Climb Speed, VX. The airspeed at which an aircraft gains the greatest amount of altitude in a given distance. It is used during a short field takeoff to clear an obstacle. Best Rate of Climb Speed, VY. The airspeed that provides the most altitude gain in a given period of time. Single Engine Best Rate of Climb, VYSE. The best rate of climb, or minimum rate of sink, in a light twin-engine aircraft with one engine inoperative. It is marked on the ASI with a blue line. VYSE is commonly referred to as blue line. Minimum Control Speed, VMC. The minimum flight speed at which a light, twin-engine aircraft can be satisfactorily controlled when an engine suddenly becomes inoperative and the remaining engine is at takeoff power. Instrument check. Prior to takeoff, the ASI should read 0. However, if there is a strong wind blowing directly into the pitot tube, the ASI may read higher than 0. When beginning the takeoff, make sure the airspeed is increasing at an appropriate rate. Blockage of the pitot-static system. Errors almost always indicate blockage of the pitot tube, the static ports, or both. Blockage may be caused by moisture, including ice, dirt, or even insects. During pre-flight, make sure the pitot tube cover is removed. Then, check the pitot and static port openings. A blocked pitot tube affects the accuracy of the ASI, but a blockage of the static port not only affects the ASI, but also causes errors in the altimeter and VSI. Blocked pitot system. The pitot system can become blocked completely or only partially if the pitot tube drain hole remains open. If the pitot tube becomes blocked and its associated drain hole remains clear, ram air no longer is able to enter the pitot system. Air already in the system vents through the drain hole, and the remaining pressure drops to ambient, outside, air pressure. Under these circumstances, the ASI reading decreases to 0, because the ASI senses no difference between ram and static air pressure. The ASI no longer operates since dynamic pressure cannot enter the pitot tube opening. Static pressure is able to equalize on both sides since the pitot drain hole is still open. The apparent loss of airspeed is not usually instantaneous, but happens very quickly. Figure 7-9. If both the pitot tube opening and the drain hole should become clogged simultaneously, then the pressure in the pitot tube is trapped. No change is noted on the airspeed indication should the airspeed increase or decrease. If the static port is unblocked and the aircraft should change altitude, then a change is noted on the ASI. The change is not related to a change in airspeed, but a change in static pressure. The total pressure in the pitot tube does not change due to the blockage. However, the static pressure will change. Because airspeed indications rely upon both static and dynamic pressure together, the blockage of either of these systems affects the ASI reading. Remember that the ASI has a diaphragm in which dynamic air pressure is entered. Behind this diaphragm is a reference pressure called static pressure that comes from the static ports. The diaphragm pressurizes against this static pressure, and as a result, changes the airspeed indication via levers and indicators. Figure 7-10. For example, take an aircraft and slow it down to 0 knots at given altitude. If the static port, providing static pressure, and the pitot tube, providing dynamic pressure, are both unobstructed, the following claims can be made. 1. The ASI would be 0. 2. There must be a relationship between both dynamic and static pressure. At 0 speed, dynamic pressure and static pressure are the same, static air pressure. 3. Because both dynamic and static air pressure are equal at 0 speed with increased speed, dynamic pressure must include two components, static pressure and dynamic pressure. It can be inferred that airspeed indication must be based upon a relationship between these two pressures, and indeed it is. An ASI uses the static pressure as a reference pressure, and as a result, the ASI's case is kept at this pressure behind the diaphragm. On the other hand, the dynamic pressure through the pitot tube is connected to a highly sensitive diaphragm within the ASI case. Because an aircraft in 0 motion, regardless of altitude, results in a 0 airspeed, the pitot tube always provides static pressure in addition to dynamic pressure. Therefore, the airspeed indication is the result of two pressures, the pitot tube static and dynamic pressure within the diaphragm, as measured against the static pressure in case. What does this mean if the pitot tube is obstructed? If the aircraft were to descend, the pressure in the pitot system, including the diaphragm, would remain constant. It is clogged, and the diaphragm is at a single pressure. But as the descent is made, the static pressure would increase against the diaphragm, causing it to compress, thereby resulting in an indication of decreased airspeed. Conversely, if the aircraft were to climb, the static pressure would decrease, allowing the diaphragm to expand, thereby showing an indication of greater airspeed. Figure 7-10. The pitot tube may become blocked during flight due to visible moisture. Some aircraft may be equipped with pitot heat for flight in visible moisture. Consult the AFM/POH for specific procedures regarding the use of pitot heat. Blocked static system. If the static system becomes blocked but the pitot tube remains clear, the ASI continues to operate. However, it is inaccurate. The airspeed indicates lower than the actual airspeed when the aircraft is operated above the altitude where the static ports became blocked, because the trapped static pressure is higher than normal for that altitude. When operating at a lower altitude, a faster than actual airspeed is displayed due to the relatively low static pressure trapped in the system. Revisiting the ratios that were used to explain a blocked pitot tube, the same principle applies for a blocked static port. If the aircraft descends, the static pressure increases on the pitot side, showing an increase on the ASI. This assumes that the aircraft does not actually increase its speed. The increase in static pressure on the pitot side is equivalent to an increase in dynamic pressure, since the pressure cannot change on the static side. If an aircraft begins to climb after a static port becomes blocked, the airspeed begins to show a decrease as the aircraft continues to climb. This is due to the decrease in static pressure on the pitot side, while the pressure on the static side is held constant. A blockage of the static system also affects the altimeter and VSI. Trapped static pressure causes the altimeter to freeze at the altitude where the blockage occurred. In the case of the VSI, a blocked static system produces a continuous zero indication. Figure 7-11. Some aircraft are equipped with an alternate static source in the flight deck. In the case of a blocked static source, opening the alternate static source introduces static pressure from the flight deck back into the system. Flight deck static pressure is lower than outside static pressure. Check the aircraft AOM/POH for airspeed corrections when utilizing alternate static pressure. End of Part 2 of Chapter 7. Part 3 of Chapter 7 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 7, Part 3. Electronic Flight Display, EFD. Advances in digital displays and solid-state electronic components have been introduced into the flight decks of general aviation (GA) aircraft. In addition to the improvement in system reliability, which increases overall safety, electronic flight displays (EFD) have decreased the overall cost of equipping aircraft with state-of-the-art instrumentation. Primary electronic instrumentation packages are less prone to failure than their analog counterparts. No longer is it necessary for aircraft designers to create cluttered panel layouts in order to accommodate all necessary flight instruments. Instead, multi-panel digital flight displays combine all flight instruments onto a single screen, which is called a primary flight display, PFD. The traditional six-pack of instruments is now displayed on one liquid crystal display, LCD, screen. Airspeed tape. Configured similarly to traditional panel layouts, the ASI is located on the left side of the screen and is displayed as a vertical speed tape. As the aircraft increases in speed, the larger numbers descend from the top of the tape. The TAS is displayed at the bottom of the tape through the input to the Air Data Computer, ADC, from the outside air temperature probe. Airspeed markings for Vx, Vy, and rotation speed, VR, are displayed for pilot reference. An additional pilot-controlled airspeed bug is available to set at any desired reference speed. As on traditional analog ASIs, the electronic airspeed tape displays the color-coded ranges for the flap operating range, normal range, and caution range. Figure 7-12. The number value changes color to red when the airspeed exceeds VNE, to warn the pilot of exceeding the maximum speed limitation. Attitude indicator. One improvement over analog instrumentation is the larger attitude indicator on EFD. The artificial horizon spans the entire width of the PFD, figure 7-12. This expanded instrumentation offers better reference through all phases of flight and all flight maneuvers. The attitude indicator receives its information from the Attitude Heading and Reference System, AHRS. Altimeter. The altimeter is located on the right side of the PFD, figure 7-12. As the altitude increases, the larger numbers descend from the top of the display tape, with the current altitude being displayed in the black box in the center of the display tape. The altitude is displayed in increments of 20 feet. Vertical Speed Indicator, VSI. The VSI is displayed to the right of the altimeter tape and can take the form of an arced indicator or a vertical speed tape. Figure 7-12. Both are equipped with a vertical speed bug. Heading indicator. The heading indicator is located below the artificial horizon and is normally modeled after a horizontal situation indicator, HSI, figure 7-12. As in the case of the attitude indicator, the heading indicator receives its information from the magnetometer, which feeds information to the AHRS unit, and then out to the PFD. Turn indicator. The turn indicator takes a slightly different form than the traditional instrumentation. A sliding bar moves left and right below the triangle to indicate deflection from coordinated flight. Figure 7-12 and errata. Reference for coordinated flight comes from accelerometers contained in the AHRS unit. Tachometer. The sixth instrument normally associated with the 6-pack package is the tachometer. This is the only instrument that is not located on the PFD. The tachometer is normally located on the multifunction display, MFD. In the event of a display screen failure, it is displayed on the remaining screen with the PFD flight instrumentation. Figure 7-13. Slip skid indicator. The slip skid indicator, figure 7-12, is the horizontal line below the roll pointer. Like a ball in a turn and slip indicator, a bar width off center is equal to 1 ball width displacement. Turn rate indicator. The turn rate indicator, illustrated in figure 7-12, is typically found directly above the rotating compass card. Tick marks to the left and right of the lubber line denote the turn, standard rate versus half standard rate, typically denoted by a trend line. If the trend vector is extended to the second tick mark, the aircraft is in a standard rate turn. Individual panel displays are able to be configured for a variety of aircraft simply by installing different software packages. Figure 7-14. Manufacturers are also able to upgrade existing instrument displays in a similar manner, eliminating the need to replace individual gauges in order to upgrade. Air Data Computer, ADC. Electronic flight displays utilize the same type of instrument inputs as traditional analog gauges. However, the processing system is different. The pitot-static inputs are received by an ADC. The ADC computes the difference between the total pressure and the static pressure, and generates the information necessary to display the airspeed on the PFD. Outside air temperatures are also monitored and introduced into various components within the system, as well as being displayed on the PFD screen. Figure 7-15. The ADC is a separate solid-state device which, in addition to providing data to the PFD, is capable of providing data to the autopilot control system. In the event of system malfunction, the ADC can quickly be removed and replaced in order to decrease downtime and maintenance turnaround times. Altitude information is derived from the static pressure port, just as an analog system does. However, the static pressure does not enter a diaphragm. The ADC computes the received barometric pressure and sends a digital signal to the PFD to display the proper altitude readout. Electronic flight displays also show trend vectors, which show the pilot how the altitude and airspeed are progressing. Trend vectors. Trend vectors are magenta lines which move up and down both the ASI and the altimeter. Figures 7-16 and 7-17. Errata. Refer to the Instrument Flying Handbook. The ADC computes the rate of change and displays the 6-second projection of where the aircraft will be. Pilots can utilize the trend vectors to better control the aircraft's attitude. By including the trend vectors in the instrument scan, pilots are able to precisely control airspeed and altitude. Additional information can be obtained by referencing the Instrument Flying Handbook or specific avionics manufacturer's training material. Gyroscopic flight instruments. Several flight instruments utilize the properties of a gyroscope for their operation. The most common instruments containing gyroscopes are the turn coordinator, heading indicator, and the attitude indicator. To understand how these instruments operate requires knowledge of the instrument power systems, gyroscopic principles, and the operating principles of each instrument. Gyroscopic principles. Any spinning object exhibits gyroscopic properties. A wheel or rotor designed and mounted to utilize these properties is called a gyroscope. Two important design characteristics of an instrument gyro are great weight for its size, or high density, and rotation at high speed with low friction bearings. There are two general types of mountings. The type used depends upon which property of the gyro is utilized. A freely or universally mounted gyroscope is free to rotate in any direction about its center of gravity. Such a wheel is said to have 3 planes of freedom. The wheel or rotor is free to rotate in any plane in relation to the base, and is balanced so that, with the gyro wheel at rest, it remains in the position in which it is placed. Restricted or semi-rigidly mounted gyroscopes are those mounted so that one of the planes of freedom is held fixed in relation to the base. There are 2 fundamental properties of gyroscopic action: rigidity in space and precession. Rigidity in space. Rigidity in space refers to the principle that a gyroscope remains in a fixed position in the plane in which it is spinning. An example of rigidity in space is that of a bicycle wheel. As the bicycle wheels increase speed, they become more and more stable in their plane of rotation. This is why a bicycle is very unstable and very maneuverable at low speeds, and very stable and less maneuverable at higher speeds. By mounting this wheel, or gyroscope, on a set of gimbal rings, the gyro is able to rotate freely in any direction. Thus, if the gimbal rings are tilted, twisted, or otherwise moved, the gyro remains in the plane in which it was originally spinning. Figure 7-18. Precession. Precession is the tilting or turning of a gyro in response to a deflective force. The reaction to this force does not occur at the point at which it was applied. Rather, it occurs at a point that is 90 degrees later in the direction of rotation. This principle allows the gyro to determine a rate of turn by sensing the amount of pressure created by a change in direction. The rate at which the gyro precesses is inversely proportional to the speed of the rotor and proportional to the deflective force. Using the example of the bicycle, precession acts on the wheels in order to allow the bicycle to turn. While riding at normal speed, it is not necessary to turn the handlebars in the direction of the desired turn. A rider simply leans in the direction that he or she wishes to go. Since the wheels are rotating in a clockwise direction when viewed from the right side of the bicycle, if a rider leans to the left, a force is applied to the top of the wheel to the left. The force actually acts 90 degrees in the direction of rotation, which has the effect of applying a force to the front of the tire, causing the bicycle to move to the left. There is a need to turn the handlebars at low speeds because of the instability of the slowly turning gyros, and also to increase the rate of turn. Precession can also create some minor errors in some instruments. Figure 7-19. Precession can cause a freely spinning gyro to become displaced from its intended plane of rotation through bearing friction, etc. Certain instruments may require corrective realignment during flight, such as the heading indicator. Sources of power. In some aircraft, all the gyros are vacuum, pressure, or electrically operated. In other aircraft, vacuum or pressure systems provide the power for the heading and attitude indicators, while the electrical system provides the power for the turn coordinator. Most aircraft have at least two sources of power to ensure at least one source of bank information is available if one power source fails. The vacuum or pressure system spins the gyro by drawing a stream of air against the rotor vanes to spin the rotor at high speed, much like the operation of a water wheel or turbine. The amount of vacuum or pressure required for instrument operation varies, but is usually between 4.5 inches of mercury and 5.5 inches of mercury. One source of vacuum for the gyros is a vane-type engine-driven pump that is mounted on the accessory case of the engine. Pump capacity varies in different airplanes, depending on the number of gyros. A typical vacuum system consists of an engine-driven vacuum pump, relief valve, air filter, gauge, and tubing necessary to complete the connections. The gauge is mounted in the aircraft's instrument panel and indicates the amount of pressure in the system. Vacuum is measured in inches of mercury less than ambient pressure. As shown in Figure 7-20, air is drawn into the vacuum system by the engine-driven vacuum pump. It first goes through a filter, which prevents foreign matter from entering the vacuum or pressure system. The air then moves through the attitude and heading indicators, where it causes the gyros to spin. A relief valve prevents the vacuum pressure, or suction, from exceeding prescribed limits. After that, The air is expelled overboard or used in other systems, such as for inflating pneumatic de-icing boots. It is important to monitor vacuum pressure during flight, because the attitude and heading indicators may not provide reliable information when suction pressure is low. The vacuum or suction gauge is generally marked to indicate the normal range. Some aircraft are equipped with a warning light that illuminates when the vacuum pressure drops below the acceptable level. When the vacuum pressure drops below the normal operating range, the gyroscopic instruments may become unstable and inaccurate. Cross-checking the instruments routinely is a good habit to develop. Turn indicators. Aircraft use two types of turn indicators: turn and slip indicator and turn coordinator. Because of the way the gyro is mounted, the turn and slip indicator shows only the rate of turn in degrees per second. The turn coordinator is mounted at an angle, or canted, so it can initially show roll rate. When the roll stabilizes, it indicates rate of turn. Both instruments indicate turn direction and quality, coordination, and also serve as a backup source of bank information in the event an attitude indicator fails. Coordination is achieved by referring to the inclinometer, which consists of a liquid-filled curved tube with a ball inside. Figure 7-21. Turn and slip indicator. The gyro in the turn and slip indicator rotates in the vertical plane, corresponding to the aircraft's longitudinal axis. A single gimbal limits the planes in which the gyro can tilt, and a spring tries to return it to center. Because of precession, a yawing force causes the gyro to tilt left or right, as viewed from the pilot seat. The turn and slip indicator uses a pointer, called the turn needle, to show the direction and rate of turn. The turn and slip indicator is incapable of tumbling off its rotational axis because of the restraining springs. When extreme forces are applied to a gyro, the gyro is displaced from its normal plane of rotation, rendering its indications invalid. Certain instruments have specific pitch and bank limits that induce a tumble of the gyro. Turn coordinator. The gimbal in the turn coordinator is canted. Therefore, its gyro can sense both rate of roll and rate of turn. Since turn coordinators are more prevalent in training aircraft, this discussion concentrates on that instrument. When rolling into or out of a turn, the miniature aircraft banks in the direction the aircraft is rolled. A rapid roll rate causes the miniature aircraft to bank more steeply than a slow roll rate. The turn coordinator can be used to establish and maintain a standard rate turn by aligning the wing of the miniature aircraft with the turn index. Figure 7-22 shows a picture of a turn coordinator. There are two marks on each side, left and right, of the face of the instrument. The first mark is used to reference a wing's level 0 rate of turn. The second mark, on the left and right side of the instrument, serve to indicate a standard rate of turn. A standard rate turn is defined as a turn rate of 3 degrees per second. The turn coordinator indicates only the rate and direction of turn. It does not display a specific angle of bank. End of Chapter 7, Part 3. Part 4 of Chapter 7 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 7, Part 4. Inclinometer. The inclinometer is used to depict aircraft yaw, which is the side-to-side movement of the aircraft's nose. During coordinated straight and level flight, the force of gravity causes the ball to rest in the lowest part of the tube, centered between the reference lines. Coordinated flight is maintained by keeping the ball centered. If the ball is not centered, it can be centered by using the rudder. To center the ball, apply rudder pressure on the side to which the ball is deflected. Use the simple rule, step on the ball, to remember which rudder pedal to press. If aileron and rudder are coordinated during a turn, the ball remains centered in the tube. If aerodynamic forces are unbalanced, the ball moves away from the center of the tube. As shown in Figure 7-22, in a slip, the rate of turn is too slow for the angle of bank, and the ball moves to the inside of the turn. In a skid, the rate of turn is too great for the angle of bank, and the ball moves to the outside of the turn. To correct for these conditions and improve the quality of the turn, remember to step on the ball. Varying the angle of bank can also help restore coordinated flight from a slip or skid. To correct for a slip, decrease bank and/or increase the rate of turn. To correct for a skid, increase the bank and/or decrease the rate of turn. Yaw string. One additional tool which can be added to the aircraft is a yaw string. A yaw string is simply a string or piece of yarn attached to the center of the windscreen. When in coordinated flight, the string trails straight back over the top of the windscreen. When the aircraft is either slipping or skidding, the yaw string moves to the right or left depending on the direction of slip or skid. Instrument check. During the pre-flight, check to see that the inclinometer is full of fluid and has no air bubbles. The ball should also be resting at its lowest point. When taxiing, the turn coordinator should indicate a turn in the correct direction, while the ball moves opposite the direction of the turn. Attitude indicator. The attitude indicator, with its miniature aircraft and horizon bar, displays a picture of the attitude of the aircraft. The relationship of the miniature aircraft to the horizon bar is the same as the relationship of the real aircraft to the actual horizon. The instrument gives an instantaneous indication of even the smallest changes in attitude. The gyro in the attitude indicator is mounted in a horizontal plane and depends upon rigidity and space for its operation. The horizon bar represents the true horizon. This bar is fixed to the gyro and remains in a horizontal plane, as the aircraft is pitched or banked about its lateral or longitudinal axis, indicating the attitude of the aircraft relative to the true horizon. Figure 7-23. The gyro spins in the horizontal plane and resists deflection of the rotational path. Since the gyro relies on rigidity in space, the aircraft actually rotates around the spinning gyro. An adjustment knob is provided with which the pilot may move the miniature aircraft up or down to align the miniature aircraft with the horizon bar to suit the pilot's line of vision. Normally, the miniature aircraft is adjusted so that the wings overlap the horizon bar when the aircraft is in straight and level cruising flight. The pitch and bank limits depend upon the make and model of the instrument. Limits in the banking plane are usually from 100 degrees to 110 degrees, and the pitch limits are usually from 60 degrees to 70 degrees. If either limit is exceeded, the instrument will tumble or spill, and will give incorrect indications until realigned. A number of modern attitude indicators do not tumble. Every pilot should be able to interpret the banking scale illustrated in Figure 7-24. Most banking scale indicators on the top of the instrument move in the same direction from that in which the aircraft is actually banked. Some other models move in the opposite direction from that in which the aircraft is actually banked. This may confuse the pilot if the indicator is used to determine the direction of bank. This scale should be used only to control the degree of desired bank. The relationship of the miniature aircraft to the horizon bar should be used for an indication of the direction of bank. The attitude indicator is reliable and the most realistic flight instrument on the instrument panel. Its indications are very close approximations of the actual attitude of the aircraft. Heading indicator. The heading indicator is fundamentally a mechanical instrument designed to facilitate the use of the magnetic compass. Errors in the magnetic compass are numerous, making straight flight and precision turns to headings difficult to accomplish, particularly in turbulent air. A heading indicator, however, is not affected by the forces that make the magnetic compass difficult to interpret. Figure 7-25. The operation of the heading indicator depends upon the principle of rigidity in space. The rotor turns in a vertical plane, and fixed to the rotor is a compass card. Since the rotor remains rigid in space, the points on the card hold the same position in space relative to the vertical plane of the gyro. The aircraft actually rotates around the rotating gyro, not the other way around. As the instrument case and the aircraft revolve around the vertical axis of the gyro, the card provides clear and accurate heading information. Because of precession caused by friction, the heading indicator creeps or drifts from a heading to which it is set. Among other factors, the amount of drift depends largely upon the condition of the instrument. If the bearings are worn, dirty, or improperly lubricated, the drift may be excessive. Another error in the heading indicator is caused by the fact that the gyro is oriented in space, and the Earth rotates in space at a rate of 15 degrees in 1 hour. Thus, discounting precession caused by friction, the heading indicator may indicate as much as 15 degrees error per every hour of operation. Some heading indicators, referred to as horizontal situation indicators, HSI, receive a magnetic north reference from a magnetic slaving transmitter and generally need no adjustment. The magnetic slaving transmitter is called a magnetometer. Attitude and Heading Reference System, AHRS. Electronic flight displays have replaced free-spinning gyros with solid-state laser systems that are capable of flight at any attitude without tumbling. This capability is the result of the development of the Attitude and Heading Reference System, AHRS. The AHRS sends attitude information to the PFD in order to generate the pitch and bank information of the attitude indicator. The heading information is derived from a magnetometer, which senses the Earth's lines of magnetic flux. This information is then processed and sent out to the PFD to generate the heading display. Figure 7-26. The Flux Gate Compass System. As mentioned earlier, the lines of flux in the Earth's magnetic field have two basic characteristics. A magnet aligns with them, and an electrical current is induced or generated in any wire crossed by them. The flux gate compass that drives slaved gyros uses the characteristic of current induction. The flux valve is a small segmented ring, like the one in Figure 7-27, made of soft iron that readily accepts lines of magnetic flux. An electrical coil is wound around each of the 3 legs to accept the current induced in this ring by the Earth's magnetic field. A coil wound around the iron spacer in the center of the frame has 400 Hz alternating current, AC, flowing through it. During the times when this current reaches its peak, twice during each cycle, there is so much magnetism produced by this coil that the frame cannot accept the lines of flux from the Earth's field. As the current reverses between the peaks, it demagnetizes the frame so it can accept the flux from the Earth's field. As this flux cuts across the windings in the 3 coils, it causes current to flow in them. These 3 coils are connected in such a way that the current flowing in them changes as the heading of the aircraft changes. Figure 7-28. The 3 coils are connected to 3 similar but smaller coils in a synchro inside the instrument case. The synchro rotates the dial of a radio magnetic indicator, RMI, or an HSI. Remote indicating compass. Remote indicating compasses were developed to compensate for the errors and limitations of the older type of heading indicators. The 2 panel-mounted components of a typical system are the pictorial navigation indicator and the slaving control and compensator unit. Figure 7-29. The pictorial navigation indicator is commonly referred to as an HSI. The slaving control and compensator unit has a push button that provides a means of selecting either the slaved gyro or free gyro mode. This unit also has a slaving meter and 2 manual heading drive buttons. The slaving meter indicates the difference between the displayed heading and the magnetic heading. A right deflection indicates a clockwise error of the compass card. A left deflection indicates a counterclockwise error. Whenever the aircraft is in a turn and the card rotates, the slaving meter shows a full deflection to one side or the other. When the system is in free gyro mode, the compass card may be adjusted by depressing the appropriate heading drive button. A separate unit, the magnetic slaving transmitter, is mounted remotely, usually in a wingtip to eliminate the possibility of magnetic interference. It contains the flux valve, which is the direction sensing device of the system. A concentration of lines of magnetic force, after being amplified, becomes a signal relayed to the heading indicator unit, which is also remotely mounted. This signal operates a torque motor in the heading indicator unit that processes the gyro unit until it is aligned with the transmitter signal. The magnetic slaving transmitter is connected electrically to the HSI. There are a number of designs of the remote indicating compass. Therefore, only the basic features of the system are covered here. Instrument pilots must become familiar with the characteristics of the equipment in their aircraft. As instrument panels become more crowded and the pilot's available scan time is reduced by a heavier flight deck workload, instrument manufacturers have worked toward combining instruments. One good example of this is the RMI in Figure 7-30. The compass card is driven by signals from the flux valve, and the 2 pointers are driven by an automatic direction finder, ADF, and a very high frequency VHF omnidirectional radio range, VOR. Heading indicators that do not have this automatic north-seeking capability are called free gyros and require periodic adjustment. It is important to check the indications frequently, approximately every 15 minutes, and reset the heading indicator to align it with the magnetic compass when required. Adjust the heading indicator to the magnetic compass heading when the aircraft is straight and level at a constant speed to avoid compass errors. The bank and pitch limits of the heading indicator vary with the particular design and make of instrument. On some heading indicators found in light aircraft, the limits are approximately 55 degrees of pitch and 55 degrees of bank. When either of these attitude limits is exceeded, the instrument tumbles or spills and no longer gives the correct indication until reset. After spilling, it may be reset with the caging knob. Many of the modern instruments used are designed in such a manner that they do not tumble. An additional precession error may occur due to a gyro not spinning fast enough to maintain its alignment. When the vacuum system stops producing adequate suction to maintain the gyro speed, the heading indicator and the attitude indicator gyros begin to slow down. As they slow, they become more susceptible to deflection from the plane of rotation. Some aircraft have warning lights to indicate that a low vacuum situation has occurred. Other aircraft may have only a vacuum gauge that indicates the suction. Instrument check. As the gyro spools up, make sure there are no abnormal sounds. While taxiing, the instrument should indicate turns in the correct direction, and precession should not be abnormal. At idle power settings, the gyroscopic instruments using the vacuum system might not be up to operating speeds, and precession might occur more rapidly than during flight. End of Chapter 7, Part 4. Part 5 of Chapter 7 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 7, Part 5. Compass Systems. The Earth is a huge magnet, spinning in space, surrounded by a magnetic field made up of invisible lines of flux. These lines leave the surface at the magnetic North Pole and re-enter at the magnetic South Pole. Lines of magnetic flux have two important characteristics. Any magnet that is free to rotate will align with them, and an electrical current is induced into any conductor that cuts across them. Most direction indicators installed in aircraft make use of one of these two characteristics. Magnetic compass. One of the oldest and simplest instruments for indicating direction is the magnetic compass. It is also one of the basic instruments required by Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, for both VFR and IFR flight. A magnet is a piece of material, usually a metal containing iron, which attracts and holds lines of magnetic flux. Regardless of size, every magnet has two poles, north and south. When one magnet is placed in the field of another, the unlike poles attract each other, and like poles repel. An aircraft magnetic compass, such as the one in Figure 7-31, has two small magnets attached to a metal float sealed inside a bowl of clear compass fluid similar to kerosene. A graduated scale, called a card, is wrapped around the float and viewed through a glass window with a lubber line across it. The card is marked with letters representing the cardinal directions, north, east, south, and west, and a number for each 30 degrees between these letters. The final 0 is omitted from these directions. For example, 3 equals 30 degrees, 6 equals 60 degrees, and 33 equals 330 degrees. There are long and short graduation marks between the letters and numbers, each long mark representing 10 degrees and each short mark representing 5 degrees. The float and card assembly has a hardened steel pivot in its center that rides inside a special, spring-loaded, hard glass jewel cup. The buoyancy of the float takes most of the weight off the pivot, and the fluid damps the oscillation of the float and card. This jewel and pivot type mounting allows the float freedom to rotate and tilt up to approximately 18 degrees angle of bank. At steeper bank angles, the compass indications are erratic and unpredictable. The compass housing is entirely full of compass fluid. To prevent damage or leakage when the fluid expands and contracts with temperature changes, the rear of the compass case is sealed with a flexible diaphragm, or with a metal bellows in some compasses. The magnets align with the Earth's magnetic field, and the pilot reads the direction on the scale opposite the lubber line. Note that in Figure 7-31, the pilot sees the compass card from its backside. When the pilot is flying north, as the compass shows, east is to the pilot's right. On the card, 33, which represents 330 degrees, west of north, is to the right of north. The reason for this apparent backward graduation is that the card remains stationary, and the compass housing and the pilot turn around it, always viewing the card from its backside. A compensator assembly mounted on the top or bottom of the compass allows an aviation maintenance technician, AMT, to create a magnetic field inside the compass housing that cancels the influence of local outside magnetic fields. This is done to correct for deviation error. The compensator assembly has two shafts, whose ends have screwdriver slots accessible from the front of the compass. Each shaft rotates one or two small compensating magnets. The end of one shaft is marked E-W, and its magnets affect the compass when the aircraft is pointed east or west. The other shaft is marked N-S, and its magnets affect the compass when the aircraft is pointed north or south. Magnetic compass-induced errors. The magnetic compass is the simplest instrument in the panel, but it is subject to a number of errors that must be considered. Variation. The Earth rotates about its geographic axis. Maps and charts are drawn using meridians of longitude that pass through the geographic poles. Directions measured from the geographic poles are called true directions. The magnetic North Pole, to which the magnetic compass points, is not co-located with the geographic North Pole, but is some 1,300 miles away. Directions measured from the magnetic poles are called magnetic directions. In aerial navigation, the difference between true and magnetic directions is called variation. This same angular difference in surveying and land navigation is called declination. Figure 7-32 shows the isogonic lines that identify the number of degrees of variation in their area. The line that passes near Chicago is called the agonic line. Anywhere along this line, the two poles are aligned, and there is no variation. East of this line, the magnetic North Pole is to the west of the geographic North Pole, and a correction must be applied to a compass indication to get a true direction. Flying in the Washington, D.C. area, for example, the variation is 10 degrees west. If a pilot wants to fly a true course of south, 180 degrees, the variation must be added to this, resulting in a magnetic course of 190 degrees to fly. Flying in the Los Angeles, California area, the variation is 14 degrees east. To fly a true course of 180 degrees there, the pilot would have to subtract the variation and fly a magnetic course of 166 degrees. The variation error does not change with the heading of the aircraft. It is the same anywhere along the isogonic line. Deviation. The magnets in a compass align with any magnetic field. Local magnetic fields in an aircraft caused by electrical current flowing in the structure, in nearby wiring, or any magnetized part of the structure, conflict with the Earth's magnetic field and cause a compass error called deviation. Deviation, unlike variation, is different on each heading, but it is not affected by the geographic location. Variation error cannot be reduced or changed, but deviation error can be minimized when an AMT performs the maintenance task known as swinging the compass. Most airports have a compass rose, which is a series of lines marked out on a ramp or maintenance run-up area where there is no magnetic interference. Lines, oriented to magnetic north, are painted every 30 degrees, as shown in Figure 7-33. The AMT aligns the aircraft on each magnetic heading and adjusts the compensating magnets to minimize the difference between the compass indication and the actual magnetic heading of the aircraft. Any error that cannot be removed is recorded on a compass correction card, like the one in Figure 7-34, and placed in a card holder near the compass. The pilot can taxi the aircraft to the compass rose and maneuver the aircraft to the headings prescribed by the AMT. And if authorized to do so, the AMT can also taxi and maneuver the aircraft. However, only the AMT can adjust the compass or complete the compass correction card. If the pilot wants to fly a magnetic heading of 120 degrees, and the aircraft is operating with the radios on, the pilot should fly a compass heading of 123 degrees. The corrections for variation and deviation must be applied in the correct sequence, and is shown below, starting from the true course desired. Step 1. Determine the magnetic course. True course, 180 degrees, plus or minus variation, plus 10 degrees, equals magnetic course, 190 degrees. The magnetic course, 190 degrees, is steered if there is no deviation error to be applied. The compass card must now be considered for the compass course of 190 degrees. Step 2. Determine the compass course. Magnetic course, 190 degrees from step 1, plus or minus deviation, minus 2 degrees from correction card, equals compass course, 188 degrees. Note: intermediate magnetic courses between those listed on the compass card need to be interpreted. Therefore, to steer a true course of 180 degrees, the pilot would follow a compass course of 188 degrees. To find the true course that is being flown when the compass course is known, compass course plus or minus deviation equals magnetic course plus or minus variation equals true course. Dip errors. The lines of magnetic flux are considered to leave the Earth at the magnetic North Pole and enter at the magnetic South Pole. At both locations, the lines are perpendicular to the Earth's surface. At the magnetic equator, which is halfway between the poles, the lines are parallel with the surface. The magnets in a compass align with this field, and near the poles they dip or tilt the float-end card. This dip causes two very noticeable errors. northerly turning error, and acceleration error. The pull of the vertical component of the Earth's magnetic field causes northerly turning error, which is apparent on a heading of north or south. When an aircraft flying on a heading of north makes a turn toward east, the aircraft banks to the right, and the compass card tilts to the right. The vertical component of the Earth's magnetic field pulls the north-seeking end of the magnet to the right, and the float rotates, causing the card to rotate toward west, the direction opposite the direction the turn is being made. Figure 7-35. If the turn is made from north to west, the aircraft banks to the left, and the compass card tilts down on the left side. The magnetic field pulls on the end of the magnet that causes the card to rotate toward east. This indication is, again, opposite to the direction the turn is being made. The rule for this error is, when starting a turn from a northerly heading, the compass indication lags behind the turn. When an aircraft is flying on a heading of south and begins a turn toward east, the Earth's magnetic field pulls on the end of the magnet that rotates the card toward east, the same direction the turn is being made. If the turn is made from south toward west, the magnetic pull starts the card rotating toward west, again, in the same direction the turn is being made. The rule for this error is, when starting a turn from a southerly heading, the compass indication leads the turn. In acceleration error, the dip correction weight causes the end of the float and card marked N, the south-seeking end, to be heavier than the opposite end. When the aircraft is flying at a constant speed on a heading of east or west, the float and card is level. The effects of magnetic dip and the weight are approximately equal. If the aircraft accelerates on a heading of east, Figure 7-36, the inertia of the weight holds its end of the float back, and the card rotates toward north. As soon as the speed of the aircraft stabilizes, the card swings back to its east indication. If, while flying on this easterly heading, the aircraft decelerates, the inertia causes the weight to move ahead, and the card rotates toward south until the speed again stabilizes. When flying on a heading of west, the same things happen. Inertia from acceleration causes the weight to lag, and the card rotates toward north. When the aircraft decelerates on a heading of west, inertia causes the weight to move ahead, and the card rotates toward south. A mnemonic or memory jogger for the effect of acceleration error is the word AND. Acceleration, north. Deceleration, south. Acceleration causes an indication toward north. Deceleration causes an indication toward south. Oscillation error. Oscillation is a combination of all of the other errors, and it results in the compass card swinging back and forth around the heading being flown. When setting the gyroscopic heading indicator to agree with the magnetic compass, use the average indication between the swings. The vertical card magnetic compass. The floating magnet type of compass not only has all the errors just described, but also lends itself to confused reading. It is easy to begin a turn in the wrong direction because its card appears backward. East is on what the pilot would expect to be the west side. The vertical card magnetic compass eliminates some of the errors and confusion. The dial of this compass is graduated with letters representing the cardinal directions, numbers every 30 degrees, and tick marks every 5 degrees. The dial is rotated by a set of gears from the shaft-mounted magnet, and the nose of the symbolic aircraft on the instrument glass represents the lubber line for reading the heading of the aircraft from the dial. Eddy currents induced into an aluminum damping cup damp, or decrease, oscillation of the magnet. Figure 7-37. Lags or leads. When starting a turn from a northerly heading, the compass lags behind the turn. When starting a turn from a southerly heading, the compass leads the turn. Eddy current damping. In the case of a vertical card magnetic compass, flux from the oscillating permanent magnet produces eddy currents in a damping disc or cup. The magnetic flux produced by the eddy currents opposes the flux from the permanent magnet and decreases the oscillations. Outside air temperature, OAT gauge. The outside air temperature, OAT gauge, is a simple and effective device mounted so that the sensing element is exposed to the outside air. The sensing element consists of a bimetallic type thermometer in which two dissimilar materials are welded together in a single strip and twisted into a helix. One end is anchored into a protective tube, and the other end is affixed to the pointer, which reads against the calibration on a circular face. OAT gauges are calibrated in degrees Celsius, degrees Fahrenheit, or both. An accurate air temperature provides the pilot with useful information about temperature lapse rate with altitude change. Figure 7-38. Chapter Summary. Flight instruments enable an aircraft to be operated with maximum performance and enhanced safety, especially when flying long distances. Manufacturers provide the necessary flight instruments, but to use them effectively, pilots need to understand how they operate. As a pilot, it is important to become very familiar with the operational aspects of the pitot-static system and associated instruments, the vacuum system and associated instruments, the gyroscopic instruments, and the magnetic compass. End of Chapter 7, Part 5.
Part 1 of Chapter 8 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 1 of Chapter 8, Flight Manuals and Other Documents. Introduction. Each aircraft comes with documentation and a set of manuals with which a pilot must be familiar in order to fly that aircraft. This chapter covers airplane flight manuals, AFM, the Pilot's Operating Handbook, POH, and aircraft documents pertaining to ownership, airworthiness, maintenance, and operations with inoperative equipment. Knowledge of these required documents and manuals is essential for a pilot to conduct a safe flight. Airplane Flight Manuals, AFM. Flight manuals and operating handbooks are concise reference books that provide specific information about a particular aircraft or subject. They contain basic facts, information, and/or instructions for the pilot about the operation of an aircraft, flying techniques, etc., and are intended to be kept at hand for ready reference. The Aircraft Owner/Information Manual is a document developed by the manufacturer and contains general information about the make and model of aircraft. The manual is not approved by the Federal Aviation Administration, FAA, and is not specific to an individual aircraft. The manual provides general information about the operation of an aircraft, is not kept current, and cannot be substituted for the AFM/POH. An AFM is a document developed by the manufacturer and approved by the FAA. This book contains the information and instructions required to operate an aircraft safely. A pilot must comply with this information, which is specific to a particular make and model aircraft, usually by serial number. An AFM contains the operating procedures and limitations of that aircraft. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91 requires that pilots comply with the operating limitations specified in the approved flight manuals, markings, and placards. Originally, flight manuals followed whatever format and content the manufacturer felt was appropriate, but this changed with the acceptance of Specification Number 1 prepared by the General Aviation Manufacturers Association, GAMA. Specification Number 1 established a standardized format for all general aviation airplane and helicopter flight manuals. The POH is a document developed by the aircraft manufacturer and contains FAA-approved AFM information. If POH is used in the main title, a statement must be included on the title page indicating that sections of the document are FAA-approved as the AFM. The POH for most light aircraft built after 1975 is also designated as the FAA-approved flight manual. The typical AFM/POH contains the following 9 sections: General, Limitations, Emergency Procedures, Normal Procedures, Performance, Weight and Balance/Equipment List, Systems Description, Handling, Service, and Maintenance, and Supplements. Manufacturers also have the option of including additional sections, such as one on safety and operational tips, or an alphabetical index at the end of the POH. Preliminary pages. While the AFM/POH may appear similar for the same make and model of aircraft, each manual is unique and contains specific information about a particular aircraft, such as the equipment installed and the weight and balance information. Manufacturers are required to include the serial number and registration on the title page to identify the aircraft to which the manual belongs. If a manual does not indicate a specific aircraft registration and serial number, it is limited to general study purposes only. Most manufacturers include a table of contents which identifies the order of the entire manual by section number and title. Usually, each section also contains a table of contents for that section. Page numbers reflect the section and page within that section: 1-1, 1-2, 2-1, 3-1, etc. If the manual is published in loose-leaf form, each section is usually marked with a divider tab indicating the section number or title or both. The Emergency Procedures section may have a red tab for quick identification and reference. General, Section 1. The General section provides the basic descriptive information on the airframe and the power plant or power plants. Some manuals include a 3-dimensional drawing of the aircraft that provide dimensions of various components. Included are such items as wingspan, maximum height, overall length, wheelbase length, main landing gear track width, diameter of the rotor system, maximum propeller diameter, propeller ground clearance, minimum turning radius, and wing area. This section serves as a quick reference and helps a pilot become familiar with the aircraft. The last segment of the General section contains definitions, abbreviations, explanations of symbology, and some of the terminology used in the POH. At the option of the manufacturer, metric and other conversion tables may also be included. Limitations, Section 2. The Limitations section contains only those limitations required by regulation or that are necessary for the safe operation of the aircraft, power plant, systems, and equipment. It includes operating limitations, instrument markings, color coding, and basic placards. Some of the limitation areas are airspeed, power plant, weight and loading distribution, and flight. Airspeed. Airspeed limitations are shown on the airspeed indicator, ASI, by color coding and on placards or graphs in the aircraft. Refer to Figure 8-1. A red line on the ASI shows the airspeed limit beyond which structural damage could occur. This is called the Never Exceed Speed, VNE. A yellow arc indicates the speed range between maximum structural cruising speed, VNO, and VNE. Operation of an airplane in the yellow airspeed arc is for smooth air only, and then only with caution. A green arc depicts the normal operating speed range, with the upper end at VNO and the lower end at stalling speed at maximum weight with the landing gear and flaps retracted, VS1. For airplanes, the flap operating range is depicted by the white arc, with the upper end at the maximum flap extended speed, VFE, and the lower end at the stalling speed with the landing gear and flaps in the landing configuration, VSO. In addition to the markings listed above, small multi-engine airplanes will have a red radial line to indicate single-engine minimum controllable airspeed, VMC. A blue radial line is used to indicate single-engine best rate of climb speed at maximum weight at sea level, VYSE. Refer to Figure 8-2. Power plant. The power plant limitations portion describes operating limitations on an aircraft's reciprocating or turbine engine or engines. These include limitations for takeoff power, maximum continuous power, and maximum normal operating power, which is the maximum power the engine can produce without any restrictions and is depicted by a green arc. Other items that can be included in this area are the minimum and maximum oil and fuel pressures, oil and fuel grades, and propeller operating limits. Refer to Figure 8-3. All reciprocating engine-powered aircraft must have a revolutions per minute RPM indicator for each engine. Aircraft equipped with a constant speed propeller or rotor system use a manifold pressure gauge to monitor power output and a tachometer to monitor propeller or rotor speed. Both instruments depict the maximum operating limit with a red radial line and the normal operating range with a green arc. Refer to Figure 8-4. Some instruments may have a yellow arc to indicate a caution area. Weight and loading distribution. Weight and loading distribution contains the maximum certificated weights as well as the center of gravity, CG range. The location of the reference datum used in balance computations is included in this section. Weight and balance computations are not provided in this area, but rather in the weight and balance section of the AFM/POH. Flight limits. Flight limits list authorized maneuvers with appropriate entry speeds, flight load factor limits, and kinds of operation limits. It also indicates those maneuvers that are prohibited, such as spins or acrobatic flight, as well as operational limitations such as flight into known icing conditions. Placards. Most aircraft display one or more placards that contain information having a direct bearing on the safe operation of the aircraft. These placards are located in conspicuous places and are reproduced in the limitations section or as directed by an airworthiness directive, AD. Refer to Figure 8-5. Emergency Procedures, Section 3. Checklists describing the recommended procedures and airspeeds for coping with various types of emergencies or critical situations are located in the Emergency Procedures section. Some of the emergencies covered include engine failure, fire, and system failure. The procedures for in-flight engine restarting and ditching may also be included. Manufacturers may first show an emergency checklist in an abbreviated form with the order of items reflecting the sequence of action. Amplified checklists that provide additional information on the procedures follow the abbreviated checklist. To be prepared for emergency situations, memorize the immediate action items and, after completion, refer to the appropriate checklist. Manufacturers may include an optional subsection titled Abnormal Procedures. This subsection describes recommended procedures for handling malfunctions that are not considered emergencies. Normal Procedures, Section 4. This section begins with a list of the airspeeds for normal operations. The next area consists of several checklists that may include pre-flight inspection, before starting procedures, starting engine, before taxiing, before takeoff, climb, cruise, descent, before landing, balked landing, after landing, and post-flight procedures. An amplified procedures area follows the checklist to provide more detailed information about the various previously mentioned procedures. To avoid missing important steps, always use the appropriate checklist when available. Consistent adherence to approved checklists is a sign of a disciplined and competent pilot. Performance, Section 5. The Performance section contains all the information required by the aircraft certification regulations and any additional performance information the manufacturer deems important to pilot ability to safely operate the aircraft. Performance charts, tables, and graphs vary in style, but all contain the same basic information. Examples of the performance information found in most flight manuals include a graph or table for converting calibrated airspeed to true airspeed, stall speeds in various configurations, and data for determining takeoff and climb performance, cruise performance, and landing performance. Figure 8-6 is an example of a typical performance graph. For more information on the use of charts, graphs, and tables, refer to Chapter 10, Aircraft Performance. Weight and Balance Slant Equipment List, Section 6. The Weight and Balance Slant Equipment List section contains all the information required by the FAA to calculate the weight and balance of an aircraft. Manufacturers include sample weight and balance problems. Weight and balance is discussed in greater detail in Chapter 9, Weight and Balance. Systems Description, Section 7. This section describes the aircraft systems in a manner appropriate to the pilot most likely to operate the aircraft. For example, a manufacturer might assume an experienced pilot will be reading the information for an advanced aircraft. For more information on aircraft systems, refer to Chapter 6, Aircraft Systems. Handling, Service, and Maintenance, Section 8. The Handling, Service, and Maintenance section describes the maintenance and inspections recommended by the manufacturer and the regulations. Additional maintenance or inspections may be required by the issuance of AD applicable to the airframe, engine, propeller, or components. This section also describes preventive maintenance that may be accomplished by certificated pilots as well as the manufacturer's recommended ground handling procedures. It includes considerations for hangaring, tie-down, and general storage procedures for the aircraft. Supplements, Section 9. The Supplements section contains information necessary to safely and efficiently operate the aircraft when equipped with optional systems and equipment not provided with the standard aircraft. Some of this information may be supplied by the aircraft manufacturer or by the manufacturer of the optional equipment. The appropriate information is inserted into the flight manual at the time the equipment is installed. Autopilots, navigation systems, and air conditioning systems are examples of equipment described in this section. Refer to Figure 8-7. Safety Tips, Section 10. The Safety Tips section is an optional section containing a review of information that enhances the safe operation of the aircraft. For example, physiological factors, general weather information, fuel conservation procedures, high-altitude operations, or cold weather operations might be discussed. Aircraft Documents. Certificate of Aircraft Registration. Before an aircraft can be flown legally, it must be registered with the FAA Aircraft Registry. The Certificate of Aircraft Registration, which is issued to the owner as evidence of the registration, must be carried in the aircraft at all times. Refer to Figure 8-8. The Certificate of Aircraft Registration cannot be used for operations when the aircraft is registered under the laws of a foreign country, the aircraft's registration is canceled upon written request to the certificate holder, the aircraft is totally destroyed or scrapped, the ownership of the aircraft is transferred, or the certificate holder loses United States citizenship. For additional information, see 14 CFR Section 47.41. When one of the events listed in 14 CFR Section 47.41 occurs, the previous owner must notify the FAA by filling in the back of the Certificate of Aircraft Registration and mailing it to FAA Aircraft Registration Branch, AFS-750, P.O. Box 25504, Oklahoma City, Oklahoma, 73125-0504. A dealer's aircraft registration certificate is another form of registration certificate, but is valid only for required flight tests by the manufacturer or in flights that are necessary for the sale of the aircraft by the manufacturer or a dealer. The dealer must remove the certificate when the aircraft is sold. Upon complying with 14 CFR Section 47.31, the pink copy of the application for an aircraft registration application, Aeronautical Center AC Form 8050-1, provides authorization to operate an unregistered aircraft for a period not to exceed 90 days. Since the aircraft is unregistered, it cannot be operated outside of the United States until a permanent certificate of aircraft registration is received and placed in the aircraft. The FAA does not issue any certificate of ownership or endorse any information with respect to ownership on a certificate of aircraft registration. Note: for additional information concerning the aircraft registration application or the aircraft bill of sale, contact the nearest FAA Flight Standards District Office, FSDO. Light Sport Aircraft, LSA. The FAA recently added a new category called Light Sport Aircraft, LSA. Requirements for registration of these aircraft differ from those of other aircraft. The following guidelines are provided for LSA registration, but a more detailed explanation can be found on the FAA website at http://www.faa.gov. An existing LSA that has not been issued a United States or a foreign airworthiness certificate and does not meet the provisions of 14 CFR Section 103.1 must meet specific criteria in order to be certificated as an experimental LSA under 14 CFR Section 21.191, paragraph I-1, before January 31, 2008. The following items must be provided: evidence of ownership of the parts or the manufacturer's kit, aircraft registration application, AC Form 8050-1, and a $5 registration fee. If evidence of ownership cannot be supplied, an affidavit stating why it is not available must be submitted on the AC Form 8050-88A. If an owner wants to register a newly manufactured LSA that will be certificated as an experimental light sport aircraft under 14 CFR Section 21.191, paragraph I-2, the following items must be provided: AC Form 8050-88A or its equivalent, completed by the LSA manufacturer, unless previously submitted to the registry by the manufacturer, evidence from the manufacturer of ownership of an aircraft, kit built or flyaway, AC Form 8050-1, and a $5 registration fee. Airworthiness Certificate. An airworthiness certificate is issued by a representative of the FAA after the aircraft has been inspected, is found to meet the requirements of 14 CFR Part 21, and is in condition for safe operation. The airworthiness certificate must be displayed in the aircraft so it is legible to the passengers and crew whenever it is operated. The airworthiness certificate is transferred with the aircraft except when it is sold to a foreign purchaser. A standard airworthiness certificate is issued for aircraft type certificated in the normal, utility, acrobatic, commuter, transport categories, and manned free balloons. Figure 8-9 illustrates a standard airworthiness certificate, and an explanation of each item in the certificate follows. 1. National and registration marks. The N indicates the aircraft is registered in the United States. Registration marks consist of a series of up to 5 numbers or numbers and letters. In this case, N2631A is the registration number assigned to this airplane. 2. Manufacturer and model indicates the manufacturer, make, and model of the aircraft. 3. Aircraft serial number indicates the manufacturer's serial number assigned to the aircraft as noted on the aircraft data plate. 4. Category indicates the category in which the aircraft must be operated. In this case, it must be operated in accordance with the limitations specified for the normal category. 5. Authority and basis for issuance. Indicates the aircraft conforms to its type certificate and is considered in condition for safe operation at the time of inspection and issuance of the certificate. Any exemptions from the applicable airworthiness standards are briefly noted here and the exemption number given. The word none is entered if no exemptions exist. 6. Terms and conditions. Indicates the airworthiness certificate is in effect indefinitely if the aircraft is maintained in accordance with 14 CFR Parts 21, 43, and 91, and the aircraft is registered in the United States. Also included are the date the certificate was issued and the signature and office identification of the FAA representative. A standard airworthiness certificate remains in effect if the aircraft receives the required maintenance and is properly registered in the United States. Flight safety relies in part on the condition of the aircraft, which is determined by inspections performed by mechanics, approved repair stations, or manufacturers that meet specific requirements of 14 CFR Part 43. A special airworthiness certificate is issued for all aircraft certificated in other than the standard classifications, such as experimental, restricted, limited, provisional, and LSA. LSA receive a pink special airworthiness certificate. There are exceptions. For example, the Piper Cub is in the new LSA category, but it was certificated as a normal aircraft during its manufacture. When purchasing an aircraft classified as other than standard, it is recommended that the local FSDO be contacted for an explanation of the pertinent airworthiness requirements and the limitations of such a certificate. Aircraft maintenance. Maintenance is defined as the preservation, inspection, overhaul, and repair of an aircraft, including the replacement of parts. Regular and proper maintenance ensures that an aircraft meets an acceptable standard of airworthiness throughout its operational life. Although maintenance requirements vary for different types of aircraft, experience shows that aircraft need some type of preventative maintenance every 25 hours of flying time or less, and minor maintenance at least every 100 hours. This is influenced by the kind of operation, climatic conditions, storage facilities, age, and construction of the aircraft. Manufacturers supply maintenance manuals, parts, catalogs, and other service information that should be used in maintaining the aircraft. End of Part 1 of Chapter 8. Part 2 of Chapter 8 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 2 of Chapter 8, Flight Manuals and Other Documents. Aircraft Inspections. 14 CFR Part 91 places primary responsibility on the owner or operator for maintaining an aircraft in an airworthy condition. Certain inspections must be performed on the aircraft, and the owner must maintain the airworthiness of the aircraft during the time between required inspections by having any defects corrected. 14 CFR Part 91, Subpart E, requires the inspection of all civil aircraft at specific intervals to determine the overall condition. The interval depends upon the type of operations in which the aircraft is engaged. All aircraft need to be inspected at least once each 12 calendar months, while inspection is required for others after each 100 hours of operation. Some aircraft are inspected in accordance with an inspection system set up to provide for total inspection of the aircraft on the basis of calendar time, time in service, number of system operations, or any combination of these. All inspections should follow the current manufacturer's maintenance manual, including the instruction for continued airworthiness concerning inspections intervals, parts replacement, and life-limited items as applicable to the aircraft. Annual inspection. Any reciprocating engine or single-engine turbojet slant turbo propeller-powered small aircraft 12,500 pounds and under, flown for business or pleasure, and not flown for compensation or hire, is required to be inspected at least annually. The inspection shall be performed by a certificated airframe and power plant A&P mechanic who holds an inspection authorization IA by the manufacturer of the aircraft or by a certificated and appropriately rated repair station. The aircraft may not be operated unless the annual inspection has been performed within the preceding 12 calendar months. A period of 12 calendar months extends from any day of the month to the last day of the same month the following year. An aircraft overdue for an annual inspection may be operated under a special flight permit issued by the FAA for the purpose of flying the aircraft to a location where the annual inspection can be performed. However, all applicable ADs that are due must be complied with before the flight. 100-hour inspection. All aircraft under 12,500 pounds, except turbojet slant-turbo propeller-powered multi-engine airplanes and turbine-powered rotorcraft, used to carry passengers for hire, must have received a 100-hour inspection within the preceding 100 hours of time in service and have been approved for return to service. Additionally, an aircraft used for flight instruction for hire, when provided by the person giving the flight instruction, must also have received a 100-hour inspection. This inspection must be performed by an FAA-certificated A&P mechanic, an appropriately rated FAA-certificated repair station, or by the aircraft manufacturer. An annual inspection, or an inspection for the issuance of an airworthiness certificate, may be substituted for a required 100-hour inspection. The 100-hour limitation may be exceeded by not more than 10 hours while en route to reach a place where the inspection can be done. The excess time used to reach a place where the inspection can be done must be included in computing the next 100 hours of time in service. Other inspection programs. The annual and 100-hour inspection requirements do not apply to large, over 12,500 pounds, airplanes, turbojets, or turbopropeller-powered multi-engine airplanes, or to aircraft for which the owner complies with a progressive inspection program. Details of these requirements may be determined by reference to 14 CFR Section 43.11 and 14 CFR Part 91, Subpart E, and by inquiring at a local FSDO. Altimeter System Inspection. 14 CFR Section 91.411 requires that the altimeter, encoding altimeter, and related system be tested and inspected in the preceding 24 months before operated in controlled airspace under instrument flight rules, IFR. Transponder Inspection. 14 CFR Section 91.413 requires that before a transponder can be used under 14 CFR Section 91.215A, it shall be tested and inspected within the preceding 24 months. Emergency Locator Transmitter. An emergency locator transmitter, ELT, is required by 14 CFR Section 91.207 and must be inspected within 12 calendar months after the last inspection for the following: proper installation, battery corrosion, operation of the controls and crash sensor, the presence of a sufficient signal radiated from its antenna. The ELT must be attached to the airplane in such a manner that the probability of damage to the transmitter in the event of crash impact is minimized. Fixed and deployable automatic type transmitters must be attached to the airplane as far aft as practicable. Batteries used in the ELTs must be replaced or recharged if the batteries are rechargeable when the transmitter has been in use for more than 1 cumulative hour, or when 50% of the battery useful life, or for rechargeable batteries, 50% of useful life of the charge has expired. An expiration date for replacing or recharging the battery must be legibly marked on the outside of the transmitter and entered in the aircraft maintenance record. This does not apply to batteries that are essentially unaffected during storage intervals, such as water-activated batteries. Pre-flight inspections. The pre-flight inspection is a thorough and systematic means by which a pilot determines if the aircraft is airworthy and in condition for safe operation. POHs and owner slant information manuals contain a section devoted to a systematic method of performing a pre-flight inspection. Minimum Equipment Lists, MEL, and Operations with Inoperative Equipment. 14 CFR requires that all aircraft instruments and installed equipment be operative prior to each departure. When the FAA adopted the Minimum Equipment List, MEL concept for 14 CFR Part 91 operations, this allowed operations with inoperative equipment determined to be non-essential for safe flight. At the same time, it allowed Part 91 operators without an MEL to defer repairs on non-essential equipment within the guidelines of Part 91. The FAA has two acceptable methods of deferring maintenance on small rotorcraft, non-turbine-powered airplanes, gliders, or lighter-than-air aircraft operated under Part 91. They are the deferral provision of 14 CFR Section 91.213D and an FAA-approved MEL. The deferral provision of 14 CFR Section 91.213D is widely used by most pilot slant operators. Its popularity is due to simplicity and minimal paperwork. When inoperative equipment is found during pre-flight or prior to departure, the decision should be made to cancel the flight, obtain maintenance prior to flight, or to defer the item or equipment. Maintenance deferrals are not used for in-flight discrepancies. The manufacturer's AFM/POH procedures are to be used in those situations. The discussion that follows assumes that the pilot wishes to defer maintenance that would ordinarily be required prior to flight. Using the deferral provision of 14 CFR Section 91.213D, the pilot determines whether the inoperative equipment is required by type design, 14 CFR, or ADs. If the inoperative item is not required and the aircraft can be safely operated without it, the deferral may be made. The inoperative item shall be deactivated or removed and an inoperative placard placed near the appropriate switch, control, or indicator. If deactivation or removal involves maintenance, removal always will, it must be accomplished by certificated maintenance personnel and recorded in accordance with 14 CFR Part 43. For example, if the position lights, installed equipment, were discovered to be inoperative prior to a daytime flight, the pilot would follow the requirements of 14 CFR Section 91.213D. The deactivation may be a process as simple as the pilot positioning a circuit breaker to the off position or as complex as rendering instruments or equipment totally inoperable. Complex maintenance tasks require a certificated and appropriately rated maintenance person to perform the deactivation. In all cases, the item or equipment must be placarded inoperative. All small rotorcraft, non-turbine-powered airplanes, gliders, or lighter-than-air aircraft operated under 14 CFR Part 91 are eligible to use the maintenance deferral provisions of 14 CFR Section 91.213D. However, once an operator requests an MEL and a letter of authorization, LOA, is issued by the FAA, then the use of the MEL becomes mandatory for that aircraft. All maintenance deferrals must be accomplished in accordance with the terms and conditions of the MEL and the operator-generated procedures document. The use of an MEL for an aircraft operated under 14 CFR Part 91 also allows for the deferral of inoperative items or equipment. The primary guidance becomes the FAA-approved MEL issued to that specific operator and N-numbered aircraft. The FAA has developed Master Minimum Equipment Lists, MMELs, for aircraft in current use. Upon written request by an operator, the local FSDO may issue the appropriate make and model MMEL, along with an LOA and the preamble. The operator then develops operations and maintenance O&M procedures from the MMEL. This MMEL with O&M procedures now becomes the operator's MEL. The MEL, LOA, preamble, and the procedures document developed by the operator must be on board the aircraft when it is operated. The FAA considers an approved MEL to be a supplemental type certificate, STC, issued to an aircraft by serial number and registration number. It therefore becomes the authority to operate that aircraft in a condition other than originally type certificated. With an approved MEL, if the position lights were discovered inoperative prior to a daytime flight, the pilot would make an entry in the maintenance record or discrepancy record provided for that purpose. The item is then either repaired or deferred in accordance with the MEL. Upon confirming the daytime flight with inoperative position lights is acceptable in accordance with the provisions of the MEL, the pilot would leave the position lights switched off, open the circuit breaker, or whatever action is called for in the procedures document, and placard the position light switch as inoperative. There are exceptions to the use of the MEL for deferral. For example, should a component fail that is not listed in the MEL as deferrable, the tachometer, flaps, or stall warning device, for example, then repairs are required to be performed prior to departure. If maintenance or parts are not readily available at that location, a special flight permit can be obtained from the nearest FSDO. This permit allows the aircraft to be flown to another location for maintenance. This allows an aircraft that may not currently meet applicable airworthiness requirements, but is capable of safe flight, to be operated under the restrictive special terms and conditions attached to the special flight permit. Deferral of maintenance is not to be taken lightly, and due consideration should be given to the effect an inoperative component may have on the operation of an aircraft, particularly if other items are inoperative. Further information regarding MELs and operations with inoperative equipment can be found in AC 91-67, Minimum Equipment Requirements for General Aviation Operations under CFR Part 91. Preventive maintenance. Preventive maintenance is considered to be simple or minor preservation operations and the replacement of small standard parts, not involving complex assembly operations. Allowed items of preventative maintenance are listed and limited to the items of 14 CFR Part 43, Appendix A, C. Maintenance entries. All pilots who maintain or perform preventive maintenance must make an entry in the maintenance record of the aircraft. This entry must include 1. A description of the work, such as changed oil, shell aero-50 at 2,345 hours. 2. The date of completion of the work performed. 3. The entry of the pilot's name, signature, certificate number, and type of certificate held. Examples of preventive maintenance. The following examples of preventive maintenance are taken from 14 CFR Part 43, Maintenance, Preventative Maintenance, Rebuilding, and Alteration, which should be consulted for a more in-depth look at preventive maintenance a pilot can perform on an aircraft. Remember, preventive maintenance is limited to work that does not involve complex assembly operations and includes removal, installation, and repair of landing gear tires and shock cords, servicing landing gear shock struts by adding oil, air, or both, servicing gear wheel bearings, replacing defective safety wiring or cotter keys, lubrication not requiring disassembly other than removal of non-structural items such as cover plates, cowlings, and fairings, making simple fabric patches not requiring rib stitching or the removal of structural parts or control surfaces. In the case of balloons, the making of small fabric repairs to envelopes, as defined in and in accordance with the balloon manufacturer's instructions, not requiring load tape repair or replacement. Replenishing hydraulic fluid in the hydraulic reservoir, refinishing decorative coating of fuselage, balloon baskets, wings, tail group surfaces, excluding balanced control surfaces, fairings, cowlings, landing gear, cabin or flight deck interior when removal or disassembly of any primary structure or operating system is not required, applying preservative or protective material to components where no disassembly of any primary structure or operating system is involved, and where such coating is not prohibited or is not contrary to good practices, repairing upholstery and decorative furnishings of the cabin, flight deck, or balloon basket interior when a repair does not require disassembly of any primary structure or operating system or interfere with an operating system or affect the primary structure of the aircraft, making small, simple repairs to fairings, non-structural cover plates, cowlings, and small patches and reinforcements, not changing the contour to interfere with proper airflow, replacing side windows where that work does not interfere with the structure or any operating system such as controls, electrical equipment, etc. Replacing safety belts, seats, or seat parts with replacement parts approved for the aircraft, not involving disassembly of any primary structure or operating system, bulbs, reflectors, and lenses of position and landing lights, replacing wheels and skis where no weight and balance computation is involved, replacing any cowling not requiring removal of the propeller or disconnection of flight controls, replacing or cleaning spark plugs and setting of spark plug gap clearance, replacing any hose connection, except hydraulic connections. However, prefabricated fuel lines may be replaced. Cleaning or replacing fuel and oil strainers or filter elements, servicing batteries, cleaning of balloon burner pilot and main nozzles in accordance with the balloon manufacturer's instructions, the interchange of balloon baskets and burners on envelopes when the basket or burner is designated as interchangeable in the balloon type certificate data, and the baskets and burners are specifically designed for quick removal and installation, adjustment of non-structural standard fasteners incidental to operations, the installations of anti-misfueling devices to reduce the diameter of fuel tank filler openings only if the specific device has been made a part of the aircraft type certificate data by the aircraft manufacturer. The aircraft manufacturer has provided FAA-approved instructions for installation of the specific device, and installation does not involve the disassembly of the existing tank filler opening. Troubleshooting and repairing broken circuits and landing light wiring circuits. Removing and replacing self-contained, front instrument panel-mounted navigation and communication devices, employing tray-mounted connectors that connect the unit when the unit is installed into the instrument panel. Excluding automatic flight control systems, transponders, and microwave frequency distance measuring equipment, DME. The approved unit must be designed to be readily and repeatedly removed and replaced, and pertinent instructions must be provided. Prior to the unit's intended use, an operational check must be performed in accordance with the applicable sections of 14 CFR Part 91 on checking, removing, and replacing magnetic chip detectors. Inspection and maintenance tasks prescribed and specifically identified as preventative maintenance in a primary category aircraft type certificate or a supplemental type certificate holder's approved special inspection and preventative maintenance program when accomplished on a primary category aircraft. Updating self-contained front instrument panel-mounted air traffic control ATC navigational software databases, excluding those of automatic flight control systems, transponders, and microwave frequency DME, only if no disassembly of the unit is required and pertinent instructions are provided. Prior to the unit's intended use, an operational check must be performed in accordance with applicable sections of 14 CFR Part 91. Certificated pilots, excluding student pilots, sport pilots, and recreational pilots, may perform preventative maintenance on any aircraft that is owned or operated by them, provided that aircraft is not used in air carrier service or 14 CFR Part 121, 129, or 135. A pilot holding a sport pilot certificate may perform preventive maintenance on an aircraft owned or operated by that pilot if that aircraft is issued a special airworthiness certificate in the LSA category. Sport pilots operating LSA should refer to 14 CFR Part 65 for maintenance privileges. 14 CFR Part 43, Appendix A, contains a list of the operations that are considered to be preventive maintenance. Repairs and alterations. Repairs and alterations are classified as either major or minor. 14 CFR Part 43, Appendix A, describes the alterations and repairs considered major. Major repairs or alterations shall be approved for return to service on FAA Form 337, Major Repair and Alteration, by an appropriately rated certificated repair station, an FAA certificated A&P mechanic holding an IA, or a representative of the administrator. Minor repairs and minor alterations may be approved for return to service with a proper entry in the maintenance records by an FAA certificated A&P mechanic or an appropriately certificated repair station. For modifications of experimental aircraft, refer to the operating limitations issued to that aircraft. Modifications in accordance with FAA Order 8130.2, Airworthiness Certification of Aircraft and Related Products, may require the notification of the issuing authority. Special Flight Permits. A special flight permit is a special airworthiness certificate authorizing operation of an aircraft that does not currently meet applicable airworthiness requirements, but is safe for a specific flight. Before the permit is issued, an FAA inspector may personally inspect the aircraft or require it to be inspected by an FAA certificated A&P mechanic or an appropriately certificated repair station to determine its safety for the intended flight. The inspection shall be recorded in the aircraft records. The special flight permit is issued to allow the aircraft to be flown to a base where repairs, alterations, or maintenance can be performed, for delivering or exporting the aircraft, or for evacuating an aircraft from an area of impending danger. A special flight permit may be issued to allow the operation of an overweight aircraft for flight beyond its normal range over water or land areas where adequate landing facilities or fuel is not available. If a special flight permit is needed, assistance and the necessary forms may be obtained from the local FSDO or designated airworthiness representative, DAR. Refer to Figure 8-10. Airworthiness Directives, ADs. A primary safety function of the FAA is to require correction of unsafe conditions found in an aircraft engine, propeller, or appliance when such conditions exist and are likely to exist or develop in other products of the same design. The unsafe condition may exist because of a design defect, maintenance, or other causes. 14 CFR Part 39 and Airworthiness Directives, ADs, define the authority and responsibility of the administrator for requiring the necessary corrective action. ADs are used to notify aircraft owners and other interested persons of unsafe conditions and to specify the conditions under which the product may continue to be operated. ADs are divided into two categories. 1. Those of an emergency nature requiring immediate compliance prior to further flight. 2. Those of a less urgent nature requiring compliance within a specified period of time. ADs are regulatory and shall be complied with unless a specific exemption is granted. It is the responsibility of the aircraft owner or operator to ensure compliance with all pertinent ADs, including those ADs that require recurrent or continuing action. For example, an AD may require a repetitive inspection each 50 hours of operation, meaning the particular inspection shall be accomplished and recorded every 50 hours of time in service. Owners/operators are reminded there is no provision to overfly the maximum hour requirement of an AD unless it is specifically written into the AD. To help determine if an AD applies to an amateur-built aircraft, contact the local FSDO. 14 CFR Section 91.417 requires a record to be maintained that shows the current status of applicable ADs, including the method of compliance, the AD number and revision date, if recurring, next due date and time, the signature, kind of certificate, and the certificate number of the repair station or mechanic who performed the work. For ready reference, many aircraft owners have a chronological listing of the pertinent ADs in the back of their aircraft engine and propeller maintenance records. All ADs and the AD Bi-Weekly are free on the Internet at http://rgl.faa.gov. In July of 2007, the FAA made ADs available through email. Individuals can enroll for the email service at the link above. Mailing paper copies of ADs will be discontinued when the email system is proven to be effective. Paper copies of the Summary of Airworthiness Directives and the AD Biweekly may be purchased from the Superintendent of Documents. The summary contains all the valid ADs previously published and is divided into two areas. The small aircraft and helicopter books contain all ADs applicable to small aircraft, 12,500 pounds or less maximum certificated takeoff weight, and ADs applicable to all helicopters. The large aircraft books contain all ADs applicable to large aircraft. For current information on how to order paper copies of AD books and the AD Biweekly, visit the FAA Online Regulatory and Guidance Library at http://rgl.faa.gov. Aircraft Owner/Operator Responsibilities. The registered owner/operator of an aircraft is responsible for having a current airworthiness certificate and a certificate of aircraft registration in the aircraft, maintaining the aircraft in an airworthy condition, including compliance with all applicable ADs and assuring that maintenance is properly recorded, keeping abreast of current regulations concerning the operation and maintenance of the aircraft, notifying the FAA Aircraft Registry immediately of any change of permanent mailing address or of the sale or export of the aircraft or of the loss of the eligibility to register an aircraft. Refer to 14 CFR Section 47.41. Having a current Federal Communications Commission FCC radio station license if equipped with radios, including Emergency Locator Transmitter ELT, if operated outside of the United States. Chapter Summary. Knowledge of an aircraft's AFM/POH and documents such as ADs help a pilot to have ready access to pertinent information needed to safely fly a particular aircraft. By understanding the operations, limitations, and performance characteristics of the aircraft, the pilot can make good flight decisions. By learning what preventative maintenance is allowed on the aircraft, a pilot can maintain his or her aircraft in an airworthy condition. The goal of every pilot is a safe flight. Flight manuals and aircraft documentation are essential tools used to reach that goal. End of Part 2 of Chapter 8. Part 1 of Chapter 9 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 1 of Chapter 9, Weight and Balance. Introduction. Compliance with the weight and balance limits of any aircraft is critical to flight safety. Operating above the maximum weight limitation compromises the structural integrity of an aircraft and adversely affects its performance. Operation with the center of gravity, CG, outside the approved limits results in control difficulty. Weight control. As discussed in Chapter 4, Aerodynamics of Flight, weight is the force with which gravity attracts a body toward the center of the Earth. It is a product of the mass of a body and the acceleration acting on the body. Weight is a major factor in aircraft construction and operation and demands respect from all pilots. The force of gravity continuously attempts to pull an aircraft down toward Earth. The force of lift is the only force that counteracts weight and sustains an aircraft in flight. The amount of lift produced by an airfoil is limited by the airfoil design, angle of attack, AOA, airspeed, and air density. To assure that the lift generated is sufficient to counteract weight, loading an aircraft beyond the manufacturer's recommended weight must be avoided. If the weight is greater than the lift generated, the aircraft may be incapable of flight. Effects of weight. Any item aboard the aircraft that increases the total weight is undesirable for performance. Manufacturers attempt to make an aircraft as light as possible without sacrificing strength or safety. The pilot should always be aware of the consequences of overloading. An overloaded aircraft may not be able to leave the ground, or if it does become airborne, it may exhibit unexpected and unusually poor flight characteristics. If not properly loaded, the initial indication of poor performance usually takes place during takeoff. Excessive weight reduces the flight performance in almost every respect. For example, the most important performance deficiencies of an overloaded aircraft are high takeoff speed, longer takeoff run, reduced rate and angle of climb, lower maximum altitude, shorter range, reduced cruising speed, reduced maneuverability, higher stalling speed, higher approach and landing speed, longer landing roll, excessive weight on the nose wheel or tail wheel. The pilot must be knowledgeable about the effect of weight on the performance of the particular aircraft being flown. Pre-flight planning should include a check of performance charts to determine if the aircraft's weight may contribute to hazardous flight conditions. Excessive weight in itself reduces the safety margins available to the pilot, and becomes even more hazardous when other performance-reducing factors are combined with excess weight. The pilot must also consider the consequences of an overweight aircraft if an emergency condition arises. If an engine fails on takeoff, or airframe ice forms at low altitude, it is usually too late to reduce an aircraft's weight to keep it in the air. Weight changes. The operating weight of an aircraft can be changed by simply altering the fuel load. Gasoline has considerable weight, 6 pounds per gallon. 30 gallons of fuel may weigh more than one passenger. If a pilot lowers airplane weight by reducing fuel, the resulting decrease in the range of the airplane must be taken into consideration during flight planning. During flight, fuel burn is normally the only weight change that takes place. As fuel is used, an aircraft becomes lighter and performance is improved. Changes of fixed equipment have a major effect upon the weight of an aircraft. The installation of extra radios or instruments, as well as repairs or modifications, may also affect the weight of an aircraft. Balance, stability, and center of gravity. Balance refers to the location of the CG of an aircraft and is important to stability and safety in flight. The CG is a point at which the aircraft would balance if it were suspended at that point. The primary concern in balancing an aircraft is the fore and aft location of the CG along the longitudinal axis. The CG is not necessarily a fixed point. Its location depends on the distribution of weight in the aircraft. As variable load items are shifted or expended, there is a resultant shift in CG location. The distance between the forward and back limits for the position for the center of gravity or CG range is certified for an aircraft by the manufacturer. The pilot should realize that if the CG is displaced too far forward on the longitudinal axis, a nose-heavy condition will result. Conversely, if the CG is displaced too far aft on the longitudinal axis, a tail-heavy condition results. It is possible that the pilot could not control the aircraft if the CG location produced an unstable condition. Refer to Figure 9-1. Location of the CG with reference to the lateral axis is also important. For each item of weight existing to the left of the fuselage centerline, there is an equal weight existing at a corresponding location on the right. This may be upset by unbalanced lateral loading. The position of the lateral CG is not computed in all aircraft, but the pilot must be aware that adverse effects arise as a result of a laterally unbalanced condition. In an airplane, lateral unbalance occurs if the fuel load is mismanaged by supplying the engine or engines unevenly from tanks on one side of the airplane. The pilot can compensate for the resulting wing-heavy condition by adjusting the trim or by holding a constant control pressure. This action places the aircraft controls in an out-of-streamline condition, increases drag, and results in decreased operating efficiency. Since lateral balance is addressed when needed in the Aircraft Flight Manual, AFM, and longitudinal balance is more critical, Further reference to balance in this handbook means longitudinal location of the CG. A single pilot operating a small rotorcraft may require additional weight to keep the aircraft laterally balanced. Flying an aircraft that is out of balance can produce increased pilot fatigue, with obvious effects on the safety and efficiency of flight. The pilot's natural correction for longitudinal unbalance is a change of trim to remove the excessive control pressure. Excessive trim, however, has the effect of reducing not only aerodynamic efficiency, but also the primary control travel distance in the direction the trim is applied. Effects of adverse balance. Adverse balance conditions affect flight characteristics in much the same manner as those mentioned for an excess weight condition. It is vital to comply with weight and balance limits established for all aircraft, especially rotorcraft. Operating above the maximum weight limitation compromises the structural integrity of the rotorcraft and adversely affects performance. Balance is also critical because on some fully loaded rotorcraft, CG deviations as small as 3 inches can dramatically change handling characteristics. Stability and control are also affected by improper balance. Stability. Loading in a nose-heavy condition causes problems in controlling and raising the nose, especially during takeoff and landing. Loading in a tail-heavy condition has a serious effect upon longitudinal stability and reduces the capability to recover from stalls and spins. Tail-heavy loading also produces very light control forces, another undesirable characteristic. This makes it easy for the pilot to inadvertently overstress an aircraft. It is important to reevaluate the balance in a rotorcraft whenever loading changes. In most aircraft, offloading a passenger is unlikely to adversely affect the CG, but offloading a passenger from a rotorcraft can create an unsafe flight condition. An out-of-balance loading condition also decreases maneuverability, since cyclic control is less effective in the direction opposite to the CG location. Limits for the location of the CG are established by the manufacturer. There are the fore and aft limitations beyond which the CG should not be located for flight. These limits are published for each aircraft in the Type Certificate Data Sheet, TCDS, or Aircraft Specification, and the AFM, or Pilot's Operating Handbook, POH. If the CG is not within the allowable limits after loading, it will be necessary to relocate some items before flight is attempted. The forward CG limit is often established at a location that is determined by the landing characteristics of an aircraft. During landing, one of the most critical phases of flight, exceeding the forward CG limit may result in excessive loads on the nose wheel, a tendency to nose over on tailwheel type airplanes, decreased performance, higher stalling speeds, and higher control forces. Control. In extreme cases, a CG location that is beyond the forward limit may result in nose heaviness, making it difficult or impossible to flare for landing. Manufacturers purposefully place the forward CG limit as far rearward as possible to aid pilots in avoiding damage when landing. In addition to decreased static and dynamic longitudinal stability, other undesirable effects caused by a CG location after the allowable range may include extreme control difficulty, violent stall characteristics, and very light control forces which make it easy to overstress an aircraft inadvertently. A restricted forward CG limit is also specified to assure that sufficient elevator control deflection is available at minimum airspeed. When structural limitations do not limit the forward CG position, it is located at the position where full-up elevator control deflection is required to obtain a high AOA for landing. The aft CG limit is the most rearward position at which the CG can be located for the most critical maneuver or operation. As the CG moves aft, a less stable condition occurs, which decreases the ability of the aircraft to right itself after maneuvering or turbulence. For some aircraft, both fore and aft CG limits may be specified to vary as gross weight changes. They may also be changed for certain operations, such as acrobatic flight, retraction of the landing gear, or the installation of special loads and devices that change the flight characteristics. The actual location of the CG can be altered by many variable factors and is usually controlled by the pilot. Placement of baggage and cargo items determines the CG location. The assignment of seats to passengers can also be used as a means of obtaining a favorable balance. If an aircraft is tail-heavy, it is only logical to place heavy passengers in forward seats. Fuel burn can also affect the CG based on the location of the fuel tanks. For example, most small aircraft carry fuel in the wings very near the CG, and burning off fuel has little effect on the loaded CG. On rotorcraft, the fuel tanks are often located behind the CG, and fuel consumption from a tank after the rotor mast causes the loaded CG to move forward. A rotorcraft in this condition has a nose-low attitude when coming to a hover following a vertical takeoff. Excessive rearward displacement of the cyclic control is needed to maintain a hover in a no-wind condition. Flight should not be continued since rearward cyclic control fades as fuel is consumed. Deceleration to a stop may also be impossible. In the event of engine failure and auto-rotation, there may not be enough cyclic control to flare properly for a landing. Management of weight and balance control. Title 14 of the Code of Federal Regulations, 14 CFR, Section 23.23, requires establishment of the ranges of weights and CGs within which an aircraft may be operated safely. The manufacturer provides this information, which is included in the approved AFM, TCDS, or aircraft specifications. While there are no specified requirements for a pilot operating under 14 CFR Part 91 to conduct weight and balance calculations prior to each flight, 14 CFR Section 91.9 requires the pilot in command, PIC, to comply with the operating limits in the approved AFM. These limits include the weight and balance of the aircraft. To enable pilots to make weight and balance computations, charts and graphs are provided in the approved AFM. Weight and balance control should be a matter of concern to all pilots. The pilot controls loading and fuel management, the two variable factors that can change both total weight and CG location of a particular aircraft. The aircraft owner or operator should make certain that up-to-date information is available for pilot use and should ensure that appropriate entries are made in the records when repairs or modifications have been accomplished. The removal or addition of equipment results in changes to the CG. Weight changes must be accounted for, and the proper notations made in weight and balance records. The equipment list must be updated if appropriate. Without such information, the pilot has no foundation upon which to base the necessary calculations and decisions. Standard parts with negligible weight or the addition of minor items of equipment such as nuts, bolts, washers, rivets, and similar standard parts of negligible weight on fixed-wing aircraft do not require a weight and balance check. Rotorcraft are, in general, more critical with respect to control with changes in CG position. The following criteria for negligible weight change is outlined in Advisory Circular AC 43.13-1 as revised. Methods, Techniques, and Practices. Aircraft Inspection and Repair. 1 pound or less for an aircraft whose weight empty is less than 5,000 pounds. 2 pounds or less for an aircraft with an empty weight of more than 5,000 pounds to 50,000 pounds. And 5 pounds or less for aircraft with an empty weight of more than 50,000 pounds. Negligible CG change is any change of less than 0.05% mean aerodynamic chord, MAC, for fixed-wing aircraft, 0.2% of the maximum allowable CG range for rotorcraft. Exceeding these limits would require a weight and balance check. Before any flight, the pilot should determine the weight and balance condition of the aircraft. Simple and orderly procedures based on sound principles have been devised by the manufacturer for the determination of loading conditions. The pilot uses these procedures and exercises good judgment when determining weight and balance. In many modern aircraft, it is not possible to fill all seats, baggage compartments, and fuel tanks and still remain within the approved weight and balance limits. If the maximum passenger load is carried, the pilot must often reduce the fuel load or reduce the amount of baggage. 14 CFR Part 125 requires aircraft with 20 or more seats or weighing 6,000 pounds or more to be weighed every 36 calendar months. Multi-engine aircraft operated under a 14 CFR Part 135 are also required to be weighed every 36 months. Aircraft operated under 14 CFR Part 135 are exempt from the 36-month requirement if operated under a weight and balance system approved in the operation specifications of the certificate holder. AC 43.13-1, Acceptable Methods, Techniques, and Practices, Aircraft Inspection and Repair, also requires that the aircraft mechanic must ensure the weight and balance data in the aircraft records is current and accurate after a 100-hour or annual inspection. Terms and definitions. The pilot should be familiar with terms used in working problems related to weight and balance. The following list of terms and their definitions is standardized, and knowledge of these terms aids the pilot to better understand weight and balance calculations of any aircraft. Terms defined by the General Aviation Manufacturers Association, GAMA, as industry standard are marked in the titles with GAMA. Arm, moment arm. The horizontal distance in inches from the reference datum line to the CG of an item. The algebraic sign is plus if measured after the datum, and minus if measured forward of the datum. Basic empty weight, GAMA. The standard empty weight plus the weight of optional and special equipment that have been installed. Center of gravity, CG. The point about which an aircraft would balance if it were possible to suspend it at that point. It is the mass center of the aircraft, or the theoretical point at which the entire weight of the aircraft is assumed to be concentrated. It may be expressed in inches from the reference datum or in percent of MAC. The CG is a three-dimensional point with longitudinal, lateral, and vertical positioning in the aircraft. CG limits. The specified forward and aft points within which the CG must be located during flight. These limits are indicated on pertinent aircraft specifications. CG range. The distance between the forward and aft CG limits indicated on pertinent aircraft specifications. Datum, reference datum. An imaginary vertical plane or line from which all measurements of arm are taken. The datum is established by the manufacturer. Once the datum has been selected, all moment arms and the location of CG range are measured from this point. Delta. A Greek letter expressed by the symbol delta to indicate a change of values. As an example, delta CG indicates a change or movement of the CG. Floor load limit. The maximum weight the floor can sustain per square inch or foot as provided by the manufacturer. Fuel load. The expendable part of the load of the aircraft. It includes only usable fuel, not fuel required to fill the lines or that which remains trapped in the tank sumps. Licensed empty weight. The empty weight that consists of the airframe, engine or engines, unusable fuel, and undrainable oil, plus standard and optional equipment as specified in the equipment list. Some manufacturers use this term prior to GAMA standardization. Maximum landing weight. The greatest weight that an aircraft normally is allowed to have at landing. Maximum ramp weight. The total weight of a loaded aircraft and includes all fuel. It is greater than the takeoff weight due to the fuel that will be burned during the taxi and run-up operations. Ramp weight may also be referred to as taxi weight. Maximum takeoff weight. the maximum allowable weight for takeoff. Maximum weight. The maximum authorized weight of the aircraft and all of its equipment as specified in the TCDS for the aircraft. Maximum zero fuel weight, GAMA. The maximum weight exclusive of usable fuel. Mean aerodynamic chord, MAC. The average distance from the leading edge to the trailing edge of the wing. Moment. The product of the weight of an item multiplied by its arm. Moments are expressed in pound-inches, or inch-pounds. Total moment is the weight of the airplane multiplied by the distance between the datum and the CG. Moment index, or index. A moment divided by a constant such as 100, 1,000, or 10,000. The purpose of using a moment index is to simplify weight and balance computations of aircraft where heavy items and long arms result in large, unmanageable numbers. Payload, GAMA. The weight of occupants, cargo, and baggage. Standard empty weight, GAMA. Aircraft weight that consists of the airframe, engines, and all items of operating equipment that have fixed locations and are permanently installed in the aircraft, including fixed ballast, hydraulic fluid, unusable fuel, and full engine oil. Standard weights. Established weights for numerous items involved in weight and balance computations. These weights should not be used if actual weights are available. Some of the standard weights are gasoline, 6 pounds per U.S. gallon. Jet A, Jet A1, 6.8 pounds per U.S. gallon. Jet B, 6.5 pounds per U.S. gallon. Oil, 7.5 pounds per U.S. gallon. And water, 8.35 pounds per U.S. gallon. Station. A location in the aircraft that is identified by a number designating its distance in inches from the datum. The datum is therefore identified as Station 0. An item located at Station plus 50 would have an arm of 50 inches. Useful load. The weight of the pilot, co-pilot, passengers, baggage, usable fuel, and drainable oil. It is the basic empty weight subtracted from the maximum allowable gross weight. This term applies to general aviation GA aircraft only. End of Part 1 of Chapter 9. Part 2 of Chapter 9 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 9, Weight and Balance. Principles of Weight and Balance Computations. It might be advantageous at this point to review and discuss some of the basic principles of weight and balance determination. The following method of computation can be applied to any object or vehicle for which weight and balance information is essential. By determining the weight of the empty aircraft and adding the weight of everything loaded on the aircraft, a total weight can be determined. A simple concept. A greater problem, particularly if the basic principles of weight and balance are not understood, is distributing this weight in such a manner that the entire mass of the loaded aircraft is balanced around a point, CG, that must be located within specified limits. The point at which an aircraft balances can be determined by locating the CG, which is, as stated in the definition of terms, the imaginary point at which all the weight is concentrated. To provide the necessary balance between longitudinal stability and elevator control, the CG is usually located slightly forward of the center of lift. This loading condition causes a nose-down tendency in flight, which is desirable during flight at high AOA and slow speeds. As mentioned earlier, a safe zone within which the balance point, CG, must fall is called the CG range. The extremities of the range are called the forward CG limits and aft CG limits. These limits are usually specified in inches along the longitudinal axis of the airplane, measured from a reference point called a datum reference. The datum is an arbitrary point established by aircraft designers, which may vary in location between different aircraft. Refer to Figure 9-2. The distance from the datum to any component part or any object loaded on the aircraft is called the arm. When the object or component is located after the datum, it is measured in positive inches. If located forward of the datum, it is measured as negative inches or minus inches. The location of the object or part is often referred to as the station. If the weight of any object or component is multiplied by the distance from the datum, arm, the product is the moment. The moment is the measurement of the gravitational force that causes a tendency of the weight to rotate about a point or axis and is expressed in inch-pounds. To illustrate, assume a weight of 50 pounds is placed on the board at a station or point 100 inches from the datum. The downward force of the weight can be determined by multiplying 50 pounds by 100 inches, which produces a moment of 5,000 inch-pounds. Refer to Figure 9-3. To establish a balance, a total of 5,000 inch-pounds must be applied to the other end of the board. Any combination of weight and distance which, when multiplied, produces a 5,000 inch-pound moment will balance the board. For example, illustrated in Figure 9-4, if a 100-pound weight is placed at a point or station 25 inches from the datum, and another 50-pound weight is placed at a point or station 50 inches from the datum, the sum of the product of the two weights and their distances will total a moment of 5,000 inch-pounds, which will balance the board. Weight and balance restrictions. An aircraft's weight and balance restrictions should be closely followed. The loading conditions and empty weight of a particular aircraft may differ from that found in the AFM/POH, because modifications or equipment changes may have been made. Sample loading problems in the AFM/POH are intended for guidance only. Therefore, each aircraft must be treated separately. Although an aircraft is certified for a specified maximum gross takeoff weight, it will not safely take off with this load under all conditions. Conditions that affect takeoff and climb performance, such as high elevations, high temperatures, and high humidity, high-density altitudes, may require a reduction in weight before flight is attempted. Other factors to consider prior to takeoff are runway length, runway surface, runway slope, surface wind, and the presence of obstacles. These factors may require a reduction in weight prior to flight. Some aircraft are designed so that it is difficult to load them in a manner that will place the CG out of limits. These are usually small aircraft with the seats, fuel, and baggage areas located near the CG limit. Pilots must be aware that while within CG limits, these aircraft can be overloaded in weight. Other aircraft can be loaded in such a manner that they will be out of CG limits, even though the useful load has not been exceeded. Because of the effects of an out-of-balance or overweight condition, a pilot should always be sure that an aircraft is properly loaded. Determining loaded weight in CG. There are various methods for determining the loaded weight in CG of an aircraft. There is the computational method, as well as methods that utilize graphs and tables provided by the aircraft manufacturer. Computational method. The following is an example of the computational method involving the application of basic math functions. Aircraft allowances. Maximum gross weight, 3,400 pounds. CG range, 78 to 86 inches. Given: weight of the front seat occupants, 340 pounds. Weight of rear seat occupants, 350 pounds. Fuel, 75 gallons. Weight of baggage in Area 1, 80 pounds. 1. List the weight of the aircraft, occupants, fuel, and baggage. Remember that aviation gas, avgas, weighs 6 pounds per gallon and is used in this example. 2. Enter the moment for each item listed. Remember, weight times arm equals moment. 3. Find the total weight and total moment. 4. To determine the CG, divide the total moment by the total weight. Note: the weight and balance records for a particular aircraft will provide the empty weight and moment as well as the information on the arm distance. Refer to Figure 9-5. The total loaded weight of 3,320 pounds does not exceed the maximum gross weight of 3,400 pounds, and the CG of 84.8 is within the 78 to 86 inch range. Therefore, the aircraft is loaded within limits. Graph method. Another method for determining the loaded weight in CG is the use of graphs provided by the manufacturers. To simplify calculations, the moment may sometimes be divided by 100, 1,000, or 10,000. Refer to Figures 9-6, 9-7, and 9-8. Front seat occupants, 340 pounds. Rear seat occupants, 300 pounds. Fuel, 40 gallons. Baggage area 1, 20 pounds. The same steps should be followed as in the computational method, except the graphs provided will calculate the moments and allow the pilot to determine if the aircraft is loaded within limits. To determine the moment using the loading graph, find the weight and draw a line straight across until it intercepts the item for which the moment is to be calculated. Then draw a line straight down to determine the moment. The red line on the loading graph represents the moment for the pilot and front passenger. All other moments were determined in the same way. Once this has been done for each item, total the weight and moments and draw a line for both weight and moment on the CG envelope graph. If the lines intersect within the envelope, the aircraft is loaded within limits. In this sample loading problem, the aircraft is loaded within limits. Table method. The table method applies the same principles as the computational and graph methods. The information and limitations are contained in tables provided by the manufacturer. Figure 9-9 is an example of a table and a weight and balance calculation based on that table. In this problem, the total weight of 2,799 pounds and moment of 2,278 divided by 100 are within limits of the table. Computations with a negative arm. Figure 9-10 is a sample of weight and balance computation using an airplane with a negative arm. It is important to remember that a positive times a negative equals a negative, and a negative would be subtracted from the total moments. Computations with zero fuel weight. Figure 9-11 is a sample of weight and balance computation using an aircraft with a zero fuel weight. In this example, the total weight of the aircraft less fuel is 4,240 pounds, which is under the zero fuel weight of 4,400 pounds. If the total weight of the aircraft without fuel had exceeded 4,400 pounds, passengers or cargo would have needed to be reduced to bring the weight at or below the max zero fuel weight. Shifting, adding, and removing weight. A pilot must be able to solve any problems accurately that involve the shift, addition, or removal of weight. For example, the pilot may load the aircraft within the allowable takeoff weight limit, then find a CG limit has been exceeded. The most satisfactory solution to this problem is to shift baggage, passengers, or both. The pilot should be able to determine the minimum load shift needed to make the aircraft safe for flight. Pilots should be able to determine if shifting a load to a new location will correct an out-of-limit condition. There are some standardized calculations that can help make these determinations. Weight shifting. When weight is shifted from one location to another, the total weight of the aircraft is unchanged. The total moments, however, do change in relation and proportion to the direction and distance the weight is moved. When weight is moved forward, the total moments decrease. When weight is moved aft, total moments increase. The moment change is proportional to the amount of weight moved. Since many aircraft have forward and aft baggage compartments, weight may be shifted from one to the other to change the CG. If starting with a known aircraft weight, CG, and total moments, calculate the new CG after the weight shift by dividing the new total moments by the total aircraft weight. To determine the new total moments, find out how many moments are gained or lost when the weight is shifted. Assume that 100 pounds has been shifted from station 30 to station 150. This movement increases the total moments of the aircraft by 12,000 inch-pounds. Moment when at station 150 equals 100 pounds times 150 inches equals 15,000 inch-pounds. Moment when at station 30 equals 100 pounds times 30 inches equals 3,000 inch-pounds. The moment change is equal to 15,000 minus 3,000 equals 12,000 inch-pounds. By adding the moment change to the original moment, or subtracting if the weight had been moved forward instead of aft, the new total moments are obtained. Then determine the new CG by dividing the new moments by the total weight. Total moment equals 616,000 inch-pounds plus 12,000 inch-pounds equals 628,000 inch-pounds. CG is equal to 628,000 inch-pounds divided by 8,000 pounds equals 78.5 inches. The shift has caused the CG to shift to station 78.5. A simpler solution may be obtained by using a computer or a calculator and a proportional formula. This can be done because the CG will shift a distance that is proportional to the distance the weight is shifted. Example: weight shifted divided by total weight equals delta CG, or change of CG, divided by the distance weight is shifted. 100 divided by 8,000 equals delta CG divided by 120. The delta CG is equal to 1.5 inches. The change of CG is added or subtracted from, when appropriate, the original CG to determine the new CG. 77 plus 1.5 equals 78.5 inches after datum. The shifting weight proportion formula can also be used to determine how much weight must be shifted to achieve a particular shift of the CG. The following problem illustrates a solution of this type. Example: given aircraft total weight 7,800 pounds, CG station 81.5 inches, aft CG limit 80.5 inches. Determine how much cargo must be shifted from the aft cargo compartment at station 150 to the forward cargo compartment at station 30 to move the CG to exactly the aft limit. The solution: the weight to be shifted divided by the total weight equals delta CG divided by the distance weight is shifted. So, weight to be shifted divided by 7,800 pounds equals 1.0 inches divided by 120 inches. The weight to be shifted equals 65 pounds. Weight addition or removal. In many instances, the weight and balance of the aircraft will be changed by the addition or removal of weight. When this happens, a new CG must be calculated and checked against the limitations to see if the location is acceptable. This type of weight and balance problem is commonly encountered when the aircraft burns fuel in flight, thereby reducing the weight located at the fuel tanks. Most small aircraft are designed with the fuel tanks positioned close to the CG. Therefore, the consumption of fuel does not affect the CG to any great extent. The addition or removal of cargo presents a CG change problem that must be calculated before flight. The problem may always be solved by calculations involving total moments. A typical problem may involve the calculation of a new CG for an aircraft which, when loaded and ready for flight, receives some additional cargo or passengers just before departure time. Example: given an aircraft total weight of 6,860 pounds, CG station 80.0 inches. Determine the location of the CG if 140 pounds of baggage is added to station 150. Solution: added weight divided by the new total weight is equal to the delta CG divided by the distance between the weight and old CG. 140 pounds divided by 6,860 pounds plus 140 pounds is equal to delta CG divided by 150 inches minus 80 inches. 140 pounds divided by 7,000 pounds equals delta CG divided by 70 inches. The CG is equal to 1.4 inches aft. Add the delta CG to the old CG. The new CG is equal to 80 inches plus 1.4 inches, which is equal to 81.4 inches. Example: given an aircraft total weight of 6,100 pounds, CG station of 80.0 inches. Determine the location of the CG if 100 pounds is removed from station 150. Solution: weight removed divided by the new total weight equals delta CG divided by the distance between the weight and the old CG. So 100 pounds divided by 6,100 pounds minus 100 pounds equals delta CG divided by 150 inches minus 80 inches. 100 pounds divided by 6,000 pounds is equal to delta CG over 70 inches. And the CG is equal to 1.2 inches forward. Subtract delta CG from the old CG. The new CG is equal to 80 inches minus 1.2 inches equals 78.8 inches. In the previous examples, the delta CG is either added or subtracted from the old CG. Deciding which to accomplish is best handled by mentally calculating which way the CG will shift for the particular weight change. If the CG is shifting aft, the delta CG is added to the old CG. If the CG is shifting forward, the delta CG is subtracted from the old CG. Chapter Summary. Operating an aircraft within the weight and balance limits is critical to flight safety. Pilots must ensure that the CG is and remains within approved limits for all phases of a flight. Additional information on weight, balance, CG, and aircraft stability can be found in FAA-H-8083-1, Aircraft Weight and Balance Handbook. Those pilots flying helicopters or gyroplanes should consult the Rotorcraft Flying Handbook, FAA-H-8083-21, for specific information relating to aircraft type. End of Part 2 of Chapter 9. Part 1 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 1 of Chapter 10, Aircraft Performance. Introduction. This chapter discusses the factors that affect aircraft performance, which include the aircraft weight, atmospheric conditions, runway environment, and the fundamental physical laws governing the forces acting on an aircraft. Importance of performance data. The Performance or Operational Information section of the Aircraft Flight Manual / Pilot's Operating Handbook, AFM / POH, contains the operating data for the aircraft, that is, the data pertaining to takeoff, climb, range, endurance, descent, and landing. The use of this data in flying operations is mandatory for safe and efficient operation. Considerable knowledge and familiarity of the aircraft can be gained through study of this material. It must be emphasized that the manufacturer's information and data furnished in the AFM / POH is not standardized. Some provide the data in tabular form, while others use graphs. In addition, the performance data may be presented on the basis of standard atmospheric conditions, pressure altitude, or density altitude. The performance information in the AFM/POH has little or no value unless the user recognizes those variations and makes the necessary adjustments. To be able to make practical use of the aircraft's capabilities and limitations, it is essential to understand the significance of the operational data. The pilot must be cognizant of the basis for the performance data, as well as the meanings of the various terms used in expressing performance capabilities and limitations. Since the characteristics of the atmosphere have a major effect on performance, it is necessary to review the two dominant factors, pressure and temperature. Structure of the atmosphere. The atmosphere is an envelope of air that surrounds the Earth and rests upon its surface. It is as much a part of the Earth as its land and water. However, air differs from land and water inasmuch as it is a mixture of gases. It has mass, weight, and indefinite shape. Air, like any other fluid, is able to flow and change its shape when subjected to even minute pressures because of the lack of strong molecular cohesion. For example, gas will completely fill any container into which it is placed, expanding or contracting to adjust its shape to the limits of the container. The atmosphere is composed of 78% nitrogen, 21% oxygen, and 1% other gases, such as argon or helium. Most of the oxygen is contained below 35,000 feet altitude. Atmospheric pressure. Though there are various kinds of pressure, pilots are mainly concerned with atmospheric pressure. It is one of the basic factors in weather changes, helps to lift the aircraft, and actuates some of the most important flight instruments in the aircraft. These instruments often include the altimeter, the airspeed indicator, ASI, the vertical speed indicator, and the manifold pressure gauge. Though air is very light, it has mass and is affected by the attraction of gravity. Therefore, like any other substance, it has weight. Because it has weight, it has force. Since it is a fluid substance, this force is exerted equally in all directions, and its effect on bodies within the air is called pressure. Under standard conditions at sea level, the average pressure exerted by the weight of the atmosphere is approximately 14.7 pounds per square inch, psi. The density of air has significant effects on the aircraft's performance. As air becomes less dense, it reduces power because the engine takes in less air, thrust because the propeller is less efficient in thin air, lift because the thin air exerts less force on the airfoils. The pressure of the atmosphere varies with time and altitude. Due to the changing atmospheric pressure, a standard reference was developed. The standard atmosphere at sea level is a surface temperature of 59 degrees Fahrenheit, degrees F, or 15 degrees Celsius, degrees C, and a surface pressure of 29.92 inches of mercury, inches Hg, or 1013.2 millibars, MB. Refer to Figure 10-1. A standard temperature lapse rate is one in which the temperature decreases at the rate of approximately 3.5 degrees Fahrenheit or 2 degrees Celsius per 1,000 feet up to 36,000 feet. Above this point, the temperature is considered constant up to 80,000 feet. A standard pressure lapse rate is one in which pressure decreases at a rate of approximately 1 inch mercury per 1,000 feet of altitude gain to 10,000 feet. Refer to Figure 10-2. The International Civil Aviation Organization, ICAO, has established this as a worldwide standard, and it is often referred to as International Standard Atmosphere, ISA, or ICAO Standard Atmosphere. Any temperature or pressure that differs from the standard lapse rates is considered non-standard temperature and pressure. Adjustments for non-standard temperatures and pressures are provided on the manufacturer's performance charts. Since all aircraft performance is compared and evaluated with respect to the standard atmosphere, all aircraft instruments are calibrated for the standard atmosphere. Thus, certain corrections must apply to the instrumentation as well as aircraft performance if the actual operating conditions do not fit the standard atmosphere. In order to account properly for the non-standard atmosphere, certain related terms must be defined. Pressure altitude. Pressure altitude is the height above the standard datum plane, SDP. The aircraft altimeter is essentially a sensitive barometer calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 29.92 inches of mercury SDP, the altitude indicated is the pressure altitude, the altitude in the standard atmosphere corresponding to the sensed pressure. The SDP is a theoretical level where the pressure of the atmosphere is 29.92 inches of mercury and the weight of air is 14.7 psi. As atmospheric pressure changes, the SDP may be below, at, or above sea level. Pressure altitude is important as a basis for determining aircraft performance, as well as for assigning flight levels to aircraft operating at above 18,000 feet. The pressure altitude can be determined by any of three methods. 1. By setting the barometric scale of the altimeter to 29.92 inches of mercury and reading the indicated altitude. Or 2. By applying a correction factor to the indicated altitude according to the reported altimeter setting. See Figure 10-3. Or 3. By using a flight computer. Density altitude. The more appropriate term for correlating aerodynamic performance in the non-standard atmosphere is density altitude, the altitude in the standard atmosphere corresponding to a particular value of air density. Density altitude is pressure altitude corrected for non-standard temperature. As the density of the air increases, lower density altitude, aircraft performance increases. Conversely, as air density decreases, higher density altitude, aircraft performance decreases. A decrease in air density means a high density altitude. An increase in air density means a lower density altitude. Density altitude is used in calculating aircraft performance. Under standard atmospheric condition, air at each level in the atmosphere has a specific density. Under standard conditions, pressure altitude and density altitude identify the same level. Density altitude, then, is the vertical distance above sea level in the standard atmosphere at which a given density is to be found. The computation of density altitude must involve consideration of pressure altitude, and temperature. Since aircraft performance data at any level is based upon air density under standard day conditions, such performance data apply to air density levels that may not be identical to altimeter indications. Under conditions higher or lower than standard, these levels cannot be determined directly from the altimeter. Density altitude is determined by first finding pressure altitude and then correcting this altitude for non-standard temperature variations. Since density varies directly with pressure and inversely with temperature, a given pressure altitude may exist for a wide range of temperature by allowing the density to vary. However, a known density occurs for any one temperature and pressure altitude. The density of the air, of course, has a pronounced effect on aircraft and engine performance. Regardless of the actual altitude at which the aircraft is operating, it will perform as though it were operating at an altitude equal to the existing density altitude. For example, when set at 29.92 inches of mercury, the altimeter may indicate a pressure altitude of 5,000 feet. According to the AFM/POH, the ground run on takeoff may require a distance of 790 feet under standard temperature conditions. However, if the temperature is 20 degrees Celsius above standard, the expansion of air raises the density level. Using temperature correction data from tables or graphs or by deriving the density altitude with a computer, it may be found that the density level is above 7,000 feet, and the ground run may be closer to 1,000 feet. Air density is affected by changes in altitude, temperature, and humidity. High-density altitude refers to thin air, while low-density altitude refers to dense air. The conditions that result in high-density altitude are high elevations, low atmospheric pressures, high temperatures, high humidity, or some combination of these factors. Lower elevations, high atmospheric pressure, low temperatures, and low humidity are more indicative of low-density altitude. Using a flight computer, density altitude can be computed by inputting the pressure altitude and outside air temperature at flight level. Density altitude can also be determined by referring to the table and chart in Figures 10-3 and 10-4. Effects of pressure on density. Since air is a gas, it can be compressed or expanded. When air is compressed, a greater amount of air can occupy a given volume. Conversely, when pressure on a given volume of air is decreased, the air expands and occupies a greater space. That is, the original column of air at a lower pressure contains a smaller mass of air. In other words, the density is decreased. In fact, density is directly proportional to pressure. If the pressure is doubled, the density is doubled, and if the pressure is lowered, so is the density. This statement is true only at a constant temperature. Effects of temperature on density. Increasing the temperature of a substance decreases its density. Conversely, decreasing the temperature increases the density. Thus, the density of air varies inversely with temperature. This statement is true only at a constant pressure. In the atmosphere, both temperature and pressure decrease with altitude and have conflicting effects upon density. However, the fairly rapid drop in pressure as altitude is increased usually has the dominant effect. Hence, pilots can expect the density to decrease with altitude. Effects of humidity, moisture, on density. The preceding paragraphs are based on the presupposition of perfectly dry air. In reality, it is never completely dry. The small amount of water vapor suspended in the atmosphere may be negligible under certain conditions, but in other conditions humidity may become an important factor in the performance of an aircraft. Water vapor is lighter than air. Consequently, moist air is lighter than dry air. Therefore, as the water content of the air increases, the air becomes less dense, increasing density altitude and decreasing performance. It is lightest or least dense when, in a given set of conditions, it contains the maximum amount of water vapor. Humidity, also called relative humidity, refers to the amount of water vapor contained in the atmosphere and is expressed as a percentage of the maximum amount of water vapor the air can hold. This amount varies with the temperature. Warm air can hold more water vapor, while colder air can hold less. Perfectly dry air that contains no water vapor has a relative humidity of 0%, while saturated air that cannot hold any more water vapor has a relative humidity of 100%. Humidity alone is usually not considered an essential factor in calculating density altitude and aircraft performance. However, it does contribute. The higher the temperature, the greater amount of water vapor the air can hold. When comparing two separate air masses, the first warm and moist, both qualities making air lighter, and the second cold and dry, both qualities making it heavier, the first must be less dense than the second. Pressure, temperature, and humidity have a great influence on aircraft performance because of their effect upon density. There is no rule of thumb or chart used to compute the effects of humidity on density altitude, but it must be taken into consideration. Expect a decrease in overall performance in high humidity conditions. End of Part 1 of Chapter 10. Part 2 of Chapter 10 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 10. Aircraft Performance. Performance. Performance is a term used to describe the ability of an aircraft to accomplish certain things that make it useful for certain purposes. For example, the ability of an aircraft to land and take off in a very short distance is an important factor to the pilot who operates in and out of short, unimproved airfields. The ability to carry heavy loads, fly at high altitudes at fast speeds, or travel long distances is essential performance for operators of airline and executive-type aircraft. The primary factors most affected by performance are the takeoff and landing distance, rate of climb, ceiling, payload, range, speed, maneuverability, stability, and fuel economy. Some of these factors are often directly opposed. For example, high speed versus short landing distance, long range versus great payload, and high rate of climb versus fuel economy. It is the preeminence of one or more of these factors that dictates differences between aircraft and explains the high degree of specialization found in modern aircraft. The various items of aircraft performance result from the combination of aircraft and power plant characteristics. The aerodynamic characteristics of the aircraft generally define the power and thrust requirements at various conditions of flight, while power plant characteristics generally define the power and thrust available at various conditions of flight. The matching of the aerodynamic configuration with the power plant is accomplished by the manufacturer to provide maximum performance at the specific design condition, e.g. range, endurance, and climb. Straight and level flight. All of the principal components of flight performance involve steady-state flight conditions and equilibrium of the aircraft. For the aircraft to remain in steady level flight, equilibrium must be obtained by a lift equal to the aircraft weight and a power plant thrust equal to the aircraft drag. Thus, the aircraft drag defines the thrust required to maintain steady level flight. As presented in Chapter 4, Aerodynamics of Flight, all parts of an aircraft contribute to the drag, either induced from lifting surfaces or parasite drag. While the parasite drag predominates at high speed, induced drag predominates at low speed. Refer to Figure 10-5. For example, if an aircraft in a steady flight condition at 100 knots is then accelerated to 200 knots, the parasite drag becomes 4 times as great, but the power required to overcome that drag is 8 times the original value. Conversely, when the aircraft is operated in steady level flight at twice as great a speed, the induced drag is 1/4 the original value, and the power required to overcome that drag is only 1/2 the original value. When an aircraft is in steady level flight, the condition of equilibrium must prevail. The unaccelerated condition of flight is achieved with the aircraft trimmed for lift equal to weight and the power plant set for a thrust equal to the aircraft drag. The maximum level flight speed for the aircraft will be obtained when the power or thrust required equals the maximum power or thrust available from the power plant. Refer to Figure 10-6. The minimum level flight airspeed is not usually defined by thrust or power requirements, since conditions of stall or stability and control problems generally predominate. Climb performance. Climb performance is a result of using the aircraft's potential energy provided by one or a combination of 2 factors. The first is the use of excess power above that required for level flight. An aircraft equipped with an engine capable of 200 horsepower at a given altitude, but using 130 horsepower to sustain level flight at a given airspeed, has 70 excess horsepower available for climbing. A second factor is that the aircraft can trade off its kinetic energy and increase its potential energy by reducing its airspeed. The reduction in airspeed will increase the aircraft's potential energy, thereby also making the aircraft climb. Both terms, power and thrust, are often used in aircraft performance. However, they should not be confused. Although the terms power and thrust are sometimes used interchangeably, erroneously implying that they are synonymous, it is important to distinguish between the two when discussing climb performance. Work is the product of a force moving through a distance and is usually independent of time. Work is measured by several standards. The most common unit is called a foot-pound. If a 1-pound mass is raised 1 foot, a work unit of 1 foot-pound has been performed. The common unit of mechanical power is horsepower. 1 horsepower is work equivalent to lifting 33,000 pounds a vertical distance of 1 foot in 1 minute. The term power implies work rate, or units of work per unit of time, and as such is a function of the speed at which the force is developed. Thrust, also a function of work, means the force that imparts a change in the velocity of a mass. This force is measured in pounds but has no element of time or rate. It can be said, then, that during steady climb, the rate of climb is a function of excess thrust. This relationship means that, for a given weight of an aircraft, the angle of climb depends on the difference between the thrust and drag, or the excess power. Refer to Figure 10-7. Of course, when the excess thrust is 0, the inclination of the flight path is 0, and the aircraft will be in steady level flight. When the thrust is greater than the drag, the excess thrust will allow a climb angle depending on the value of excess thrust. On the other hand, when the thrust is less than the drag, the deficiency of thrust will allow an angle of descent. The most immediate interest in the climb angle performance involves obstacle clearance. The most obvious purpose for which it might be used is to clear obstacles when climbing out of short or confined airports. The maximum angle of climb would occur where there exists the greatest difference between thrust available and thrust required, i.e., for the propeller-powered airplane, the maximum excess thrust and angle of climb will occur at some speed just above the stall speed. Thus, if it is necessary to clear an obstacle after takeoff, the propeller-powered airplane will attain maximum angle of climb at an airspeed close to, if not at, the takeoff speed. Of greater interest in climb performance are the factors that affect the rate of climb. The vertical velocity of an aircraft depends on the flight speed and the inclination of the flight path. In fact, the rate of climb is the vertical component of the flight path velocity. For rate of climb, the maximum rate would occur where there exists the greatest difference between power available and power required. Refer to Figure 10-8. The above relationship means that, for a given weight of an aircraft, the rate of climb depends on the difference between the power available and the power required, or the excess power. Of course, when the excess power is 0, the rate of climb is 0 and the aircraft is in steady level flight. When power available is greater than the power required, the excess power will allow a rate of climb specific to the magnitude of excess power. During a steady climb, the rate of climb will depend on excess power, while the angle of climb is a function of excess thrust. The climb performance of an aircraft is affected by certain variables. The conditions of the aircraft's maximum climb angle or maximum climb rate occur at specific speeds, and variations in speed will produce variations in climb performance. There is sufficient latitude in most aircraft that small variations in speed from the optimum do not produce large changes in climb performance, and certain operational considerations may require speeds slightly different from the optimum. Of course, climb performance would be most critical with high gross weight, at high altitude, in obstructed takeoff areas, or during malfunction of a power plant. Then, optimum climb speeds are necessary. Weight has a very pronounced effect on aircraft performance. If weight is added to an aircraft, it must fly at a higher angle of attack, AOA, to maintain a given altitude and speed. This increases the induced drag of the wings, as well as the parasite drag of the aircraft. Increased drag means that additional thrust is needed to overcome it, which in turn means that less reserve thrust is available for climbing. Aircraft designers go to great effort to minimize the weight, since it has such a marked effect on the factors pertaining to performance. A change in an aircraft's weight produces a twofold effect on climb performance. First, a change in weight will change the drag and the power required. This alters the reserve power available, which in turn affects both the climb angle and the climb rate. Secondly, an increase in weight will reduce the maximum rate of climb, but the aircraft must be operated at a higher climb speed to achieve the smaller peak climb rate. An increase in altitude also will increase the power required and decrease the power available. Therefore, the climb performance of an aircraft diminishes with altitude. The speeds for maximum rate of climb, maximum angle of climb, and maximum and minimum level flight airspeeds vary with altitude. As altitude is increased, these various speeds finally converge at the absolute ceiling of the aircraft. At the absolute ceiling, there is no excess of power, and only one speed will allow steady level flight. Consequently, the absolute ceiling of an aircraft produces zero rate of climb. The service ceiling is the altitude at which an aircraft is unable to climb at a rate greater than 100 feet per minute, FPM. Usually, these specific performance reference points are provided for the aircraft at a specific design consideration. Refer to Figure 10-9. In discussing performance, it frequently is convenient to use the terms power loading, wing loading, blade loading, and disc loading. Power loading is expressed in pounds per horsepower and is obtained by dividing the total weight of the aircraft by the rated horsepower of the engine. It is a significant factor in an aircraft's takeoff and climb capabilities. Wing loading is expressed in pounds per square foot and is obtained by dividing the total weight of an airplane in pounds by the wing area, including ailerons, in square feet. It is the airplane's wing loading that determines the landing speed. Blade loading is expressed in pounds per square foot and is obtained by dividing the total weight of a helicopter by the area of the rotor blades. Blade loading is not to be confused with disc loading, which is the total weight of a helicopter divided by the area of the disc swept by the rotor blades. Range performance. The ability of an aircraft to convert fuel energy into flying distance is one of the most important items of aircraft performance. In flying operations, the problem of efficient range operation of an aircraft appears in two general forms. 1. To extract the maximum flying distance from a given fuel load. 2. To fly a specified distance with a minimum expenditure of fuel. A common element for each of those operating problems is the specific range, that is, nautical miles, NM, of flying distance versus the amount of fuel consumed. Range must be clearly distinguished from the item of endurance. Range involves consideration of flying distance, while endurance involves consideration of flying time. Thus, it is appropriate to define a separate term, specific endurance. Specific endurance equals flight hours divided by pounds of fuel, or specific endurance equals flight hours per hour divided by pounds of fuel per hour, or specific endurance equals 1 divided by the fuel flow. Fuel flow can be defined in either pounds or gallons. If maximum endurance is desired, the flight condition must provide a minimal fuel flow. In Figure 10-10, at point A, the airspeed is low and the fuel flow is high. This would occur during ground operations or when taking off and climbing. As airspeed is increased, power requirements decrease due to aerodynamic factors, and fuel flow decreases to point B. This is the point of maximum endurance. Beyond this point, increases in airspeed come at a cost. Airspeed increases require additional power, and fuel flow increases with additional power. Cruise flight operations for maximum range should be conducted so that the aircraft obtains maximum specific range throughout the flight. The specific range can be defined by the following relationship. Specific range equals nautical miles divided by pounds of fuel, or specific range equals nautical miles per hour divided by pounds of fuel per hour, or specific range equals knots divided by fuel flow. If maximum specific range is desired, the flight condition must provide a maximum of speed per fuel flow. While the peak value of specific range would provide maximum range operation, long-range cruise operation is generally recommended at some slightly higher airspeed. Most long-range cruise operations are conducted at flight condition that provides 99% of the absolute maximum specific range. The advantage of such operation is that 1% of range is traded for 3 to 5% higher cruise speed. Since the higher cruise speed has a great number of advantages, the small sacrifice of range is a fair bargain. The values of specific range versus speed are affected by three principal variables. 1. Aircraft gross weight. 2. Altitude. 3. The external aerodynamic configuration of the aircraft. These are the source of range and endurance operating data included in the performance section of the AFM/POH. Cruise control of an aircraft implies that the aircraft is operated to maintain the recommended long-range cruise condition throughout the flight. Since fuel is consumed during cruise, the gross weight of the aircraft will vary, and optimum airspeed, altitude, and power setting can also vary. Cruise control means the control of the optimum airspeed, altitude, and power setting to maintain the 99% maximum specific range condition. At the beginning of cruise flight, the relatively high initial weight of the aircraft will require specific values of airspeed, altitude, and power setting to produce the recommended cruise condition. As fuel is consumed and the aircraft's gross weight decreases, the optimum airspeed and the power setting may decrease, or the optimum altitude may increase. In addition, the optimum specific range will increase. Therefore, the pilot must provide the proper cruise control procedure to ensure that optimum conditions are maintained. Total range is dependent on both fuel available and specific range. When range and economy of operation are the principal goals, the pilot must ensure that the aircraft is operated at the recommended long-range cruise condition. By this procedure, the aircraft will be capable of its maximum design operating radius or can achieve flight distances less than the maximum with a maximum of fuel reserve at the destination. A propeller-driven aircraft combines the propeller with the reciprocating engine for propulsive power. Fuel flow is determined mainly by the shaft power put into the propeller rather than thrust. Thus, the fuel flow can be related directly to the power required to maintain the aircraft in steady level flight, and on performance charts, power can be substituted for fuel flow. This fact allows for the determination of range through analysis of power required versus speed. The maximum endurance condition would be obtained at the point of minimum power required, since this would require the lowest fuel flow to keep the airplane in steady level flight. Maximum range condition would occur where the ratio of speed to power required is greatest. Refer to Figure 10-10. The maximum range condition is obtained at maximum lift to drag ratio, L/D max, and it is important to note that for a given aircraft configuration, the L/D max occurs at a particular AOA and lift coefficient, and is unaffected by weight or altitude. A variation in weight will alter the values of airspeed and power required to obtain the L/D max. Refer to Figure 10-11. The variations of speed and power required must be monitored by the pilot as part of the cruise control procedure to maintain the L/D max. When the aircraft's fuel weight is a small part of the gross weight and the aircraft's range is small, the cruise control procedure can be simplified to essentially maintaining a constant speed and power setting throughout the time of cruise flight. However, a long-range aircraft has a fuel weight that is a considerable part of the gross weight, and cruise control procedures must employ scheduled airspeed and power changes to maintain optimum range conditions. The effective altitude on the range of a propeller-driven aircraft is illustrated in Figure 10-12. A flight conducted at high altitude has a greater true airspeed, TAS, and the power required is proportionally greater than when conducted at sea level. The drag of the aircraft at altitude is the same as the drag at sea level, but the higher TAS causes a proportionately greater power required. Note, the straight line that is tangent to the sea level power curve is also tangent to the altitude power curve. The effect of altitude on specific range also can be appreciated from the previous relationships. If a change in altitude causes identical changes in speed and power required, the proportion of speed to power required would be unchanged. The fact implies that the specific range of a propeller-driven aircraft would be unaffected by altitude. Actually, this is true to the extent that specific fuel consumption and propeller efficiency are the principal factors that could cause a variation of specific range with altitude. If compressibility effects are negligible, any variation of specific range with altitude is strictly a function of engine/propeller performance. An aircraft equipped with a reciprocating engine will experience very little, if any, variation of specific range up to its absolute altitude. There is negligible variation of brake-specific fuel consumption for values of brake horsepower below the maximum cruise power rating of the engine that is the lean range of engine operation. Thus, an increase in altitude will produce a decrease in specific range only when the increased power requirement exceeds the maximum cruise power rating of the engine. One advantage of supercharging is that cruise power may be maintained at higher altitude, and the aircraft may achieve the range at high altitude with the corresponding increase in TAS. The principal differences in the high-altitude cruise and low-altitude cruise are the TAS and climb fuel requirements. Region of reversed command. The aerodynamic properties of an aircraft generally determine the power requirements at various conditions of flight, while the power plant capabilities generally determine the power available at various conditions of flight. When an aircraft is in steady level flight, a condition of equilibrium must prevail. An unaccelerated condition of flight is achieved when lift equals weight and the power plant is set for thrust equal to drag. The power required to achieve equilibrium in constant altitude flight at various airspeeds is depicted on a power required curve. The power required curve illustrates the fact that at low airspeeds near the stall or minimum controllable airspeed, the power setting required for steady level flight is quite high. Flight in the region of normal command means that while holding a constant altitude, a higher airspeed requires a higher power setting, and a lower airspeed requires a lower power setting. The majority of aircraft flying, climb, cruise, and maneuvers, is conducted in the region of normal command. Flight in the region of reversed command means flight in which a higher airspeed requires a lower power setting, and a lower airspeed requires a higher power setting to hold altitude. It does not imply that a decrease in power will produce lower airspeed. The region of reversed command is encountered in the low-speed phases of flight. Flight speeds below the speed for maximum endurance, lowest point on the power curve, require higher power settings with a decrease in airspeed. Since the need to increase the required power setting with decreased speed is contrary to the normal command of flight, the regime of flight speeds between the speed for minimum required power setting and the stall speed, or minimum control speed, is termed the region of reversed command. In the region of reversed command, a decrease in airspeed must be accompanied by an increased power setting in order to maintain steady flight. Figure 10-13 shows the maximum power available as a curved line. Lower power settings such as cruise power would also appear in a similar curve. The lowest point on the power required curve represents the speed at which the lowest brake horsepower will sustain level flight. This is termed the best endurance airspeed. An airplane performing a low airspeed, high-pitch attitude power approach for a short field landing is an example of operating in the region of reversed command. If an unacceptably high sink rate should develop, it may be possible for the pilot to reduce or stop the descent by applying power. But without further use of power, the airplane would probably stall or be incapable of flaring for the landing. Merely lowering the nose of the airplane to regain flying speed in this situation without the use of power would result in a rapid sink rate and corresponding loss of altitude. If during a soft field takeoff and climb, for example, the pilot attempts to climb out of ground effect without first attaining normal climb pitch attitude and airspeed, the airplane may inadvertently enter the region of reverse command at a dangerously low altitude. Even with full power, the airplane may be incapable of climbing or even maintaining altitude. The pilot's only recourse in this situation is to lower the pitch attitude in order to increase airspeed, which will inevitably result in a loss of altitude. Airplane pilots must give particular attention to precise control of airspeed when operating in the low flight speeds of the region of reverse command. End of Part 2 of Chapter 10.